What's up, guys? In this video, I want to go over polynomials. So I went through my back catalog of all the videos I had on polynomials, hundreds of videos on polynomials, and I hand selected 90 videos that I want you to focus on to get a better understanding of polynomials. We talk about the basic definition of a polynomial, how to identify a polynomial, leading coefficient, the degree. We talk about simplifying polynomials, multiplying, adding, subtracting, simplifying using the rules of exponents. And then we get into things that are a little bit more exciting, like long division, synthetic division, factoring polynomials, finding all the zeros, multiplicity, graphing polynomials, as well as dealing with the factor theorem and the remainder theorem, Descartes' rule of signs, all the really good fun stuff. So we start with the most basic and work all the way to the end. And I can guarantee you, if you go through this whole video, you are going to have a much better understanding of polynomials. I look forward to seeing you at the end. Cheers.
In this example, they're asking us to identify what is the degree and the leading coefficient, right? Yes? The sign of the leading coefficient and what the degree would be. Now, ladies and gentlemen, we look at this graph. Let's look at the end behavior. In reality, this does not matter. It does not matter what the graph looks like. The graph could look like this. Do these two graphs have the same end behavior? Yes, they both do what? As the graph goes to the left, they're doing what? Going down or falling, right? As we go to the right, the graph is falling. So all you needed to do for these problems is go and look at your notes and say what is the degree and the leading coefficient when the graph falls left and falls right. Because I showed you graphs that look like this, but it doesn't matter what the graph looks like. If you erase the graph, do you guys agree with me they have the same end behavior? They both fall left and they both fall right. So in this, the degree has to be, anybody find it yet? Degree has to be even or odd? Even. And the LC has to be positive or odd. Oh, I'm sorry. Negative. I'm starting to do what you guys are doing. Negative. Does that make sense? Más o menos? Yes? Welcome. All right. So in this case, what we want to do is determine our leading coefficient and our degree, as well as classify the polynomial. However, remember, there's a couple rules. Before we can classify the polynomial, we need to make sure we go through our rules of what a polynomial is to make sure that it doesn't break any of the rules, so therefore we can classify it. Now, in this case, you see that we have 3 terms in the numerator and 2 terms in the denominator, which automatically brings up a red flag to me because I don't remember classifying polynomials having stuff in the numerator and denominator. So that brings up exactly my point when one of the rules of, if you have a polynomial or not, you cannot have a variable in the denominator. So therefore, this equation, which is a rational equation, is not a polynomial as per our definition of a polynomial. You cannot have a variable in the denominator. So therefore, we can't classify it as a polynomial, nor can we determine the leading coefficient and the degree. Sorry, but that's the way it is. Thanks. Welcome, ladies and gentlemen. So what I'd like to do is show you how to classify the polynomial, determine the leading coefficient and the degree, as well as determine if it's a polynomial or not. Now, remember, when our rules of polynomials, what we want to do is we want to make sure that each one of our monomials create our polynomial. But to consider it a monomial, there's a couple things that have to happen. One, we cannot have any negative exponents or any negative powers. So we look here, we have no negative powers. But also it goes with negative powers is variables in the denominator, because x to the negative first is the same thing as 1 over x. All right. The next thing is we cannot have variables multiply by each other. So we can't have x2 times the y, which in here I don't have any multiple x's here, so that's good. And then lastly is I can't have my two different variables, as I can't have the square root of x, but also, or any roots of x, or with roots, that also means rational powers, because rational powers and roots are really the same thing. Well, in this case, you can see I have a polynomial with rational powers, so therefore this is not an example of a polynomial, and therefore I cannot classify it as one or really move forward with the leading coefficient or degree because it's not a polynomial. Thanks. Welcome. What I want to do is show you how to classify this polynomial. So what we have here is we have negative 4n squared. And when we're looking at this,
one thing is, since I only have this like as one term, I'm not adding or subtracting anything. I know it can't be a binomial, as a binomial is the addition of two monomials. It can't be a trinomial, which would be the addition of three monomials. So this is actually just going to be a monomial, meaning I just have one collective term together. So this is a monomial. Because the definition of a monomial is a number or a variable or the multiplication of a number and one or more variables, which exactly this is. But this is a very special type of monomial because we look at the degree, and the degree is going to be your exponent. And I see that this has a degree of 2. And something special when we talk about polynomials with degree of 2, we want to see, can we write them in quadratic form? And when we look at this, the quadratic form is, you can say ax squared plus bx plus 3. Well, very much I can write this in quadratic form if I said my b was equal to 0 and c was also equal to 0. Therefore, this would be its quadratic form of this monomial. So therefore, whenever you have a degree to your second power, you can write it in the quadratic form. We could say this is going to be a quadratic monomial, since it's to your degree 2 and can be put in the quadratic form. There you go. Welcome. What I want to do is show you how to classify this polynomial. So what I have is 6b to the 4th minus 8b cubed minus b to the 8th minus b. So the first thing we want to do when we're classifying polynomials is we want to make sure they're in standard form, meaning that they're in descending order of our exponents, or what we call our degrees. So what I want to do is I want to make sure I write my largest degree or exponent first. So here my largest exponent is 8. So I'm going to take that term, which is negative b to the 8th, and I'm going to write that first. Then what I'm going to do is write in going down in descending order. So the next term with the largest exponent would be b to the 4th. So that's a positive 6 b to the 4th. Then I have negative 8 b cubed minus b. Now that it's in descending order, with the largest exponent first going all the way down, I can look at that largest exponent and say, all right, what is that number? That's going to be 8, which is going to be my degree. So that is going to be the degree of a polynomial. So I'm going to have a degree, which is going to be equal to 8. Then I need to classify the polynomial. Well, when a polynomial has one term, we call it one term we're going to call it monomial. A polynomial, when we're adding 2 terms, we're going to call it binomial. When we add 3 terms, we're going to have a trinomial. And anything, or if we're going to say polynomial with, for how many terms it has. So this is going to be a polynomial with 4 terms. Because you can say I have 1, 2, 3, 4 terms with a degree of 8. All right, thank you.
So ladies and gentlemen, what we're going to do for this type of problem is going to take a look at how to determine the leading coefficient and the degree. And that's all we're going to be able to find out, just the leading coefficient and the degree. We'll talk about end behavior in a little bit. So to go through this, to find leading coefficient and degree, remember, to find our degree, we have to find the monomial in your polynomial that has the largest degree, which is going to be your largest exponent. So the main important thing, what we're going to do, is we want to make sure we put this in descending order. So therefore, we're going to take the largest degree, the monomial with the largest degree, and we're going to list that first. And then we're going to go down in descending order, which we'll call standard form of a polynomial. So we look at our degree, and we say, all right, the largest degree is right there, 6. So we're going to take that whole monomial and write that first. So we have 7y to the 6th. Then the next one, largest degree, is 5. So we now take that whole monomial and write that next, which is a negative y to the 5th. Then the next highest degree is my y squared. So I take that whole monomial, which is plus 5y squared. Then y, when we don't have it raised to a power, we don't show it being raised to a power, we know it's being raised to a 1. So that would be your next largest. So you take the whole monomial, and then this can really be raised to y to the 0, which we don't write. But we just notice that that's going to be my last term, which is my constant, plus 18. OK, so now I have this in descending order from largest degree to smallest degree. So to define the degree is obviously going to be our monomial with the largest degree, and that largest degree is 6. So we say degree of the polynomial is 6. Then our leading coefficient is the coefficient of that leading term, which is 7. That's all you got to do. Here, ladies and gentlemen, we have a polynomial function, f of x equals a n of x to the n plus a n minus 1 x to the n minus 1 plus a n minus 2 x n minus 2. And you look at it and you're like, what the heck is that? Why would he write even something like that? It just looks crazy, right? And I understand, it really is something crazy. But there's a couple things I want you guys to understand. The reason why I gave you guys a general form. The first thing I want you guys to understand is, do you guys agree that if n was a number, that this number would be the highest? Because if you had, let's say n was 8, well, the next one would be 8 minus 1. The next one would be 8 minus 2. So do you guys agree with me that n right there, that is the largest power, right? So what I want you to understand is this is our formal way of writing a polynomial with the largest power first. So that n is also what we call our degree, which we kind of talked about, which n behavior, wherever that was. We talked about n behavior as your degree. Then a sub n just represents, again, a coefficient of that exponent is what we call the leading coefficient, or I will more often than not just call that your LC. All right? So the main important thing when determining if we have a polynomial or not is the powers of a polynomial must be non-negative, which is a fancy way of saying positive, and they have to be integers. Please remember, integers are going to be your whole numbers, but they're going to be negative, and they can be positive. Or I'm sorry, integers are only going to be are positive. OK, so here we have f of x equals x to the 4th minus square root of 2, x squared plus 3. So if you're going to determine if this is a polynomial or not, all you simply need to do is go by inspection and look at your powers. Are your powers non-negative integers? Yes. Yes. This looks a little confusing, and I'm kind of here to trick you because I gave you a square root as a coefficient, but that's not a power, so it's OK. So yes, this is a polynomial. Then what I'd like you to do is determine what is the degree and I messed this one up. What is the degree and the leading coefficient? Well, you can see that 4 is the largest power, and 4, and then there's 2. So 4 is my degree. And the leading coefficient is going to be the number in front of my exponent, x to the 4th, which in this case is 1. Does everybody see that? OK. This one, we have fractions as our powers. So this is not an example of a polynomial. Please also note, if you see any radicals, if you guys remember from rational exponents, radicals is the same thing as a rational power. So if you see any radicals, that's going to show it's not a polynomial as well. Yes, Anastasia?
So if there's a fraction in the exponent, then it's not.
Correct. Or if your variable is a radical of any sort, because that's the same thing as a fraction. Because this would be x to the 2/3 is the same thing as the cube root of x squared. If you guys remember your rational exponents.
Is the x under the square root?
In this one? No, it's not. That's why I said that one's a polynomial. But I kind of threw it there to trick you. So that one's not a polynomial. The next one, you can't have any negative powers. Because basically, you can't have any non-negative integers as your powers, or you can't have variables in the denominator. Because what is x to the negative first? What is that really? That's the same thing as 1 over x. You can't have x in the denominator. So rational functions, where you had a polynomial up top and a polynomial down below, is not actually a polynomial of itself. It's a function. But you can't have polynomials in the numerator and the denominator. So this one is not a polynomial. And the last one, here's a fraction, but is there any denominator in there? Is there any variable in the denominator? No. So actually, this is, remember that 5 divides into all of those terms. So that's really 7/5 x squared plus x plus 1/5, because the 5 is divided to 1. So now we again look at the highest power, which in this case is 2. So my degree is 2, and my leading coefficient is 7/5. A lot of students will write the leading coefficient as 7. That's why I had to give you guys that example. So just be careful. Yes? Welcome, ladies and gentlemen. So what I like to do is show you how to simplify using our rules of exponents. And basically, remember, when we're looking into using a rule of exponent, if I have x to the negative a, to rewrite that as a positive, I'm just going to rewrite that now in my denominator. So basically, what I'll have is 5 times 1 over x to the positive third times 1 over y to the positive fifth. Therefore, when I multiply across, I get 5 over x cubed times y to the fifth. So make sure when you have a negative exponent, you rewrite them as a positive exponent in the denominator. And the 5 was always kind of in the numerator, so I can just leave that up there. Thanks. So in this case, again, what we have here is we have the power to product rule up top. So we want to apply the power to product rule. So therefore, that becomes 3 squared a cubed squared over 18a. 3 squared is obviously 9. A cubed raised to the second, you multiply the powers. That's a to the 6th divided by 18, a. Remember, you always want to reduce your fraction. 9 over 18 is 1/2. A to the 6th divided by a would be a to the 5th. Or you could also subtract your powers. So it becomes a to the 5th in the numerator. And then obviously, we don't really need to write the 1 up there. So the final answer, you could say a to the 5th over 2. Welcome. What I want to do is show you how to find the simplest answer to this expression. So I wrote down the rules of exponents that I'm going to use in this problem, and I'm going to try to touch base on almost all of them, except for the division, as this one doesn't have any division in here. But I'm going to go through each one of these rules as I'm explaining how I'm going to use them to simplify it. So the first thing I want to do is part of PEMDAS. I see I have parentheses up here, so I'm going to want to make sure I distribute to get rid of those parentheses. So what I notice is I have a term here with a couple exponents raised to another power. So when I have something raised to another power, what I notice is I'm going to multiply my two exponents. Well, sometimes we have exponents, sometimes we don't. You can see here, this 2 does not have an exponent. So we can put in the number 1 because 2 raised to the first power we know equals 2. Now, the next thing we need to understand is, when we have a number outside an exponent, that exponent is going to distribute to all of our terms inside. We have a number inside our parentheses. That exponent is going to distribute to every single number inside of the parentheses. So therefore, I really have 2 to the 1 times 4, which is 2 to the 4th, x to the 0 times 4, which is x to the 0, and y to the negative 4th, times a negative 2, x to the 5th, y to the 4th. Now, x raised to the 0 power is going to equal 1. That's actually another kind of rule we can talk about. So therefore, that's going to equal 1. That's going to kind of, what we can say, is just cancel out. 2 raised to the 14th power is going to, or 14th power. 2 raised to the 4th power is going to give me 16. Now, y to the negative 4th, before I do anything with this, before I even notice this and say, oh, you can put it below, what I can do is I can say, well, I'm multiplying y times y, so I can say y to the negative 4th plus 4 times negative 2 x to the 5th. Well, a negative 4 plus 4 is going to give me 0 again. And like x to the 0, y to the 0 is going to cancel out. So therefore, I'll be left with x times negative 2 x to the 5th. Well, now all last I have to do is multiply my 16 times my negative 2, which will give me a negative 32 times x to the 5th. And that is simply all we need to do. Just make sure we know our multiplication rule to add our two exponents. And that's it. That's all we'll need to do to simplify our answer. Thanks very much. In this example, there's a couple things that I like to do. First of all, it's not always necessary, but I always like to rewrite without negative powers. So since I have a negative power on this outside, I got to make that positive before I can do anything else. So the first thing I'm going to do is I'm going to make this positive. So what I'm going to do is I'm going to move this up to the numerator. So therefore, this is now 3 times x squared y raised to the 3rd power times 9x to the negative 3rd y squared. Does everybody see what I did? All I did was I took my denominator and brought it up because that this whole denominator is being raised to a negative second power. So you have to take the whole expression up. Just also a little FYI, you don't need to write this, but if I had a 5 down here, that 5 would still remain down there. Because the 5 is not being raised to the negative power. Yes, Logan. Well, what I'm trying to tell you is dividing by an expression with a negative power is the same thing as multiplication. It's the same thing. Let me put it to you this way. 5 to the negative first power is equal to what? 1 over 5. So if I said 5 times 5 to the negative first, that's really the same thing as 5 times 1 over 5, which is the same thing as 5 divided by 5. So yeah, multiplication of a number to a negative power is the same thing as dividing. Huh? I'll come to you in a second, because that's in your notes. All right, I do want to move on. So now we need to apply the power to product rule. I do not have any addition or subtraction, so I will distribute. Now, notice I am not distributing the 3 to that 3, because that 3 is not inside the parentheses. So you don't need to apply distributive property to that. So I now obtain 3 times, is it OK if I don't rewrite everything? Can I do the math with the distributing here? Well, it's power to product rule, so you're going to be multiplying all of these. So 3 times 2 is 6, y to the third. Then I have 9 squared, which would be 81. X to the negative 3 times 2 is x to the negative 6, and then y squared. OK? Now, again, we're multiplying. There's no really addition. We really don't need these parentheses. But notice I still have a negative. X to the negative power, we need to write that as positive. So I need to put that in the denominator. Then 81 times 3, 81 is 162, 243. 81 times 3. You can multiply those 81 times 3.
Wait, are you distributing?
I'm not distributing. Notice 3 times 4 times 5 is the same thing as 4 times 5 times 3. Right? Doesn't matter how you, when you have just numbers multiplied, look at these are all multiplied. It doesn't matter what order I multiply them. I can multiply 3 times 81. Do you agree? Or do you need me to reorder them? Yes?
Please, could you please run that first fraction? Why did you multiply?
Guys, watch. You guys agree with me? 3 times 4 times 5, right? That is 60. Watch. Parentheses first. 3 times 4 is 12. 12 times 5 is 60. OK? Let's put parentheses over here. 4 times 5 is 20. 20 times 3 is 60. Parentheses are grouping symbols, right? Grouping is very, very important, especially when we're doing addition and subtraction, because we got to group what we want to do first. However, when you have multiplication, grouping doesn't really matter which one we do. It doesn't matter if I do 3 times 4 first and then multiply by 5, or 4 times 5 and then multiply by 3. The grouping symbols was just a way for us to, we had to use the grouping symbols because what the grouping symbols told us is what to raise to our powers. But now that I've raised all my powers to their numbers, I don't need the grouping symbols anymore. Yes?
So you're saying that if 3 were multiplied to the first, like all the numbers in the first parentheses, it would equal to the same amount as if you multiplied it by 81x to the negative 6? Would it equal
I didn't follow you the same.
Okay. So if it was 3 times x to the power of 6 and y to the power of 3, would it equal the same amount as what you're doing right now?
Yeah. All I'm doing, guys, you can reorder this any way you want. So reorder them so the numbers and variables are next to each other. Yes, Logan, do you have a question as well? Shh. Low to extra.
So instead of multiplying 3 by 81, saying you can multiply 3 by x to the 6, like the first one, you would have to go to 81. Like multiply any of them.
Yeah, as long as there's no addition and subtraction, you can just multiply them any way you want to.
You're just distributing it any
I'm not distributing at all because there's no addition or subtraction. Distributing property is like this when you distribute to all of them. I don't need to, I can't, the thing is, guys, yes, you're just multiplying like terms. You can't multiply 3 times a variable. 3 times x is just 3 times x. The only thing I can multiply 3 by is 81. So that's what I'm doing. I can only multiply x by x. So you put them next to each other. Yes? No, it's just multiplied. Again, they're all multiplied. When they're multiplied, guys, you rearrange them. Yes?
So if there were other coefficients, you would multiply 3 by those.
Yeah, absolutely. If we had a coefficient, like if I had a 2 there or whatever else, then yeah.
But you said 2 is at the bottom, right?
Yeah, it would stay at the bottom. But you would divide that through. All right, there is a couple other points I still want to highlight. 3 times 81, I said, was 284. 243. Shh. I'm still not done with the problem. X to the 6 times x to the negative 6. When you multiply, you add the powers, which would give me x to the 0. And then y to the 3rd times y squared is y to the 5th, which, if you guys looked at your 0 power rule, you would see that my final answer, x to the 0, is 1. So my final answer is y to the 5th. OK? In this example, ladies and gentlemen, what they basically ask is divide f of x divided by g of x, if you guys can see in the problem. And then they tell us what is f of x and what is g of x. So basically, when we're dividing, all you're simply doing is taking one function divided by the second function. All right? So that's what simply, when it tells us to divide those two functions. So you put one function above the other function. And now we have to simplify. Now, if you guys remember, we talked about when we're simplifying using these, we want to use the rules of exponents. Where you guys remember when you multiply, you add powers, right? When you divide, you subtract the powers. When you have a power raised to another power, you multiply them. And there's also the negative exponents, which we'll talk, or negative powers, we'll talk about here in a second. But one of the main important ones we also talked about was whenever you have an exponent raised to the 0 power, it always equaled the number 1. Always equaled 1. It does not matter what the number is. Whenever I have an exponent where the power is 0, it's going to equal 1. So in this case, you guys can see I have an exponent here. This is a crazy base, right? But it's raised to the 0 power. Go and rock over that way, please. So therefore, what you guys can see is this just goes to 1. Therefore, it's x squared over y to the negative 5th. Now, to further simplify this, remember we cannot have negative exponents. What we talked about was x to the negative m equals 1 over x to the m. So if I have 1 over x to the negative m, to write this as positive, I'd write it up in the numerator. So therefore, y to the negative 5th, to write this as the positive, is going to be y to the 5th over x squared. And that would be your final answer. So when Alex is paying attention to this, what he's going to notice, all right, is we need to look back on our couple of property of exponents. When I'm dealing with properties of exponents, ladies and gentlemen, the main important thing I always want to do is make sure I'm always working with positive exponents, because we can't leave our answer with the negative exponents. All right? So we got to work with positive exponents. So right now, I have a rational expression raised to a negative exponent. So how can I rewrite that so it's a positive exponent? Well, by looking at your property of exponents, you guys should notice that when I have a divided by b raised to a negative exponent, so when I have a rational expression raised to a negative exponent, to make that positive, I simply just need to take the reciprocal of that and raise it to a positive exponent. And there's a reason why, because if you put that under 1, and I can go through the whole explanation. But just so you understand, if you have a divided by b raised to a negative exponent, to make that exponent positive, you just need to make sure you're dealing with the reciprocal of your term. Do you guys see how that kind of works? Okay, went through whole explanations already before. So let's just go through this. So therefore, I want to make sure I deal with the positive exponent. Therefore, I need to take the reciprocal of my rational function. Okay, so then I flip the inside, and now I can make that a positive exponent. That's kind of step number one. The second step is the power to product rule. So that's step number one. Second step is power to product rule. And what the power of product rule says is if I have a product raised to a power, then that power is distributed to both of my terms in the product, meaning that goes a to the n and b to the n. That also works for my product and my quotient. If I have a divided by b raised to the n, that equals a to the n over b to the n. So what this is telling me right now is everything inside of here needs to be raised to the second power. Everything. So therefore, what I'm going to do is just rewrite everything to the second power. So negative x squared squared y to the fifth squared over 2 squared x cubed squared and y squared squared. Does everybody see that? So the first thing you apply is being the reciprocal. Then you use the power and quotient of power. Then the third one is you're going to use the power of power rule, which states if you have a raised to an exponent raised to an exponent, then that simply means a to the m times n. So now you're going to multiply the two powers. So on my final step, I'll have negative x squared squared. That's going to, so negative x squared times negative x squared is now going to be a positive x to the fourth. Then I have y to the 10th divided by 4 x to the 6th y to the 4th. Anybody have any questions on that? Everybody see it? No? Questions? Good. I used 3 properties of exponents to help me simplify. Get something different, JD? What do you think? I can't remember. 16. Okay. Huh? Oh, yeah, I forgot. Jeez. No wonder. I was thinking I was saying. Yes. So our last simplify, thank you. So our last one that we're going to look into, it's been a while. It's been a couple weeks since we were looking at these. Yeah, now we can simply just go through with the division. Our last exponent property, remember, states that now when you have an exponent dividing, then you do a to the n minus m, right? So let's simplify these. So x to the 4th divided by x to the 6th. So that's going to give me, so I have 4 x to, I'm sorry, 4th x to the 4 minus 6, and then y to the 10th minus 4. Well, let's go and write my answers back over here. So therefore, that becomes x to the negative 2nd, y to the 6th times 1/4. So therefore, this now has to make sure it's on the denominator, right? So therefore, my final answer is going to be y to the 6th over 4x squared. Is that a more simplified answer? Is that what you ended up getting? Good. Yes, you got to make sure you simplify it. Thank you so much, Hazel. I don't know how I forgot to do the last step. If you guys remember this last one, if you guys remember we talked about this one, I said rather than multiplying all this out, we can just start eliminating stuff as the problem is, right? Because do you guys really want to do 24 times 10 and then do 5 times 8 and then start dividing it all? It's going to get a little messy, right? So let's just start seeing this. Well, 24 over 5, that does not reduce, right? But does 5 and 10, can we reduce that? Yeah, we can say 2 over 1, right? And does 24 over 8, does that reduce? What is it? 3 over 1, because that reduces to the 3, and that would go to a 1, right? OK. So now, then this, so now we have this problem. So now we have 3 g cubed times 2, and then gf cubed is going to be g cubed f cubed, right? Over f squared times g to the 5th times f. OK, so now we can start canceling. We can start eliminating some again. Here we go. This is f cubed, right? F squared times f. That's going to be f to the 3rd power. Yes? Well, divided by f to the 3rd power, what do? You do subtract them, right? So guess what? These all divide into 1, right? Because this is f cubed on the bottom when I multiply that. And then over here, I'm going to finally get 3g to the 6th power over g to the 5th. Well, those you subtract to get g to the 1st. So the final answer is 3g to the 1st. Oh, that's the 6, right? Yeah, I'm sorry, it's a 6. Thank you. So that's your final answer, 6g. Yes? From here to here or here to? Yeah, because 24 over 18 reduces to 3 over 1. So the 24 goes to a 3, the 8 goes to a 1. All right, so I just reduced it kind of. And you guys, you could multiply that all out and then reduce it if you want to, yes? When we are simplifying, the best thing to do when simplifying is always go ahead and follow your rules of exponents. OK? So the rules of exponents, first thing we talk about is parentheses. So inside these parentheses, can we simplify anything?
Yes.
Well, I can't multiply 3 times m squared any further. I can't multiply them times a. So they're actually simplified. So inside the parentheses, we're good. Then we go into exponents, or our powers. And what you guys can see is we have a 2. And that expression is being raised to the 2nd power. Notice the expression is separated by multiplication. Since it's separated by multiplication and not addition or subtraction, we can distribute. Right? OK, so let's just go and do this. Let's do one step at a time. Actually, you know what? I'm going to do 2 steps at a time. I don't like having negative exponents. And we know we don't want to deal with negative exponents. So if I have a negative in the denominator, to rewrite that as positive, I can put it in the numerator. Very good. So I have x squared times x to the positive 3rd. Then I have 3 squared, m squared squared, and then a squared. All over 18 m to the 4th a. Everybody follows me? OK, I just wanted to show you this step. Now let's go and simplify. Remember, when you multiply, you add, right? So this becomes x to the 5th times 9 times m to the 4th times a squared all over 18 m to the 4th times a. Now, you can do this a couple different ways. When you have terms in the numerator and in the denominator, and when you're multiplying, we added. So when you're dividing, you subtract, right? So in reality, this is a squared divided by a is really a to the 2 minus 1, which is just a, right? So that just leaves you with an a. However, m to the 4th divided by m to the 4th is m to the 4th minus 4, which is equal to m to the 0. Anything raised to the 0 power on your rules of exponents is equal to 1. Or you could also say these are the same thing. It's like saying 5 divided by 5, which we know divides to 1, right? So those divide to 1. 9 over 18. 18 does not divide into 18. So you have to reduce it. What number divides both into 9 and into 18? 9, and it goes in there. That reduces to 1/2. So now, the only thing I have left here is x to the 5th times a over 2. It's right there. The 1? Yeah, it's there. We don't need to write times 1, though, over 1, right? The 1 there? It's right there. Yeah, it's just there. We just don't need to write it. When you're like all these multiplying by 1s, you don't need to write them. So we just leave them out. Anybody have any questions on that? So in this example, what we're going to do is, again, it's just like simplifying. Literally, Jim, multiplying is really not that much difficult, especially when we have multiplying using these rules of exponents. So Cameron, when you're looking up here, what you guys notice, what I really want you guys to kind of get the idea of, notice that this problem has no addition or subtraction, right? All we're basically doing is multiplying this times this. So again, as I mentioned to you guys, when you're doing this, when there's no term separated by addition or subtraction, we're just going to be using our rules of exponents. So if we're going to apply the rules of exponents, let's group things that we can apply. So what I'm going to do is, without actually doing anything, I'm going to do 16 times 9, x to the 5th times x, y to the 7th times y squared, all over 3 times 64 times x squared times y. Do you guys just see how I grouped everything? There's no addition or subtraction, so I can rearrange things. The same thing. 3 times 4 times 5 is the same thing as 5 times 3 times 4, right? It doesn't matter how you arrange it when it has multiplication. So I'm just arranging this so I have the numbers, my x's, and then my y's. Now, obviously, ladies and gentlemen, you can multiply 16 times 9 and 3 times 64 and then reduce the fraction. However, that I do not like to reduce after that. We want to see, can we simplify this on the front end? And what I notice is here that 9 divided by 3, that can reduce down to 3 over 1. Then I want to see, well, 16 and 64, can I reduce that? Well, I know that 8 divides into both of those, right? 8 goes into 16 twice, and 8 goes into 64. 8 times 8 is 64. So 8 goes into 64 8 times. So I could reduce this to 2 over 8. But then I realized, well, 2 over 8 can be reduced down to 1/4. So what that tells me is 16 goes into 64 4 times. 1/4. Now it's much easier to multiply my numbers, correct? Would you guys agree with me? OK. Now there's a couple different ways you guys can do this. What I would recommend is, when multiplying, is to multiply all the way across, so then you have a rational expression that you can then simplify like we did the last example. So here I have 1 times 3, which is just 3. Then I have x to the 5th times x, which is x to the 5 plus 1. Y to the 7 plus 2, so it'd be y to the 7 plus 2. All over 1 times 4 is 4. X to the 1 plus 2, and then times y. Would everybody agree with me on that? So what I'm doing by doing that, I'm now combining the x's and the y's on the numerator and denominator. So therefore, that ends up with a rational expression of 3x to the 6th, y to the 9th, all over 4x to the 3rd over y. Now I apply the quotient rule of my rules of exponents, and I subtract the powers. So therefore, this becomes 3/4 x to the 6 minus 3, y to the 9 minus 1. And since those are both going to be positive, they're going to remain in the numerator. And my final answer is going to be 3x to the 3rd, y to the 8th, all over 4.
Welcome. What I want to do is show you how to simplify this expression. Now, I know it looks like a huge expression to you, but that's why I'm here, to help you out and kind of work through some ways for us to manage all of this mess. So the first thing I want to do is I want to remind you of a couple properties of exponents that we're going to use to hopefully try to make this a little bit easier on you. So the first thing we need to look at is negative exponents. I see that I have a negative exponent here and a negative exponent there. So we need to understand how our negative exponent is going to affect our problem. Well, the first one is, if I have x to the negative n, that is the same thing as x, or 1 over x to the n. And 1 over x to the negative n is equal to x to the n power. The other thing I notice is I have multiplication and division going on in this problem. So we should understand, how is that going to affect our problems? Well, if I had x to the a times x to the b, that's going to equal x to the a plus b. What that means is, if I'm going to multiply two numbers with the same base, and they both have exponents, to solve that, I'm just going to add the exponents. Division works very similar. X raised to a power a divided by x raised to a power b is going to equal x a minus b.
And then the last thing I noticed is I do have some parentheses in here. And so I have a variable, or I have an exponent raised to another power. So the power rule tells us if I have a variable x to the a raised to the b power, that's simply going to mean x to the a multiplied times b. So when solving this, or when we're trying to simplify this problem, we need to look at using PEMDAS first. And that means I need to get rid of these parentheses. So I'm going to use this operation first. So remember, when you have an exponent, that exponent is referred to every single one of your term inside your parentheses. So I have b raised to the negative fourth power and a squared raised to the negative fourth power. Well, remember that b can be raised to the first power. So therefore, when actually dividing or multiplying this out, I'll have b to the negative fourth, because 1 times negative 4 is negative 4. And then a to the 2 times negative 4 is negative 8, times 2a to the fourth divided by negative 2, a to the third, b to the negative third. So now, to simplify this problem, the best way that I want to explain this is I'm going to use my negative exponent rules to put them all on the same line where there's no more division symbol, because I don't like dividing, I don't like subtracting. It's much easier for me to multiply and add. So I'm going to use my negative exponent properties to put them all on the same line, and then I'll use my multiplication rule to add and subtract, and then whatever my answer is, then I'll put the exponents back where they're supposed to be. So to put these two up there, they're going to have to change signs, right? Because if they're on the bottom, to put them up top, to put them over 1, they're now going to have to change signs. Now, my negative 2, if you notice already, these two, I can't move these. These are two numbers on a division symbol. But, so to get rid of these, I can easily just, I can easily just cancel these out, because that's 2 divided by 2, which is obviously going to be negative 1. So I'll have b to the negative fourth, a to the negative eighth. 2 divided by 2 is going to equal negative 1. It doesn't matter if it's on the top and bottom, so I'm just going to display that right there. A to the negative eighth, and then I have a to the fourth. Now a to the third up top would be a to the negative third. B to the negative third up top would be b to the third. That's me using my negative exponent rule. Now what I'm simply going to do is I'm going to combine these. I notice that I'm multiplying all these together, and I'm multiplying my two b's. So remember, when you multiply, you're just going to simply add. So I have negative 1 times a to the negative 8 plus 4 plus negative 3. And then b to the negative 4 plus 3. And when you add this up, what you get is negative 1, a to the negative 7th, and b to the negative 1st. Okay? So now, since I know that these two are negative, I have to put them under 1 to make them positive. My negative 1 can remain up top. So my final answer is going to be negative 1 all over a to the positive 7th, b to the positive 1st, which you don't need to write, which you can leave like that. So that is how you simplify. It's much easier to make sure you put them all in the same line and then use adding and multiplication. But the most important thing is you understand these rules and where to apply them, as there's multiple ways to get to my exact same answer, which is negative 1 a to the 7th over b. Thank you. You're just taking one fraction and dividing it by another fraction. But remember, we don't like to write our fractions as division. We want to write them as a multiplication, right? So to rewrite this as multiplication, rather than dividing by this fraction, we're going to multiply by the reciprocal. So therefore, I'll rewrite this as c squared y divided by 2t squared times 5d divided by negative c to the 6th power. Now, what I'll simply go ahead and do is multiply across, right? Because that's how I multiply my fractions, is multiplying across. Therefore, by multiplying across, what I'll have is a 5c squared y d divided by negative 2 c to the 6th d squared. Okay, now you might say, oh, we're done, we're good. But remember, now we have it as written as a one monomial, right? That now what we need to do is use our properties of exponents to see how we can simplify. Well, 5 divided by negative 2, that's going to reduce to a fraction. Oh, I'm sorry, that is a fraction, so we'll just leave it as that. Can't simplify it. Then we have c squared minus 6, right? Because remember, when you divide, you subtract. Well, here, I can't, y is just going to remain in the numerator. And then d, remember that's d to the first power minus 2. So therefore, I have a negative 5 halves, c to the negative 4th, y, d to the negative 1st. Okay? And then last thing, guys, remember, when you have exponents raised to a negative power, they go in the numerator or the denominator. If they're in the numerator and they're negative, they go into the denominator. If they're a negative in the denominator, then they go up to the numerator. So it's just kind of a trick question. So therefore, our final answer is going to be negative 5y divided by 2, c to the 4th, d to the 1st. And notice when I put them in the numerator denominator, from being negative, they're now positive. Okay? And the negative sign can be in the numerator denominator or just in front. Doesn't really matter. Okay? There you go. You guys remember, if I said 1/4 times 3 halves, you multiply it across, right? That equaled 3/8, correct? But now, let's try to remember when we said divide. If I said, what if I said 1/4 divided by 3 halves? One way we looked at that, and kind of a simple way to remember it, was to flip it and then multiply, right? Times the reciprocal, which is 2/3. So, when multiplying fractions, you multiply straight across, right? When dividing fractions, an easy kind of simplistic way to describe it is to multiply by the reciprocal of the fraction that you're dividing by. Okay? So rather than having division, you can reciprocate it and then multiply across. Means flip your fraction to its reciprocal. Okay? So in this case, you guys can see I have a pretty odd fraction, right? It's not as easy as 1/4 and 3/8. We have a fraction that's looking a little bit different. So what I'm going to have to do is take this, find the reciprocal of it, and then multiply across. So by doing that, I have 18xy cubed over 7a squared b squared times 35a squared b over 12x squared y. Yes or no? You got it, Alex?
I have.
Okay, good. So now we can multiply across. Now, ladies and gentlemen, you can do some simplifying before if you'd like to, or we can just multiply across and kind of see where we get. So I'm not going to simplify this yet. I'm just going to do 18 times 35 times x times y cubed times a squared times b, all divided by, let's do 12 times 7 times x squared times y times a squared times b squared. Okay, so a couple reasons why I did this with there, so you guys can kind of simplify this as far as where the terms go. All right, there's a couple different ways we can simplify this. But remember, a squared divided by a squared, we know is going to divide down to 1, right? B divided by b squared, well, that's just going to leave us with b to the first power in the denominator, right? Remember the division properties of exponents? Yes? B divided by b squared is going to be b to the negative first power, which means you'll have b to the first in the denominator. Y cubed divided by y is going to leave you y squared in the numerator, right? Because y cubed minus y to the first is y to second. Remember, you subtract the exponents. This will leave you an x in the denominator, x to the first power. Then with your numbers, you guys can do this in many different ways. You can multiply 18 times 35 and divide it by 12 times 7. However, I rewrote this and I said, how can I maybe simplify some of these numbers? 35 divided by 7 is what? 5. Good. Can I reduce 18 divided by 12? We can both divide those by 3's, right? Or by 6's, right? So that can reduce down to 3 halves. right? So now I can do 3 times 5. So my final answer, 3 times 5 is 15. The x here canceled. Y squared. The a's divided out, and the b divided out. So I just have 15y squared. And then my denominator, Hazel, I have 2 times x to the first, b to the first. Which we don't need to write the ones up there.
Wow, that one was really easy. You do know this.
Does that make sense? Anybody have any questions on that? Any questions? No questions. No preguntas.
Oh, I have a question.
Yes.
Does it matter which way you put the variables in? Like
No.
x, y, and z?
Nope. Yes.
How did you have x on top and x squared on the bottom? And then, like, wouldn't that be x to the negative one?
Right. Yes, exactly. X divided by x squared equals x to the 1 minus 2, which equals x to the negative first, which equals 1 over x to the first, which equals 1 over x. That's why I have the x in the denominator. Yep, exactly. So next thing I'd like to do is show you guys how to multiply a monomial times a trinomial. And when multiplying pretty much a monomial times a trinomial, what we're just going to have to use is our distributive property. And if you guys can remember, a easy just kind of form of distributive property is when you're multiplying a number times a quantity inside parentheses. You need to make sure you multiply that term to every single term inside of the parentheses. So I obtain AB plus AC. Well, it's no different now that I have a monomial, trinomial, and with multiple terms inside of them. So I'm just going to multiply my whole term of 3x times 2x squared times 4x and times 6. So I have 3x times 2x squared. We'll say plus a 3x times a negative 4x. Remember, that's a negative. And plus 3x times 6. Well, when multiplying these, I can only multiply my numbers and multiply my exponents. And then over here, I'm going to have to remember that I'm going to have to use my product property. When I multiply bases with exponents, you have to add the exponents. So I'm going to get 6x cubed plus a negative 12. And then x times x is x squared. And then 6 times 3 is 18 plus 18x. Now I go and look at it. There's really nothing else I can combine. And so that's my finished product. So I can do a couple other things, but that's how you multiply monomial times a trinomial. Basically, all I want you guys to do is multiply 2 of them first. So you can do that by applying FOIL. Binomial times a binomial, you can apply FOIL. Or you could use the box method, which I prefer, but I'm going to do that next. So if I was just going to multiply these, forget about this one. You just multiply these 2 first. So x times x is x squared plus 3x. Negative 2 times x is negative 2x. Negative 2 times 3 is negative 6. Times x plus 4. Does everybody see what I did? Now, let's go ahead and combine these. So this becomes x squared plus x minus 6 times x plus 4. OK? So now I'm multiplying. Now what I'm being asked is to multiply a trinomial times a binomial. Now what I like to do in this, yes? 3x minus x. Now you can see these are like terms. They both have an x, so I can combine them just to x. OK? So now I'm multiplying a trinomial times a binomial. And in this case, ladies and gentlemen, we can't do FOIL like we did here. You can still do distributive property, multiply the negative 6 times both terms, multiply the x times both terms, multiply the x squared times both terms. But that sometimes gets very, very confusing. So what I like to do is to write them on the side lengths of a box. And basically what I do is I just multiply to find the area of each box. This is what I like to call the box method. X times x squared is x cubed. X times x is x squared. X times negative 6 is negative 6x. X squared times 4 is 4x squared. 4 times x is 4x. 4 times negative 6 is a negative 24. Now, again, going back to Josh's theory, is when you have terms that are like terms, you can combine them. So therefore, my final answer is x cubed plus 5x squared minus 2x minus 24. OK? So, ladies and gentlemen, this is one of my favorite techniques to be able to use. Because when you're applying distributive property, Tristan, as I kind of mentioned, when you have a number or term outside of parentheses and you need to multiply it by both terms, then it's going to look something like that, right? But it comes into an issue is once we have a binomial being multiplied by a trinomial, or even worse, a trinomial by a trinomial, this distributive property thing can get very confusing. And you start multiplying this number by everything over here, and then this term by everything over there, and it becomes a lot of multiplication. So what I prefer to do when I start multiplying binomials and trinomials and so forth is I like to create a box to represent my multiplication. And I make a box that's going to represent the trinomial up top and the binomial on the side. Does everybody see how I kind of labeled those side lengths? So therefore, now every single term kind of has its own section. Does everybody see that? OK? So now, basically, what I'm going to do is I am going to determine the area of each box. X times x squared is x cubed. X times negative 3x is negative 3x squared. X times 4 is 4x. Does everybody follow me with that? I'll get there. Then I have x squared times 1 is x squared. Negative 3x times 1 is a negative 3x. And 4 times 1, again, I'm trying to find the area of this. So this width is 4. The length is 1. So 4 times 1 is 4. And what's nice about this method is you guys can see that when you're trying to combine your like terms, as long as you have as long as you have your polynomials ordered, then your like terms combine are on the diagonal. So now, when I'm trying to find my answer, I have x cubed. I could write out negative x squared plus x squared, but I can combine. I see that these both are x squareds, so they're like terms. So that means I can combine them. So negative 3x squared plus x squared is going to be a negative 2x squared. Negative 3x plus x is just going to be a positive x. And then I have nothing to add to my 4, so it becomes a positive 4. Anybody want me to reiterate that or re-explain it in a different way? You guys want to give it a shot? OK. Welcome, ladies and gentlemen. So what I'd like to do is show you how to multiply this binomial times a trinomial. And to go ahead and do this, what I'm simply going to do is actually, rather than using the box method, I'm just going to kind of use some distributive property basic components. Because basically, when we're multiplying with an expression times another expression, we're basically using just our distributive property, meaning I need to multiply 1 times each one of these terms. Well, when multiplying 1 times each one of these terms, that's going to be pretty simple. That's just going to be the basic negative 6y squared plus 2y plus 3. Then I need to multiply 5 times every single one of those terms. And so I'm going to kind of do this. Actually, I'll add this up. So therefore, it'll be 5 plus 5y times negative 6y squared. Now, I could have done the exact same thing with 1, with doing 1 times negative 6y squared, 1 times 2y. But we all know 1 times any one of those numbers is just going to be exactly that term. However, here, when we're multiplying, I'm going to want to write these out. Now, this is all a positive 5y, so that's why I'm writing plus 5y. If it was negative, then I'd put this subtraction symbol there. Times 2y, and then plus 5y times 3. Now, I'm using parentheses to represent my multiplication, OK? So negative 2y squared plus 2y plus 3. And obviously, you could simplify this. You could probably do those in your head. But I'm writing them out to hopefully help you not make those mistakes in your head. So positive 5 times negative 6 is going to be a negative 30. Y times y squared is y cubed. Remember, we add the exponents. Plus 5 times 2 is 10. Y times y is y squared. And 5 times 3 is a positive 15y. Now I look for like terms, and I see here I have 2y squareds. So I can combine the y squareds. By combining them, I just add and subtract their coefficients, and I keep the term the same. And then I have 2y plus 5y. I have no other constants and no other y cubed. So now I'm going to write in descending order, which I'll have negative 30y cubed. Negative 6y plus 10y is going to be a positive 4y squared. Plus 17y, 2y plus 15y is 17y plus 3. And there you go, ladies and gentlemen. That is one way how to take the product of a binomial times a trinomial. Thanks.
All right. What we're going to do is we're going to evaluate each one of these expressions for the values of a equals negative 2, b equals 3, and c equals 4.2. So one thing, if you just want to remember, when we're talking about evaluating, what we have is I have 3 expressions up here. And for each one of these 3 expressions, they really don't mean too much to us, except they just kind of represent something that we don't know. This says a minus, or a number, or we're going to assume a is represented number. Pretty much just saying a minus 2b plus 3c. And that's going to, eventually equal something if you want to put an equal sign. But what we want to do is when we evaluate, we're going to want to find that we're going to give it a value. And for each one of these terms, a, b, and c, we've decided what the value we want them to be. So we want a to represent negative 2, b to now be 3, and c to equal 4.2. Now this all can change, depending on when you're doing a problem. But for these 3 problems, these are the values we want you to use. And for each one of these expressions, we want to say what is going to be the value when those variables equal those values. So that's why we say evaluate. So if I want to evaluate a minus 2 times b plus 3c, what I'm going to do is I'm going to plug in my values for a, b, and c. For a, I have negative 2 minus 2 times b, which is 3, plus 3 times c, which is 4.2. Then I just do, this is a negative 2. Negative 2 times 3 is a negative 6. 3 times 4.2 is 12.6. Now I can subtract negative 2 minus 6. Want to real quick make sure what I am doing order of operations. Notice how I did my multiplication before I did my subtraction. You don't want to subtract negative 2 minus 2 and then multiply by 3. Forgot to mention that. This is a very important step. The next thing we're working on, besides evaluating, is doing your order of operations. First, always do inside your parentheses first, which here there's no initial parentheses. And I only included a value when I put them in parentheses. Then you work on your exponents. Then you do multiply, divide, and then do addition and subtraction left to right. So now I do negative 2, since I did all my my multiplication first. Now I'm on addition and subtraction, and I'm going to work left to right. I'm not going to add a negative 6 plus 12.6 and then what I have to be add that to negative 2. I go left to right. Negative 2 minus 6 is a negative 8 plus 12.6. Therefore, my final answer is going to be 4.6. All right. For here, I need to work inside the innermost. Well, first of all, let's evaluate, or let's plug in our values. So a doesn't represent a random number anymore. A now represents negative 2 plus 3. B now represents 3. All right, so now the first thing you always want to do is make sure you always do what's inside your parentheses first. So bracket is just another type of parenthesis. So I look inside my bracket, I have another set of parentheses that I'm going to have to evaluate for. So I'll do negative 2 plus 3 times 3 squared. I'm just going to get rid of the parentheses, you don't really need that. And then I have a negative 2. Negative 2 plus 4.2 is going to be a positive 2.2. All right? Then I can do my exponent. 3 squared will give us 9. All right, then I still need to keep on doing inside this parenthesis so I don't need it anymore. So negative 2 plus 3 times 9 minus negative 2.2 is going to give me a 6.8. Then I need to do multiplication. 3 times 6.8 is going to be, 3 times 6 is going to be 18. And then 3 times 8 would be 24. So therefore I'm going to be 20.4. And then negative 2 plus 20.4 is going to give me a positive 18.4. Over here, exact same process again. 3 times negative 2 minus 2 times 4.2 all over 4 times negative 2 times b, which is times 3. All right, now here, this is a little bit more confusing with PEMDAS because there's this division symbol. And what we're going to do is, first thing, let's just evaluate our multiplication. We don't have parentheses, we don't have exponents. Next thing we're going to do is let's do our multiplication. All right, so therefore I'm going to get a negative 6 minus, that's going to be a negative, times 4.2 is going to be 8.4, all over a negative 24. Now, here's the way we can do it. You say, well, we need to divide next, right? There's a division problem. How are you going to subtract first? Well, remember, this can be broken down into negative 6 divided by negative 24 minus minus 8.4 divided by 24. So you can separate it and then do division and then subtraction. Or, since they're together, we can actually do our subtraction on top, and then we can then last divide. So negative 6 minus 8.4 is a negative 14.4 divided by a negative 24. And those are, therefore, my negatives will cancel out, and that will be my final answer. So remember, when you're evaluating, you take your values of your variables, plug them into your expression, and then make sure you just follow your rules of PEMDAS, which is first parentheses, innermost parentheses, then work on exponents, then do multiplication, division, and then addition and subtraction from left to right.
Welcome, ladies and gentlemen. So, kind of disregard my little stand here. What I have is 5x squared. I guess it's coming all right. 5x squared plus 2 plus 2x squared minus 1. And what we want to do is we want to apply the operation of the polynomials. We want to add them. Now, when we're adding, subtracting, or adding or subtracting, what we call combining, we want to make sure we can only combine that are like terms. And what we mean by like terms is mean that they have the same variable factors. So you can see here, I have x squared and I have x squared. So these two terms I can combine. But here, 2 and negative 1, those are just values, those are just numbers, so we can go and combine those. So when I'm adding, all I simply do is, what I like to do is just rewrite these. We don't really need the parentheses, but just rewrite it as 5x squared plus 2x plus 2, and then minus 1. Now I can combine my x squareds and my constants. So 5x squared plus 2x squared, again, just kind of think of it as like 5 apples plus 2 apples, right? The x squared is just your variable, but what you're adding is the coefficient, which is 5 and 2, which gives you 7x squared plus, and then 2 minus 1 is just going to be a positive 1. So there you go, ladies and gentlemen. That is how you add polynomials. Thanks. What we're basically doing is we're adding one polynomial to the other polynomial. The most important thing, as I mentioned, which like what I last talked about, you can only add monomials that have the same variable factors. If they have x squared, then the other one has to have x squared. If you have x cubed, the other one has to have x cubed. So I always like applying what we call the vertical method. And the vertical method is basically, if I was going to say, what is 5 plus 3, you could write that as, oops. Do you guys remember that from like 2nd grade, right? You can write them vertically. You guys remember that? Adding, and then you do 5 plus 3 equals 8. So we can apply the same thing. So what we're going to do is basically create a vertical addition problem, where we're going to take one polynomial, and we're going to write it above the other polynomial. Now, what this also allows you to do is an opportunity to rewrite each polynomial, in descending order, which we practiced last class period. So this one I have 3x cubed. Now, also notice that there's no x squared, right? No x squared, correct? So I can give that a place value. I'll use a red. Minus 2x plus 5. You don't have to do the place value, but I'm going to show you why it's at least helpful to see what that would be. Then we write this one. Now, this one's not in descending order. So I don't have an x cubed, so I can write x squared minus 2x plus 3. But if I wanted to have one, 0x cubed. Okay? So you don't have to write the place value, but I just want you guys to see that when you now add these vertically, 3x cubed plus 0x cubed, you're basically really just bringing that down. So my final answer is now when I add them vertically, because notice, you guys see how these are all like terms, right? So if you align them in descending order, now you can just add them vertically. So my final answer is 3x cubed plus x squared minus 4x plus 8. Everybody see that? Yes? Good? Questions? Clarification? Welcome, ladies and gentlemen. So what I'd like to do is show you how to subtract these two polynomials. And there's a couple different ways to do polynomials. But one thing that I always like to do is nobody really likes subtraction, right? We all like addition. Addition is the first thing we learned when it comes as far as operations of numbers. And I think it's kind of the easiest and less likely to make a mistake. So one thing that we talked about, especially when we get into negative numbers, is rewriting an expression as an addition problem. So for instance, if I had 4 minus 5, what we can do is we can rewrite that as an addition problem as saying 4 plus negative 5, right? OK. And what I'm basically doing is I am taking this as, adding it to the negative value of my number. Now, the same thing works when we have distributive property. If I have a plus b, and it's times negative, well, that negative can be distributed to all of those terms. So now it's a negative a minus b, or negative a plus a negative b. OK? So the important thing that I'm trying to get at with you is when we apply this distributive property, what I'm doing is now I'm sending in all what the negative values are. Just like here, instead of saying 4 minus 5, I'm saying 4 plus the negative, or the opposite of 5. So what I'm going to do is I am going to distribute my negative sign. And by distributing my negative sign, I am just going to now turn this into an addition problem. So it's going to say x to the 4th minus x cubed plus x squared minus x plus 1 plus, and the reason why I write plus is because now I'm determining the opposite sign for each one, just like I go from here to there. So now that is negative x minus, wrong one, minus x to the 4th, positive 1, and positive x squared. OK? Now, again, obviously, we know that plus a negative x, a lot of times we just write that as subtraction, right? I understand. But I'm going to leave it like this because one thing we do is now when we're going to combine these, or when I'm combining my terms, I want to make sure that I'm combining them with my like terms. So now I need to find common terms that have the same variable factors. And the terms are the same. You can see these all have x's, but they're all x's to different powers. Well, if they have the same if they have the same powers, and they have the same variable factors, meaning the highest factor for x to the 4th is x to the 4th. Well, I can't divide x to the 4th evenly into x cubed. So therefore, I can only combine x to the 4th with x to the 4th. X to the cube here, you can see, does not have anything, right? So we know that's going to be in our part of our answer. X squared, that's going to combine with x squared. The x's combine with the x. And then 1, I do have another constant here, is another positive 1. So now let's just go through it. Let's start with x to the 4th. Well, x to the 4th minus x to the 4th. Well, that's become 0x to the 4th. So therefore, let's write it out. So my 0, I don't know, that might be easy. So x to the 4th is x to the 4th minus x to the 4th, which is equal to 0x to the 4th, which guess what? Just goes to 0. Then let's do x cubed. So that's a negative x cubed. Well, guess what? That just goes to our answer, because there's no other x cubes to combine it to. X squared, I have x squared plus x squared, which equals 2x squared. That's going to go into our answer. Then we have negative x, a negative x plus another negative x, which equals a negative 2x. Goes to our answer. And then we have a 1 plus 1 is equal to 2, which goes to our answer. Therefore, all the arrows that I have answers for are negative x cubed plus 2x squared minus 2x plus 2. So there you go, ladies and gentlemen. That is how you go ahead and subtract two polynomials. Thanks. Now, ladies and gentlemen, when we're looking into factoring the expression, again, our basic premise that we're trying to do is trying to rewrite this expression as a product. So exactly what I asked Brianna. I said, Brianna, can you factor 8? Can you rewrite 8 as a product? And you say, yeah, I can rewrite 8 as a product. 4 times 2. Basically what you do is you take a number that divides into 8, which is 4, divide 8 by 4, and then you multiply what you divided by what the answer was when you divided it. So you take 8, take a number that divides into 8, which was 4. You divide 8 into 4, you get 2. You take the number that you divided by, which was 4, and multiply it by what the answer was, which was 2. 4 times 2 is 8. Now I've taken the number 8, and I've rewritten it as a product. So now we don't have numbers. We have expressions. So what we need to do is determine what is a number or a term or a variable that divides into both of these terms. And when I'm looking at this, I can say, ask Chris Spencer, I say, what is something that divides into both of them, Chris? 5. That is what we call our greatest common factor. You can both divide in a 5. Is there any other larger number or variable that divides into both of those terms? No. So just like I said here, I said a factor was 4. I now divide by 4, rewrite what my factor or my divisor was here. So I say 5 times. Now once I take 8 divided by 4, I got 2. Well, what happens when I divide 5x plus 35 divided by 5? 5x divided by 5 gives me x. 35 divided by 5 gives me. Have I now rewritten the expression 5x plus 35 as a product? If I multiplied this back, 5 times x is 5x. 5 times 7 is 35. So is the answer the same? It's just rewritten as a product, as multiplication. Is 4 times 2 the same as 8? Yes, but 4 times 2 is written as multiplication. That's why we do factoring. We want to rewrite the expression as a product, as multiplication. Does that make sense? Yeah. OK. Welcome, ladies and gentlemen. So what I'd like to do is show you how to factor a binomial, or sorry, not binomial, but a polynomial using the difference of two squares. Now, using the difference of two squares is a binomial, but I really wanted to focus on the difference of two squares and polynomials. So when we look at the difference of two squares, the main tenet of difference of two squares is a squared term subtracted from another squared term. And when we were dealing with quadratics and factoring and solving using difference of two squares, it was fairly basic. Your terms a and b were either numbers or they were numbers with a variable or a variable. So it was pretty simplistic. And the powers were always 2. So it wasn't that bad. And if you remember, a squared minus b squared was simply a factor form of a minus b times a plus b. Now, what's nice about polynomials is that pattern of difference of two squares remains the same. However, when we're dealing with polynomials in this course, we're going to deal with terms of a that are a little bit more complicated. And we're not going to just deal with exponents that are 2. So what we're going to want to do when we do this is identify what a is and identify the values of b. And there's a little way that we can do that. So let's kind of look at an example. And I'll just make one up. Let's do 4x squared minus 9x to the 6th power. Okay? If I wanted to solve this by difference of two squares, basically what I need to do is I need to take this into two terms that are squared. So what I need to do is I need to rewrite this as a term that is squared. So to do that, what I'm going to do is I'm going to take the square root of both of these terms. Now the square root of 4x squared, you're going to do these separately. Square root of 4 is 2. The square root of x squared is just x. And then minus the square root of 9 is 3. And the square root of x to the 6 means what term multiplied by itself gives us x to the 6th? That's going to be x cubed. Again, x cubed times x cubed equals x to the 3 plus 3, which equals x to the 6th. OK? So I have this term minus this term. Now these are both squared. Now let's again verify that we know that these are square terms. Remember, when you're squaring a term, The squaring distributes to both of our terms. As long as they're separated by multiplication, they distribute. 2 squared is 4. X squared is x squared. 3 squared is 9. And x to the third to the sixth. There we go. So now we know our a and our b. So our a is 2x, and our b is 3x cubed. Now what I know at my a and b, I can simply just plug them into my formula. So that's going to be 2x minus 3x squared times 2x plus 3x squared. And there you go, ladies and gentlemen. That is how you apply the difference of two squares. Thanks.
So if I wanted to factor this trinomial here, right? The first step, always, either when looking at factoring, simplifying, solving, anytime, see what we can factor out. All right? So you always want to look at that. That's always like the first step. See how we can simplify the problem before you start doing anything. Well, I look at each one of these terms, all right, and I notice they're all divisible by 5, meaning 5 divides into all of them. So what I can do is I can divide out a 5, or we say factor out a 5. I also notice that they all have a b term. So therefore, I can also divide out a b. So when I factor out, divide out, factor out a 5b, what I'm left with is a b squared minus 6b plus 9. All right, and the way just to check to make sure you factored it out correctly is just kind of go back and do your distributive property and make sure that 5b times b squared is 5b cubed, 5b times negative 6b is negative 30b squared, and 5b times 9 is 45b. Okay, we good with that? Then here I have a trinomial. Well, the way I always like to do my trinomials is, remember, it's in the form of ax squared plus bx plus c. It's a quadratic. So you just do a times c. Since my a is a 1, don't worry about this variable. The variable is a b, I know, but we represent it as an x in my quadratic form. But a is 1 times 9, so this is really a times c, which is 1 times 9, which is a 9. And then my b for my quadratic, all right, I know my variable in this problem is b, but we usually use x, okay? But my b in this one is a negative 6. So I just ask myself the very questions. What two numbers multiply to give me 9, but then add to give me a negative 6? And you can say that would be a negative 3 and a negative 3. So I can say b minus 3 times b minus 3. So to factor out this problem, that would be factored out. Yes?
Can you also do b minus 3 squared?
And then to simplify it, yes, you could go ahead and write this out as b minus 3, squared, 2. But since we've been dealing so much in pre-calc with as far as like linear factors, but I mean, yeah, it doesn't matter. You'll notice that this also has a multiplicity of 2, or multiplicity.
Okay, so ladies and gentlemen, when we look at a problem like this, what we want to do, Biori, is try to see. Remember we talked about when we had two terms, and I said factor it. We always look for difference of two squares, difference of two cubes, or the sum of two cubes, right? When you have two terms and I ask you to factor it, that's what we immediately would think for. You always want to look for GCF first. And then, if there was a trinomial, we always look to factor in our GCF, but then we had to use our factoring techniques for how to factor trinomial. Well, ladies and gentlemen, when you have 4 or more terms, you always still look for the GCF. But then after the GCF, we want to look into grouping, all right? And the grouping form tells us to simply group. Well, first of all, let's look for GCF. Is there a term that all of these share? No. Okay. So we group the first two and the last two terms. Now we look into our first two terms. Is there terms that they share? No. Is there terms here that they share? Okay. So, well, let's think about it. Is 3 plus 4 equal to 4 plus 3?
No. 3 plus 4, so here we got 4 plus 3.
So what I'm going to do is I'm going to make sure I keep the correct signs, and I'm going to rearrange my middle terms. XR minus XS minus YS plus YR. All I simply did was rearrange my middle two terms, all right? And I kept the same signs. Now let's go through this again. by grouping my first two terms and my last two terms. Now do I have common terms in the first two? Yeah, I have an x.
No, because one's lowercase and one's uppercase.
Shut
There-
Oh my god.
No, it is on the problem. One's lowercase and one's uppercase. That has No.
That's not supposed to be. It's not supposed to be differentiated. This one's going to be x times r minus s. And then over here, I would have to go and take a look at this and say, what else can I factor out of here? If you factor out just a 1, a positive y, then you're left with a negative s plus r. Now, is r minus s the exact same as negative s plus r? Yeah, of course they are. So you can factor them out. And let's just factor out it in the form of r minus s, and you're left with x plus y. So that would be your factored form by grouping. Okay, good job. Welcome, ladies and gentlemen. So what we're going to talk about today is how exactly do we factor by the GCF. And factoring by the GCF, I think, is one of the most important things for us to understand. First of all, why are we factoring by the GCF, and how really does factoring work? Now, again, to really understand, you have to understand what exactly is factoring. Factoring, again, is rewriting an expression as the product of two other expressions. And to really kind of think about that, I always like to look at the number. Let's say I wanted to factor the number 8. And if I want to factor the number 8, that means I want to rewrite it as a product. So to do that, I have to find something that divides into 8. And let's pick the number 4. So if I pick 4 to divide into 8, that answer of 8 divided by 4 is equal to 2, right? So now, if I want to still rewrite my number 8 as a product, I can say that 4 times 2 is equal to 8, right? So basically what I did is I took a factor, which was 4, and I multiplied it by the quotient of 8 divided by 4, which was 2, and that gave me an expression that was the same as my number 8. Okay, so I rewrote the number 8 as a product. So we're going to do the same thing here, but now we're not dealing with numbers, we're dealing with expressions. So I need to determine a number or a variable that divides into both of my terms. And what we call that term is our GCF. And the GCF represents greatest common factor between both of these. Now you can see that the greatest common factor of this binomial here is just 3. So what I'm going to do is I'm going to divide by 3, just like I did with the number 8. Then, since I'm dividing by 3, I'm going to rewrite that as the product times its quotient. Well, the quotient of this divided by 3 is not just going to be a single number like it was 2. It's going to be an expression. 3x divided by 3, those go to 1. It's just going to be x. 3 divided by 3 is positive 1. Now I have factored out the GCF. See, the GCF is 3. I have divided it out. And we can always check our answer by applying the distributive property. For here, you can determine that the GCF is not a number, but now the GCF is going to be a variable, which is x. So I'm going to divide by x on both of them. And again, once I take my variable x, I factor it on the outside, and then I multiply by our quotient. So I divide it, and then multiply my divisor by the quotient. Divisor by quotient. X squared divided by x here, using the properties of exponents, I'm just left with x. X divided by x is positive 1. Again, check my answer. X squared plus x. Now lastly, this is not limited to just binomials. We could also divide trinomials or polynomials with 4, 5, 6 terms. So in this one, it gets a little bit more confusing because we want to again identify what is the largest number and variable that divides evenly into all 3 of these terms. All 3 of these are separate terms, separate monomials that we need to divide into. So in our case, the GCF, if you're looking for the largest number that divides into all of them, you want to kind of look at the smallest of terms. Well, the smallest number here is 7. Does 7 divide into 7, 14, and 21? Yes, and that is the largest number that's going to do that. Then we look at the variables. Well, the smallest variable is x squared. Does x squared divide into x cubed, x fourth? Yes, it does. So I divide every single term by 7x squared, because that is the largest term that can evenly divide into each term. Here I have 7 divided by 7, which is just 1. X to the fourth divided by x squared. Remember, you subtract the exponent, so that's just x squared. Here I have negative 14 divided by 2, which is a negative 2. X cubed minus x squared is x 3 minus 2, which is just x to the first power. And here I have 21 divided by 7, which is a positive 3. And then the x squareds divide out to 1. So I'm just left with x squared minus 2x plus 3. So there you go, ladies and gentlemen. That is how you factor out the GCF from a polynomial. Thanks. Welcome, ladies and gentlemen. What I'd like to do is show you how to factor this polynomial by grouping. And when we're looking into factoring by grouping, we always see whenever, basically I tell students, whenever I see 4 terms, think of factoring by grouping, right? Because we have a method pretty much for 3 terms and 2 terms, but for 4 terms, we only have one method, which is grouping. So to do grouping, all I'm simply going to do is group the first 2 terms and group the last 2 terms. Now, when doing this, I'm going to now look at each group and factor out the GCF. If I don't have a GCF, then what I'll do is I'll I can switch around these 2. Now, in this one, you can see I switch around the middle terms and then try to see if you have a GCF. Here, I do have a GCF, which would be y squared. So let's at least go and attempt this and see if this works. So if I factor out a y squared, that's basically like dividing a y squared from both these terms. Therefore, then I'm left with 2y minus 3. Okay? Then I look at, actually, let's write this here. Let's use the red again. Then I look at these 2 terms and I say, all right, what is the common factor between 18y and negative 27? Well, again, we look at the numbers. They don't both share a y like these 2 terms did. But the coefficient and the constant do have a common factor of 9. So I can factor out a positive 9. And when factoring out a positive 9, I'm left with 2y minus 3. Now, it's very important when you're doing factoring by grouping, the idea of it is when you factor out the GCF, that now inside the parentheses is the exact same expression. So if you don't have that, it's either you did something wrong, the problem is not factorable, or you need to rewrite those middle terms and then go ahead and try it again. But in this case, I factored out my GCFs, and I obtained the same expression inside the parentheses. Now, since this is exactly the same, this is common between these 2 expressions that are separated by the addition sign. So therefore, since it's common to both of them, I can factor it out. So therefore, I factor this out, which would leave me with 2y minus 3. And left over, I have y squared plus 9. So there you go, ladies and gentlemen. That is how you factor by grouping. Thanks. Welcome. What I want to do today is show you how to factor an expression by grouping. Now, grouping comes about as a way to factor an expression when we're going to have 4 different terms. Because when we usually ask to factor something out, the first thing we always want to do is factor out the GCF. Well, when I look at these 4 terms, they don't share anything in common that I can commonly factor out. However, if I group them into smaller parts, I will be able to factor out GCFs. And that becomes kind of the really important part because a lot of us get practice with factoring trinomials, and we notice that we can't factor this into that sort by using that type of method. But to factor by grouping, what we're going to want to do is group our first 2 terms and group our last 2 terms. Now, a lot of times it's going to depend on how the terms are arranged, and what we're going to do is as I work through this, I'll show you what to look out for and what to look out for and what kind of traps we have ahead. So when I want to group this, like I said, I can't factor anything out totally. So what I'm going to do is I'm going to group the first 2 terms and the last 2 terms. And the reason why I'm going to do this is because now what I can do is if I just focus on factoring out a GCF out of here, I can find something that these 2 terms share. And then I can also find a term that these 2 share. So it's important that when you group them, that your 2 terms have something you can pull out. If not, you might have to rearrange them, or your problem won't be factorable. So first thing I look up here and I say, what can I factor out? Well, I know that both of these terms share a 3x. So when I factor out a 3x, I'm left with the y minus 8x. Now, it's important for you to understand that whatever your answer is here, but after you factor it out, you're going to want to get the exact same thing when you factor your GCF here. So that's the important part to look for. If you're not getting the same answer, you might want to check what are you factoring out as your GCF, or should you maybe rearrange your terms and see if you might be able to get that same answer. So since I have a y here, I'm going to want to factor out not just a 7, but a negative 7. So therefore, I'll still get a y inside.
So when I factor out a negative 7 from a negative 7y, I'm left with a y minus 8x. Now what you can do is see that these two terms are now exactly the same. So what I can do is, just like we factored out GCFs before, I can take these as the GCF of my expression. So now what I'm going to do is I'm going to factor these out of the expression. So when I factor these out, since both of these terms share a y minus negative 8x, I can factor them out, and I'm left with a 3x minus 7. And therefore, now I have just successfully factored by grouping. There you go.
So if I was going to ask you guys to do this, x minus 3, do you guys see how this could be a possibility of a cube number minus another cube number? Yes? So we just got to determine, is x cubed a cube number? Yes. Is 64 a cube number? Do I have those cube numbers written up there still? Yes, I do. Right? So therefore, what we want to figure out is if we want to know, all right, what is a cubed then equal to, and what is b cubed equal to? Well, a cubed is equal to x cubed. B cubed is equal to 64. It's the difference of the cubes, right? So we don't need to include the negative symbol. So I want to figure out what a is. So if I have a cubed, to solve for a, I have to take the what? Cubed root. So what cube root is saying, what number multiplied by itself 3 times? What number multiplied by itself 3 times gives you x cubed? X. So a is equal to x. Then you say, what number multiplied by itself 3 times gives you 64? And guys, if you're having trouble with this, just work your way up the ladder. Let's try 2. 2 times 2 times 2. Does that give you 64? No, it gives you 8, right? Then do 3 times 3 times 3. Does that give you 64? No, it gives you 27. OK, let's do 4. 4 times 4 times 4. Does that give you 64? Yes. So you can say, in this case, b is equal to 4. Now, to solve my problem, all I do is replace a with x and b with 4. And that's it. That's all I'm going to ask you guys to do for half of your homework problems. So therefore, you're going to have x minus 4 is equal to x squared plus x times 4 plus 4 squared. Then just go ahead and simplify. So this is x minus 4. What the heck? It's just a product. Times x squared plus 4x plus 16. And that's all I'd want you guys to do right now, is just to factor using the difference of 2 squares. OK? So ladies and gentlemen, we learned how to factor trinomials over here, right? You can use the diamond and so forth, right? However, when you have 4 terms, we can't use that same method. So what we can use, though, is the grouping technique. And again, what the grouping technique you do is you just group the first 2 terms and the last 2 terms. Then by grouping them, Colin, now what you do is factor out the GCF, the greatest common factor of each grouping. So 21x cubed and 14x squared, what do those have in common? 7x squared. So you factor out a 7x squared. So therefore, I'm going to do this in green. What's left over is a 3x plus 2. Would everybody agree with me?
Yes.
OK. Now let's look at these two. What do these two have in common? What can I factor out of them?
5.
You could do a 5. And let's do a negative 5, because I want it to look like this.
Oh.
So if I factor out a negative 5, what I'm left over with is 3x plus 2. Negative 5x divided by negative 5 would be positive 3x, right? So do you guys see how now in my parentheses is exactly the same? So I can factor. So out of this expression and this expression, what do these two share? The 3x plus 2. So you factor out the 3x plus 2, and what are you left over with? 7x squared minus 5. Done. That's called factoring by grouping.
All right, here comes another factoring blitz. So what we're going to do is we're just going to factor 2 of these problems. And first thing I look at, ladies and gentlemen, when you have 4 terms, whenever you see 4 terms, I always automatically look and see if I can factor by grouping. Because you can't factor using trinomial method, and you always, if I look, there's nothing all four of these terms share. So if I group these, all right, let's actually take the sign with it. Then I can group that, if we group them, then let's just go and see if we can factor these out individually. So x squared and 5x squared, I can factor out an x squared. I'll be left with an x plus 5. Remember to check your answer, you can just multiply that x back through. X squared times x is x cubed. X squared times 5 is 5x squared. Out of here, I can factor out a 3. I can't factor out an x because the 15 doesn't have an x. So I can factor out a positive 3. I'm left with x plus 5. Now, I notice that these two terms are exactly the same. How can I factor this out? Imagine those two terms are p's. What do these two terms share? They both share a p. You can factor out a p. Correct? So if they both share the same thing, you can factor it out. Well, they don't share a p. They share a x plus 5. So that's what I need to factor out, is an x plus 5. And what I'm left over with is x squared and 3. Therefore, that's been factored down. I can't factor either one of those trinomials anymore. Over here, I split them up. Now, if these were interchanged, you'd want to make sure you'd have to get your a's together and your b's together, because that would automatically signal, hey, you're going to want to group these. So by grouping your a's and your b's together, that would be something that would be really helpful. And so here I can factor out an a, because I want to group them so I can factor the same thing out. When I factor out an a, I'm left with x plus 1. Here I can factor out a negative 7b. When I factor out a negative 7b, I'm left with an x plus 1. So therefore now I'm left with x plus 1 I factor out, and I'm left with a minus 7b. Factoring blitz, grouping.
When looking at this, if x squared minus 3x is a factor of x to the fourth plus x cubed minus 5x squared minus 3x plus 6, then we know that x squared minus 3 times something is equal to that. Right? That is our general understanding of a factor. If something is a factor of something else, then we can multiply that factor times something else, and we're going to get our that expression. Right? We could also look at it. We could also say then, well, we could also write x to the fourth plus x cubed minus 5x squared minus 3x plus 6 divided by, right? If something is a factor, that means you can divide by it, right? If 4 is a factor of 12, you can take 12 divided by 4, right? So here we have division. Well, we just talked about how can we use division here. How can we use division with polynomials? And again, the first one we're going to want to step up is long division. Now, the reason why I'm using long division and not trying to go with my shortcutted version, synthetic, is because if you guys remember on your notes, I can only use synthetic division for when I have a linear factor or when I'm working with my zeros. If you guys look at this, if you're going to find the zeros here, you're going to have 2 zeros, correct? Yep. So you'd have to actually do synthetic division twice, which I'll do my next example. But you just can't do synthetic division once and then get the full answer that we're going to look for. Did I miss one? I did. Minus 5x squared. OK. 5x squared minus 3x plus 6. All right, so let's go through this problem. Again, guys, if you need help understanding this, when you guys are doing division, you're only going to use the first term of your divisor. So my recommendation is that you make sure you have your divisor written in standard form, because you want to have the leading term, the term with the highest power, first. So you're only going to divide the x squared. We're only going to use this as our division into this dividend. So how many times is x squared divided into x to the fourth? A little confused by that? Just write it to the side. How many times does x squared divide into x to the fourth? X squared times. So we put that up top. That is the first term in our quotient. Now, we have to make sure we multiply this times both terms. X squared times x squared is x to the fourth. X squared times negative 3x is a negative 3x squared. I don't want to put the x squared under the x cubed because they're not like terms, right? You don't want to put like terms with like terms. But I don't have an x cubed here, right? So if you want to, you don't have to, but if you want to, you can use place values. OK? The main important thing, though, I want to drill down, guys, is you have to subtract the two rows, and you're going to want to use parentheses. OK? And you can always check to make sure you did your division correctly, is because once you divide and then multiply, you should get the exact same term. X squared, x to the fourth minus x to the fourth should give you 0x to the fourth, which is just 0. Right? You should get that every single time. Now, x cubed minus 0x cubed, you really just subtracting as x cubed. Here's the trick. Usually most students that get these wrong, guess where they make their mistakes? Adding and subtracting. Seriously, that's where mistakes are made, adding and subtracting. That's why I think using parentheses is so important. Negative 5x squared minus a negative 3x squared. You're minusing a negative, which is the same thing as adding a positive. So therefore, that turns into a positive. So it's negative 5x. That's a minus 2x squared. Negative 3x minus 0x is just going to be a negative 3x. 6 minus 0 is a positive 6. OK, so that was like one round. Now we do it again. How many times does x squared divide into x? Oops. How many times does x squared divide into x cubed? X times. So then you have to multiply again. X times x squared is x cubed. X times negative 3 is a negative 3x. OK? Now you go ahead and, again, subtract the rows. And this time, I'm not going to use place values. OK? I'm just going to subtract them. Or I'm just going to really bring them down. Because you guys can see, if you use the place values or don't, you're really just bringing down those terms. Right? So that's why a lot of times we'll just say, hey, bring them down. But anyways, this goes to x cubed minus x cubed is 0x cubed. A lot of times, guys, we just don't even write it in there. Bring down the negative 2x squared. Negative 3x minus a negative 3x. That's really negative 3x plus 3x, which is going to be a 0x, which is non-existent, and then plus 6. OK, last time. X squared divides into negative 2x squared. How many times does x squared divide into a negative 2x squared? Negative 2 times. And then we'll just do this, negative 2x squared minus 6. Subtract your rows, 0 and 0. And again, we get a remainder of 0. So now that's important, guys, because if we didn't get a remainder of 0, then this wouldn't be a factor, correct? Right? If you have, like, we don't say, like, 4 is not a factor of 13. 4 doesn't evenly divide into 13. There's a remainder of 1 there, right? So if we do all this work and we get a remainder, well, we have an issue here because it says x squared minus 3 is a factor. So it has to have a remainder of 0. So we made a mistake somewhere. But in this case, we got 0, so we know we're good. So again, now we need to understand what this means. Again, guys, this means x squared minus 3 times this equals that, right? So now I can rewrite this in there. I can say this is x squared plus x minus 2. X squared minus or plus x minus 2. All right? So what I've done is I've taken a polynomial, and I've rewritten it in a factored form, right? We just rewrote it as a product of two factors. Now, there's something important that's going on with these two factors. Are these two factors linear? No. So what we want to do, if we're asked to find the linear factorization or to find the zeros, we'd want to continually factor them down. So how do we find the zeros of x squared? Oh, let's move it over here. So basically, guys, we have f of x equals x squared minus 3 times x squared plus x minus 2. Right? This is just the factored form of that. So long division allowed us now to break it down into our factors. Can I now find the factors here? Right? And this is what we did last time, guys. What happens when you have x squared minus 3? Like, you can just use the zero product property if you want to. X squared minus 3 is equal to 0. X equals plus or minus square root of 3. Here, x squared plus x minus 2 is equal to 0. Can we factor this further? X plus 2 times x minus 1 equals 0. X equals negative 2. And x equals 1. So now I just found all the zeros. But what if I wanted to actually write this as a linear factorization? What that means is I need to be able to factor this down further, which would be x minus square root of 3 times x plus the square root of 3 times x plus 2 times x minus 1. Is everybody OK with me going from my zeros to my factors? That was something we practiced last class period. But now we found all the zeros, just given one factor. Welcome. What I want to do today is show you how to take a trinomial, 3b cubed plus 3b squared plus 45b, and divide it by a monomial, 9b. So when I'm taking a trinomial and divide it by a monomial, all I simply really need to do is divide all three of my terms divided by 9b. So what I'm going to do is I'm just going to rewrite this as 3b cubed plus 3b squared plus 45b. And if I was going to write this as divided by 9b, what that really means is I'm dividing each one of these terms by 9b. Okay? So to divide all of these by 9b, I'm just going to divide individually all these by 9b. Then I look at this and I say, all right, now what I need to do is, for my numbers, I have 3 divided by 9. And a lot of students look at this and say, well, how do you divide 3 into 9? Well, you can't, right? It doesn't go in there evenly. But what we can do is we can reduce it. So if I look at this, I have 3 divided by 9. That's going to leave me with just a 3 on the bottom. And then b squared, or b cubed, divided by b. If you remember our rules of exponents say, if I have the same base and my exponents, then I subtract my exponents. So b cubed divided by b to the first power is going to give me a b squared. And then remember, there's a 3 on the bottom. Since I can divide a 3 on the top and the bottom, 3 divided by 3 is 1. And 3 divided by 9, which is going to be 3. Plus, I can reduce this again to have a 3 on the bottom. But now I have b squared divided by b to the first is just going to leave me with b to the first power. And then plus, I have 45b divided by 9b is just going to leave me with 5. As 45 divided by 9 is 5, and b divided by b is going to leave me b to the 0, which equals 1. And there you go. That's how you divide a monomial into a trinomial. Thanks. So when doing long division, the main important thing that we want to make sure that we have is, first of all, that we have our dividend. If you guys remember what we're dividing into, dividend. And your divisor need to be in descending order, meaning the highest power needs to be first, going down. Highest power first, going down. Does everybody agree that these are in descending order? That's the most important thing we have going on. OK. Now we take our leading term of our divisor, and that's what we're going to divide into each one of our 3 terms. So the first one says x divides into x squared. How many times can I divide x into x squared? X times. Think about it this way. It's kind of the same thing, guys, where it's like doing factoring again. X squared minus 10x plus 24. If I say x is the side length, x times what gives you x squared? X. X divides into x squared how many times? X times. Does that make sense?
It's today?
Tuesday, 23rd. Does that make sense? Does this make sense? X times x gives you x squared. So when I say how many times does x divide into x squared, it divides into their x times, because x times x gives you x squared. So x times what gives you negative 10x? X divides into negative 10x how many times? Negative 10 times. Why? Because, ladies and gentlemen, x times negative 10 gives you negative 10x. What am I doing? I'm sorry. You're only doing one at a time. So we do x into x squared equals x times. Now what we do is we take this x and we multiply it times both terms. X times x is x squared. X times negative 4 is a negative 4x. So again, I'll just revisit what I did. You take your first term, divide it into your leading term. You get that answer. X times x is x squared. Now remember, guys, we already know the answer. We already know the answer is going to be x minus 6. So you guys should have known the answer is already going to be x. That's the only thing that makes sense. Now we subtract the rows. X squared minus x squared is 0x squared, which is just 0. Negative 10x minus a negative 4x. Minus a negative is like a double negative. So therefore, that becomes a negative 6x. Now we say x divides into negative 6. How many times does x divide into negative 6? Negative 6 times. So now we take negative 6 times x, and that gives us negative 6x. Negative 6 times negative 4 gives us a positive 24. Now I can subtract the rows. Again, what I have is negative 6 minus a negative 6. That's, again, a double negative. Gives us to 0, right? And then I don't have anything to subtract the 24 from, so I bring down this number, and I have 24 minus 24, which is, again, is a 0. So I have no remainders. And what that means is x minus 4 evenly divides into this polynomial x minus 6 times. OK? What we're going to do is we're going to work on using division of two polynomials. So for division of two polynomials, what we're going to do is we're going to set it up just like any other long division problems. If you guys can remember when we were doing long division, let's see if I have room over here. 7 goes into what? 124. 7. So you can say 7 goes into 14. Goes in one time, and then I multiply the 1 times 7 to get it goes in there twice, doesn't it? 2 times 7 is 14, and then I subtract these two rows to get me 0. 7 doesn't go into 0, so I bring down the next number, which is a 7. 7 goes in 7 one time, right? Yeah. This is actually a problem I actually just double checked. I was showing a student. I was like, oh, I need to divide this. Well, let me just double check my answer. I did in my head, but you can always use long division. The whole process still works. So the first thing, we're going to set our divisor and dividend in the exact same way. So I'm going to say x plus 2 divided by x to the 4th plus 5x cubed plus 6x squared minus x minus 2. So we got all this stuff we need to divide in, right? It's a lot of stuff. Well, remember, if you look at this, we have a binomial, right? Well, this number 2, this doesn't divide into any of these x values, does it? 2 can't go into x to the 4th, right? You can't divide out an x to the 4th, it doesn't go into it. It really only goes into the constant. So what we're going to work on, though, is so we're going to see what we can divide our x value into each one of these terms, and then see what we're going to get. So I say x goes into x to the 4th. We say it's going to go in x cubed times. And what do I mean it goes into x cubed times? Well, if I do x times x cubed, I'm going to get back x to the 4th. So I do x cubed times x, and I get x to the 4th. All right, so you want to see what you can divide back in there. It goes x cubed times. Now you got to make sure that when you multiply the x cubed times x, and also the x cubed times 2. So x cubed times 2 is going to give me 2x cubed. Now, here's where a lot of people forget. Remember, we're subtracting our top row from our second row. You got to make sure you subtract everything. So I'm going to put a nice little negative sign out here. It does not mean just a negative x to the 4th. It also means subtract 2x cubed. So I draw my line. X to the 4th minus x to the 4th is obviously 0x to the 4th, right? And 0x to the 4th is just 0. 5x cubed minus 2x cubed is going to give you 3x cubed. All right? So then we can say x goes into 3x cubed, 3x squared times. Then I multiply 3x squared times x. That's going to give me 3x cubed. 3x squared times 2 gives me 6x.
Bring down 6x.
Yes. Yeah. You bring 3x is going to give you down 6x.
writing down this 6x squared, we can say minus x minus 2. All right, so now I'm going to subtract again these two rows. So I say 3x cubed minus 3x cubed is 0. And 6x squared minus 6x squared is going to be 0, right? So then I bring down a negative x minus 2. So x goes into negative x, negative 1 times. Negative 1 times x is a negative x. Negative 1 times 2 is a negative 2. Again, we're going to subtract these two rows. Let me put this negative sign back out here. So just be very careful, guys, when you're doing this, because this is where the double negatives, where a lot of students make the mistake. A negative x minus a negative x, these two negatives cancel out to make it a positive, right? So this is end up going to give us a 0. Negative 2 minus a negative 2 is just like negative 2 plus 2, which also gives us a 0. So therefore, we do not have a remainder, and our final quotient is going to be x cubed plus 3x squared minus 1 is our final answer.
Is there a problem where there's a remainder?
Yes, we'll go over one of those. Absolutely. But for this one, whenever you get 0 at the end, we're going to have no remainders. So therefore, this binomial evenly divides into our polynomial. Any questions?
All right. So in this problem, again, we're going to determine if it's a divisor. So I make sure it's in standard form. I have x squared plus 1 is my divisor. And then that's going to divide into 3x to the 4th minus 4x cubed plus 12x squared. I notice that there is not an x term, so therefore I'm going to add a 0x plus 5. Does everybody see what I did? Okay. Again, it's not required to have that 0x. But guys, I mean, this is already hard enough, the process. I think it just makes a lot more sense to put in a space value for you. Yes? That's your divisor. Divisor. You just, OK, so now we're asking ourselves, how many times does x squared divide into 3x to the 4th? Again, if you're having trouble doing this or understanding this, it's first important not to talk when we're going over the problem. And secondly, I would just say write it into the side. Write it off to the side. Just do your math on a separate section. X squared goes into 3x to the 4th, x squared times. Now you take that answer and you multiply it by both terms in your divisor. X squared times x, oops, I'm sorry, that goes in there 3x times, right? So x squared times 3x squared is 3x to the 4th. 3x squared times 1 is a 3x squared. A big mistake students do is they put the 3x squared right here. The problem is you cannot combine x cubed and x squareds. Because remember, when you're adding and subtracting, they have to be like terms, right? So since these are not like terms, don't put that there. You can only put the 3x squared under the other x squared. So then what should I put here? Well, we can use a spacer. Right? Now we subtract the rows. Again, this is where almost everybody makes a mistake. So be very careful what the signs are. 3x to the 4th minus 3x to the 4th is 0x to the 4th. Negative 4x cubed minus a 0 is just still going to be a negative 4x cubed. Then 12x cubed minus 3x cubed. 12x cubed minus 3x cubed. Right? Think of it as like 12 apples minus 3 apples, right? Is going to be 9 apples. The x cubed still stay there. Yes? Oh, it's squared, yes. Sorry. Yes, you have squared apples. So therefore, that's going to be a positive 9x squared. You could subtract or bring these down, but unless you need them, I don't really worry to bring them down. So now we do the same process again. X squared divides into negative 4x how many times? So negative 4x cubed divided by x squared. Well, 1 goes into negative 4 times. X squared goes into x cubed. Remember, subtract the powers. 3 minus 2 is 1. So that's x to the first. Oops, that's a minus. Minus 4x to the first power. Now, we multiply that down. Negative 4x times x squared is going to be a negative 4x cubed. Actually, let me write it in red. Right? Negative 4x times 1 is a negative 4x. I can't subtract that from x squared, so I'm going to put that over here. So therefore, I'll bring down this 0x now to help me with my subtraction. I don't have an x squared, so then I'll use, again, another place value. Getting messed up with my... OK, so now I subtract the rows. Negative 4x cubed minus 4x cubed is 0x cubed. If you guys notice, that pattern is always going to happen. 9x squared minus 0x squared is? 9x squared. And then 0x squared minus a 4x? 0x minus a negative. Remember, minus a negative, guys, is the same thing as adding, right? So that is now a positive 4x. Now again, we keep on doing the process. X squared divides into 9x squared how many times? 9. Positive 9 times. 9 times x squared is 9x squared. 9 times 1 is going to be a positive 9. I don't have an x to the fourth, so therefore I'll put into my space value. I'll bring down this 5. And then I subtract the rows. 9x squared minus 9x squared is going to be 0x squared. Do you guys notice how that first term always goes to 0? 4x minus 0x is 4x. And then 5 minus 9 is negative 4. So therefore, this is now my remainder. OK, so in the first example, I did not have a remainder. Now I have a remainder. Doing this problem, the main thing that we're going to first look at is I'm going to take how many times does x squared get divided into x to the fourth? Again, I'm still having trouble. People are still having trouble with doing these. Again, I will just remind you, write it onto the side. How many times does x squared divide into x to the fourth? Using the rules of exponents, the answer is x squared. So we place x squared right over here. Then you multiply x squared times both terms in your divisor. Oh, first of all, we're in descending form, right? Like descending powers? OK. So x squared times x squared is x to the fourth. X squared times negative 2 is negative 2x squared. But there's a problem. The next thing is negative 3x cubed. So we have to rewrite it over here. Because you're subtracting vertically, ladies and gentlemen. And just a reminder, you guys know x squared minus y squared, those aren't like terms, right? You can't subtract x squared minus y squared, correct? Nor can you do x squared minus x cubed. So to add and subtract polynomials, which we've already kind of did in our focus lesson, you have to have the same base and the same power of your exponents. These do not have the same base and power, so you cannot subtract them. So I can't put a negative 2x squared under an x cubed. So then what do you do here? You don't have to do this, but to make sense of it, I a lot of times just like to put a 0 as my place value. Because think about it. What's 0 times anything? 0. And negative 2x minus 0 is just still going to give you that negative 2x cubed. So now I subtract my rows. I'm seeing a lot of students that are still not putting them in parentheses, which you don't have to, but I'm just telling you, this is where people make their mistakes. So you have x to the fourth minus x to the fourth is 0x to the fourth, which is just 0. Negative 2x cubed minus 0x cubed is just going to be negative 2x cubed. 3x squared minus a negative 2x squared. Sometimes this trips people up. So double negative, that gives us a positive 5x squared. And then I can just bring down my negative 4x, and I can bring down my positive 5. Is everybody OK with that first round that I did? Because now basically what we do is we just rinse and repeat. We just do the same process over and over until we can't divide anymore. But the general form of taking your first term of your divisor, dividing into the first term of the dividend, writing the quotient up top, multiplying your quotient times both terms in your divisor beneath, and then subtracting vertically. And that's what you do over and over and over again. So now we did it once. Now we have to do it again. How many times is x squared divided into negative 2x cubed? Not really sure how to do that. So I'll just write it vertically so it makes a little bit more sense. What do we do when we divide exponents? We subtract the powers. So what x cubed minus x squared is? X to the first. And you're just going to have a negative 2x to the first, or just negative 2x. Then I multiply negative 2x times both terms in my divisor. So I get a negative 2x cubed. Negative 2x times negative 2 is a negative 4, which again is going to have to go over here. Negative 4x. Again, subtract the rows. We don't have an x squared in here, do we? So I like to put place values there. You don't have to. You could easily just bring it down. It's going to be the same value. But here we get 0. Here we get 5x squared. And then here, which is again is a double negative, which is going to give you a 0. And then we have plus 5. So I'm not going to write that in there. Is everybody OK? So we did it twice. Can we do it a third time? Yes, we can, because x squared divides into 5x squared. How many times does x squared divide into 5x squared? 5. Put 5 up here. Multiply 5 times both terms. 5 times x squared is 5x squared. 5 times negative 2 is a negative 10. And we get subtract. So therefore, we get 0. And we have 5 minus a negative 10 is 15. So we have our remainder. So we write our q of x is equal to x squared minus 2x plus 5 plus my remainder over my divisor. All right. So, ladies and gentlemen, if you're going to divide this one, the main important thing is we want to apply the division algorithm. So we're going to write this using the long division format. Since you're taking 4g squared minus 9 divided by 2g plus 3, I'm going to write this as 2g plus 3 divided into 4g squared. Now, I don't have a g term, right? I have a quadratic, but I don't have a linear term. I told you guys when we first learned this, I would like you to make sure you don't have to, but it's very, very helpful when learning long division to give yourself a place value of 0g minus 9. All right? It's not necessary, but it's helpful. Okay? So now let's just go through the long division algorithm, and let's work through it. Again, we got to make sure this is in standard form, which it is, a binomial with our large term first. Then I just take 2g divided into 4g squared, and that goes in there 2g times. That's 4g squared, part of your answer.
I know what I'm saying.
And that's now just 0g.
But no, talking about like 2g times 2g equals 4g squared.
Right, exactly. And that's what we just go and double check. So we do 2g times 2g is going to give us 4g squared. And then 2g times 3 gives us 6g. And the reason why we like doing the place values, it just gives you something to, even though we know this is 0, it's just helpful to say 0g minus 6g to kind of help us get our answer. So we put parentheses around the whole second term and then subtract. 4g squared minus 4g squared is 0g squared, which we know multiplies to give us 0. 0g minus 6g is a negative 6g. Then we say how many times is 2g divided into a negative 6g? And that goes in there negative 3 times. Now you multiply the negative 3 times both terms. Negative 3 times 2g is a negative 6g. Negative 3 times positive 3 is a negative 9. Bring down this negative 9 to subtract, put it in parentheses, and subtract. So negative 6g minus a negative 6g, that becomes a double negative, which is 0g, which is negative 6g plus 6g.
The negative 6g and the negative on the outside, so we're going to make it a positive 6g.
Right, so it's negative 6g plus 6g, which is 0g, which you got. And then a negative 9 minus a negative 9, again, becomes 0. So therefore, your remainder is 0, and your final answer is 2g minus 3. Problem. Yep, I'm going to, what do you mean another way? Sure. Yeah, I'll do that. Yes, do you have a problem? Question?
Oh, yeah. Where'd you get the 6?
2g here, this 6?
Oh.
That one?
Yeah.
I did 2g times 2g, which is 4g squared, and then 2g times 3, which is 6g. You got to make sure whatever your divisor is, or your quotient is, you multiply that by both of your divisors. Okay?
So you got the 2g.
So the first problem that we just need to work on, and all this is asking us to do, ladies and gentlemen, is first just describe the end behavior. So all we need to do is just look at this graph and just kind of say, you know, what is happening with the graph? What is like the end behavior? What is the lasting effects that this graph is doing? Because it does all this crazy stuff right here, right? It goes up, goes down, goes up, goes down. But what is it finally going to do? What is its end behavior? So we look, as the graph continues to the left, we could say it's going to fall left. So we're going to say that the graph falls left. Then, as we're going to the right, you can see that the graph is also going down. So we can say the graph falls right. Now, in case we have a test or we need to write something a little bit more mathematical, we can kind of describe it as far as what are the points doing on the graph. So we're going to talk about this as a function. So we're going to say that this is your f of x axis, and this is your x axis. So what we notice is, as my points, remember each point has an x and a f of x point. As my points go to the right, and they're going to keep on going to the right till they go to infinity. So as x goes to infinity, so my points of x go to infinity, my f of x points, are they going to go to positive f of x or negative f of x? Negative f of x. So as x approaches infinity, f of x approaches negative infinity. Then we start plotting points of x in the negative direction. And we go in the negative direction, we say as x approaches negative infinity, my coordinate points f of x, do they approach positive or negative infinity? Negative infinity. So there you go. That's all you guys had to do to answer question A. For letter B, it says determine if it's an odd or an even degree. So to do that, all we simply did is determine the number of zeros that we had, or what we called our x-intercepts of the graph. Now remember the definition last class period, what we talked about. So what we talked about last class period is when you have an even number of zeros, that told you you're going to have a even degree of a polynomial. Or if you had no zeros at all, then you could have also an even one as well. So therefore, how many zeros do we have? 2. So therefore, our degree of this function must be even. So you're going to say B is going to be an even degree. And then C just says state the number of zeros, which in this case we have 2. Done. So that's all you guys had to do for 35 through 40.
Welcome to left and right side behavior of a graph. So today what I want to do is show you how to find or determine the left and right hand behavior of a function. Now, the reason why it's helpful to determine the left and right hand behavior of a graph is it's going to help us determine, you know, when we have a graph that is with a very high degree, it's a lot of time hard to determine where is your graph heading and, you know, kind of what does the graph even look like? You know, am I plotting the graph correctly? You know, what is actually the form of this graph? So there's a couple rules that we can follow to find our what is the end behavior of a graph? Where is it started from and where is it heading to? So when doing this, a couple things we need to know about our Cartesian coordinate system. So if we have an x and a y plane, one thing we know that is that our x, this goes on all the way to infinity. So remember this x line here, our x-axis, goes all the way to infinity, and it also continues all the way to a negative infinity. Now, for usually you've learned that this is your y-axis, and you know your y-axis goes all the way up to infinity and all the way down to negative infinity. But since we started talking about functions, what we've started to do is really replace our y, I'll keep it there, but our y with a f of x. Because we use our f of x as our output value when we were talking about functions. And this is just going to help us write our
end behavior a little bit better, because what we'll notice is we're always, you can see I have a list of functions here. So it's going to be helpful for me to write my end behavior in terms of those functions. The next thing I want to kind of go back through is something that you guys should kind of have a little prior knowledge with. And those are going to be our two parent functions. So what I did was I wrote f of x equals x squared, and I also have f of x equals x cubed. Now, I wrote up these two parent graphs because, and I also wrote the reflections of these two parent graphs, because when I'm doing left and right hand behavior, this is going to tell me, this is going to be my best clue for me to be able to determine how I know what's happening with my graph. So the next thing we need to look at is, if I have a negative x squared, now my graph is going to be reflected downwards. And if I have a negative x cubed, what you notice is my graph is a reflection of that over the x-axis. Now, something important to understand about the end behavior is, if you look at the end behavior of my x squared, my graph just in the blue here, what you notice is it doesn't really matter as my x goes to infinity or negative infinity. Both of my end behavior all the time both comes up. It never goes below its minimum point. However, if I have a reflection of this where it's a negative a, well, now my end behavior goes down to negative infinity for both, no matter if my values are going to the left or going to the right, all my values go down to negative infinity. And what's important now about when I have an odd degree with this function is my function, my regular function, as I go to the left, my behavior goes down to the left, to the negative, and as I go to the right, my end behavior goes up. Well, when it's the negative version, it's the exact opposite. When I go to my x values go to the left, my graph rises, and when I go to the right, my graph falls. So I'm going to use a little bit different analogy for both of these problems, and I just want to kind of use some general tips that we're going to talk about. So there's some general rules that we like to say, and a couple things we need to understand is, what we're going to do is we're going to look at our degree of we're going to look at the degree of a polynomial, and we're going to look at the coefficient. And I don't know if I have enough room over here or not, but one thing we need to know is when your degree is even, okay, what you're going to have is your end behavior is either going to be both rising or both falling. All right, and I'll go a little bit more technical definition in a second. But you guys can notice, if it's an even degree, either my graph always rises or it always falls. However, if my degree is odd, I'll erase this. If my degree is odd, then my graph either falls to the left and rises to the right, or my graph rises to the left and falls to the right. Okay? And another way you might say, well, okay, I kind of understand the rise and the left. Another way that sometimes textbooks that we use to represent this is we say, as x approaches infinity. So what I can say for this is, as my x values approach infinity, as they keep on going to infinity, my f of x, which is my output value, where does that go? And you could say for this function, as x approaches infinity, my function approaches infinity. And then for f of x equals x squared, as x approaches negative infinity, so as my graph approaches negative infinity, my f of x, my output, also approaches infinity. Okay? And what we notice is, since my degree was even, we notice that both of these both rise, meaning they both go up to positive infinity. However, let's take a look at the negative infinity, or the negative x squared. So now, as x approaches infinity, my f of x, my output value, is now going to approach negative infinity. And as x approaches negative infinity, what you can determine is now my f of x, the output value of my function, now approaches negative infinity. So sometimes you might be dealing with some notation that's going to look like this. To make things simpler for you right now, I'm just going to deal with rises to the left and rises to the right. So what we're going to do is to determine this, I'm pretty much going to go off of what my parent graphs are. And because it's really easy, because it doesn't matter. As long as, if you have an x squared, if you guys can just remember what a parabola looks like and know, okay, when it's a positive x squared, it opens up. When it's a negative x squared, it opens down. This is going to be the same end behavior if it's x squared, x to the 4th, x to the 16th. You're going to have the same end behavior. The same thing with a cubic function. If I have x cubed, what that means is I'm going to fall to the left and rise to the right for all of them. So x to the 5th, x to the 17th, they all have the same end behavior. They fall to the left, rise to the right. However, if I have a negative coefficient, a negative leading coefficient on my term, now it's going to be the exact opposite. It'll now be rises to the left and falls to the right for all odd. So let's go through some problems and let's try to see what we can do for this. So here I have a negative x squared plus 6x plus 9. I don't care about any other numbers except for my leading term, which is a negative x squared. Since, so now I'm just going to rewrite this. I have a negative x squared. Since my 2 is even, I know it's going to look like a parabola. And since I have a negative, it's going to look just like this. So therefore my end behavior is I'm just going to say falls left and falls right. Okay? Over here, let's take down our leading coefficient, which is 1/2 x cubed. So now we have an odd degree. So therefore, it's going to be one of my odd graphs over here. And what you can see from here is on my odd graphs, and then I have my leading coefficient, which is positive. So therefore, it's going to look like my blue graph right here, which is f of x equals x cubed. So therefore, my graph is going to fall to the left and rise to the right. The next one, you're going to have to do a little distributive property. Once you do a little distributive property, what you get is a 3/4 x to the 4th. Okay? So now I look at my degree, and since my degree is even, I know it's going to be either one of these graphs. This is f of x equals x squared, and this is f of x equals negative x squared. Now, I look at my leading coefficient, and I notice that that is a positive number. So therefore, it's going to be f of x equals x squared. It's going to replicate exactly the same end behavior. So therefore, I can say that it's going to rise left and rise right. Because what you can notice is this graph is going to follow the same behavior. It rises to the left and it rises to the right. All right, lastly, let's bring down our leading term, which is a negative x to the 5th. Remember, I don't care about any other terms, so let's just write this down. We look at it, it's going to be an odd, so it's going to follow my black graph here, which is f of x equals negative x cubed, which follows this pathway. Now, since it's negative, it's going to rise to the left, and it falls to the right. Rises to the left, and then falls to the right. Okay, here we go. Let's go and take a look at end behavior. Now, before we get started, a couple things I want to remind you. Remember, our end behavior is going to follow the same paths. When we have a degree that's even, our end behavior is either going to both rise or both fall. When do we know when they both rise or they both fall? That all depends on if my leading coefficient is positive or negative. If it's positive, both of my end behaviors are going to rise. If my leading coefficient is negative, both of my end behaviors are going to fall. These are two different functions, if you haven't noticed. This is f of x equals negative x squared. This is f of x equals x squared. If my degree is odd, then it's going to fall, then it falls left, rises right, or rises left, falls right. Well, how do we know which one it is? Well, if our f of x is positive, it has a leading coefficient that's positive, it's going to fall to the left and rise to the right. If my leading coefficient is negative, it's going to rise to the left and fall to the right. These are two different functions drawn on the same graph. I hope it didn't confuse you. So here we go. So remember, when we're trying to find the leading coefficient, all we need to simply do is just take out our leading term and then determine what it's going to resemble in our parent graphs. So here, I represent my leading term as a 1/3 x cubed. So now what I need to do is I need to determine, okay, I have an odd degree and a positive leading coefficient. Since I have an odd degree and my coefficient is positive, my graph is going to fall to the left and rise to the right. So all I'll simply just say is falls left, rises right. The next one, I simply take down my leading coefficient, which is 2x squared. Now it's even, and it's even, and my leading coefficient is positive. So there I have an even degree, and the leading coefficient is positive. Therefore, my function rises left and rises right. On this one, this gets a little bit tricky because guess what? My leading coefficient term, these are not in descending order of their degrees, right? This term should be front and center. However, we have the constant in front, which is all kind of messed up. So we just need to make sure if we were going to rewrite this correctly, it'd be 3x squared minus 7 halves x plus 5. So now what I can notice is this is going to be my leading term. So I have negative 3x squared. Well, very simply, it's going to be an even degree, but my leading coefficient is negative. Therefore, my end degree falls left and falls right. Lastly, here again we have another term where it's not in descending order, right? Remember, when you put in descending order, you have to have your highest degree up and then go down all the way to your constant. So this function needs to be rewritten as negative x to the 6th plus 1. Now what I can do is, when I have it in this form, now I determine, well, my x is positive and the number in front is a negative. Therefore, it's going to represent my parabola, which is flipped, which is facing downward. Therefore, I can say my end behavior is false to the left and false to the right. All right, ladies and gentlemen, that's it for the video. I hope this helped you out, and please make sure you come back and go and check out the rest. Thanks again.
So for this problem, what we're going to look at is we have f of x equals 2x to the 5th minus 5x plus 7.5. So what we're going to do is we want to find the end behavior of this graph. So what I'm going to do is I need to remember what exactly my end behavior I'm going to be looking for. And I just actually want to double check here. I want to make sure I have the correct, and I'm going to be answering this question exactly the way I want to. So this is question, okay, right hand and left hand behavior of the polynomial function. Perfect. So I'm looking on this problem. First thing I need to do is I need to make sure that my quadratic function, or not even quadratic, but just my polynomial function, is in descending order. And what I mean by that is I have my degree of my polynomials first. So the highest degree, or the highest exponent, is going to be first, which we call the degree of our polynomial function. Then from there, it is in descending order. So I look at this and I say, all right, x to the 5th, that's the highest power. Then the next highest power is x to the 1st, and then my constants are always at the end. Well, there should only have one constant because you could combine like terms. Here's an example. If originally the book maybe gave me the problem as negative 5x plus 2x to the 5th plus 7.5, that's not written in descending order. You need to make sure that your highest exponent is in front. So it's what we call your degree, and then it goes in descending order from there. So the problem already starts like that, and so we're good. The next thing we need to do is we need to find our leading coefficient, and that leading coefficient is going to be very powerful in telling us what's going to happen. So if our leading coefficient, it's either going to be a, remember it's a is your coefficient, a is either going to be less than 0, or a is going to be greater than 0. Then the next thing we need to look at, and in this case we have a is greater than 0, right? So we have 2 is greater than 0. The next thing we need to look at is at our degree. And is that going to be odd or even? And of course I'm writing odd because that's odd. And one thing that really helps me out, because I don't want to keep on remembering to infinity, to positive infinity, to negative infinity, all that other kind of mumbo jumbo. I always like to remember if it's odd, I'm going to make it look like a cubic function. All right, where going this way is to infinity, this is to negative infinity. Up the y-axis is infinity, down the y-axis negative infinity. So I know that, first of all, that's going to look like this. So an odd function is going to be in this form. And whenever it's greater than 0, it's going to look like this. If it was negative, if it was less than 0, then it would look like that. But since a is greater than 0, it's going to give you my original parent function, which this is f of x equals x cubed. Just so you guys know. So this is going to help me. I don't know what 2x to the 5th is. I don't know. But what I do know is that it's going to have the same behavior as all odd functions with a real number greater than 0 in front of them. So they all have the exact same end behavior. That's the beauty about it. That's what makes it so easy. So if you can remember the easiest odd function, then you're good for the rest of, we can go up to 17 to 81. Any odd number one you want to pick, they're all going to have the same end behavior. So I like to remember the easiest one and then just transcribe that for all other odd functions. So if it was greater than 0, it looks like, or if a is greater than 0, it looks like this. If it was negative, then it would have been, remember you would have been reflected about the x-axis or y-axis in this case. So let's look at it. How are we going to describe what the end behavior is? Well, as, you could just, there's a couple ways you could write this. You could say that it falls as x approaches negative infinity. So as my x values, here's my x values, right? As I'm going towards negative infinity, my function f of x is going towards negative infinity as well. And then as x approaches positive infinity, so I'm going to the right, my f of x goes to positive infinity. And kind of depending on what the question is and what the answer is, some people also say, well, it's going to fall left and it rises right. So those are kind of two different notations. It's really going to kind of depend on your teacher and the context of the question, what they're asking for. But pretty much, guys, if you can just remember when doing the leading coefficient test, just use your basic two functions. For odds, I use x cubed because it's easy for me to remember it. And then for if it's even, I use x squared. And the only thing you need to know is you just need to know the end behavior for those two functions. It's not hard to remember that. Just remember the end behavior for those two functions. And it's because it's going to be true for all even and all odd. And then the only thing else is you need to look at the coefficient of your leading term. And if that coefficient is negative, then remember you're just going to have to make sure you reflect it and then do the exact same thing. All right, so that's how you use the leading coefficient term on 2x to the 5th raised to 5x plus 7.5.
In this example, ladies and gentlemen, what we have is we have a polynomial, and they're just asking us to identify the end behavior. So the first thing, as I told you, that I want you to do is to write it into standard form, meaning that we need to have the powers written in descending order. So you could put an x to the 0 if you like for that, just to kind of visualize it. So if I was going to put these in descending order, I would have negative 5x to the 4th plus, minus x cubed plus 4x squared plus 9. You don't need to write the x to the 0, but I just wanted you guys to visualize when you put your phones away so you can focus on the instruction, that you can see that the powers are going down in descending order. Because if you weren't paying attention, you probably wouldn't recognize that, and then you probably would have kept it the way because you would have thought that leading coefficients were what determines it. But that's not the case. It's how the powers are in descending order. Does that make sense? Everybody's OK with that? So now, when you're determining end behavior, the only thing we care about, we need to understand what the degree is and what the leading coefficient is. So in this case, the degree is 4, and my leading coefficient is negative 5. However, as I mentioned, we don't really care what exactly the leading coefficient or the degree is for end behavior. We only care, is the degree even or odd? Is the leading coefficient positive or negative? So a lot of times to help myself out or to explain it, I just give you guys those options. And that's it. That's all you need to care about. So is 4 even or odd? Even. It's divisible by 2. Right? Even numbers are always divisible by 2. Odd or even? Or odd or negative? Negative or positive?
Odd.
Negative. Sorry. OK? So now we go to our notes. and we look at, well, what was our notes then that talked about when we have an even degree and a negative leading coefficient? Yes. The one who says hateful comments to me. Yes.
Yes, it's the upside down.
OK, so what did we say was the end behavior, though? What did we say? What did we?
It would be, so it's the down, left, down, right.
Down, left, down, right. I prefer to always say falls left, falls right. But you could say, for right now, you could say down, left, down, right. This one. So first of all, one thing we didn't talk about is we've got to find the, or when we're talking about a degree, we didn't talk about when it's not in standard form. Standard form means it's basically in descending power form. Our largest degree, or our largest power, always has to be first. So let's rewrite this in our standard form. So that's a negative 4x to the fifth minus 3x squared plus 1. Now it's in descending order. You can see that your degree is 5 and your leading coefficient is negative 4. Again, remember, there's only two questions we need to ask. Is my degree even or odd? Odd. So a lot of times I'll write degree is odd, and my leading coefficient is either positive or negative, which in this case it's negative. You could try to memorize what this says over here on this chart, or you can just think it's odd. That means it's a line, right? It's negative. That means it looks like this, right? So that means it rises left and falls right. But to make sure that I get full credit, I want to talk about my end behavior using limit notation. So I'll write limit goes to the left. That means x approaches negative infinity of our function f of x. Since it rises, that means it goes towards infinity. As it falls right, that means as my function limit as x goes to infinity, which means goes to the right of my function f of x, it falls. That means it goes down to negative infinity. OK? So all you guys have to do for this, all you have to do for this one is understand multiplication of polynomials. If you guys were to multiply these two by applying FOIL, right, the product of those two polynomials is going to produce what is the highest power that the multiplication is going to produce here? Squared. And what is the coefficient of that term that's squared? Negative 12. Because negative 3x times 4x gives you negative 12x squared, right? Who cares what the rest of it is? Why am I saying who cares what the rest of it is? Because on the last example, did we care what any of those other numbers were? No. We only cared about the front term, right? So now, if I was going to multiply this times that, again, we only are concerned about multiplying the front terms, because that's going to produce the highest degree. So this becomes negative 24x cubed. Doesn't matter what the rest of it is. Do you agree with times that? So now we can say that the degree is equal to 3, and the LC is equal to negative 24. So we know this is, again, is odd, and that is negative. Now, last example, I did a problem where we had an odd and positive. Now we're going to do an odd and negative. And if you guys look at my little chart, the only difference of odd degrees, if LC is positive, it looks like this. If LC is negative, it looks like that. So now we're going to do our left hand. That means as we go to the left. So how do we write as we go to the left? As x approaches negative infinity, f of x approaches. And then we'll do our right hand. As x approaches infinity, f of x approaches. So now let's just fill them in. So as I go to the left, where does my f of x go? Up, which is going towards positive infinity. And then let's do the right hand. As my x values go to the right, the graph is going down, which is negative infinity. Does everybody feel a little bit more comfortable with end behavior now?
First of all, find the zeros is just a way when we're talking about functions to really solve the equation, all right? The zeros are going to be when each one of the solutions to these equations when they set equal to 0. So in Algebra 2, you guys factored and you learned how to solve when an equation was set equal to 0. Now we're talking about functions. And just here's a function, so now it's just set up as, f of x equals, here's your function, your polynomial. And when I say find the zeros, all I'm telling you to do is set it equal to 0. Tell me the solutions that make that equation true. Because the solutions that make that equation true are what we call the zeros. But don't be confused just by the name of zeros. The zeros are where the graph crosses the x-axis, right? Those are your x-intercepts, or where the graph touches it. Now, how do we determine if it touches it or it crosses it? That's multiplicity. Multiplicity, if you guys remember, tells us, does the graph touch at the x-intercept or cross? So, to solve an equation like this, you can't subtract the 4 and then divide by 5 because it's a quadratic, so we have to factor. So hopefully you guys can see on this one, by factoring this, we can set this as x minus 4 times x minus 1, right? I don't know why my 4 is like that. Right? Everybody follows me with this factoring? So if I take a function, set it equal to 0, I factor, now I apply the zero product property, x minus 4 equals 0, x minus 1 equals 0, add the 4 to both sides, add the 1 to both sides, and therefore you can see the zeros here are x equals 4 and x equals 1, right? But now, and these are also the x-intercepts, but now we need to determine what is the multiplicity. So in determining multiplicity, remember guys, we had the form of x minus a raised to the k, where k told you the multiplicity. That was in your notes. So k is your multiplicity. So what we do is we go back and look at our factors. Here is the set of our factors. And you want to make sure that you have this set as your linear factors, will really help. But you look at this and you say, all right, what are the exponents of each one of my factors? And the exponent of both factors are?
0. 1.
Well, I circle them with the 0, but they are going to be 1. Right? Sorry, that was probably confusing. But inside each one of those is a 1. Right? I just kind of put a circle like where it should be. So therefore, it has a multiplicity of 1, which is odd, so yes.
But what if it doesn't factor into 2 perfect square? Or it doesn't factor like into that? Like this one, it like...
I'm going to go over that problem. I'll go over that. Don't worry about that. I'll go over that problem. So here, you have this as 1 and 1, so therefore you have an odd multiplicity, right? So your multiplicity, so you can write, you have an odd multiplicity of 1, right? And so what does that tell you about the graph? At each one of these zeros, or x-intercepts, the graph crosses. Okay? The graph crosses, yes.
How do you know whether it crosses or touches?
If it has an odd multiplicity, it crosses. If it has an even multiplicity, it touches. So let's go and take a look at what this, now, if you guys wanted to look at this graph, we know this is a quadratic, we know the end behavior is even and positive. So if I was going to graph this, right, I know it crosses at 1, 2, 3, 4. I know it crosses at 1. And I know the end behavior is going to go up and up. So if I just wanted to kind of sketch this graph, I know it's probably going to look something like that, right? All right, now let's go over to this problem. This problem, we have x to the 6th minus 5x to the 4th plus 4x squared. Now, if I was going to factor a problem like this, first of all, you always want to see what you can factor out as far as a GCF. And I noticed that they all have an x squared. So let me factor out an x squared. Okay? Now, we need to go ahead and factor this further. So you might look at this and say, well, how do I factor this? Well, ladies and gentlemen, do you see how this and that are exactly the same? The only difference is instead of using x times x, I have to get to x to the 4th. So when I factor this, I'm going to use x squared minus 4 times x squared minus 1. All right. Now I can use the zero product. Now I can use the zero product property for each one of these and say x squared equals, actually, Let me write this as a 0 real quick. Or as a factor, I'm sorry. Alright, do you guys see how x squared is the same thing as x minus 0 squared? Alright, but remember all factors are written in the form of x minus a, so you have to subtract it from your a. In this case, for x squared, it's just a is 0. Okay? So I'm just writing it in factored form. So now I have 3 factors. Well, not yet. I don't have my linear. I can rewrite these as my linear factors, but anyways, I can set these equal to 0. All right. Then I just solve for each one, right? So in this case, I have x equals 0. Here, I have x equals plus or minus 2. Here, I have x equals plus or minus 1. Okay, can't tell you how many students took the square root on their homework and forgot to include the plus or minus. So now I have x squared equals plus or minus 2, x squared equals plus or minus 1, and x squared equals 0. Now, it would be kind of helpful if I broke these, if I factored these a little bit further, because you can factor x squared minus 2, right? That's a difference of 2 squares. So it might be easier to look at the factors like this. If I factor this, I can factor that to x minus 2 times x plus 2. This can be factored into x minus 1 times x plus 1. That's another way to factor this further. If you guys notice these are difference of 2 squares, you don't have to, but I think it's easier when you look at this because now you guys can look at every 0. Now we need to look at every single factor and determine the multiplicity. So, here, this one has a multiplicity of 2, right? Yes? So you can just say an even multiplicity. Here, multiplicity of equal to 2. Here, 1, boom, boom, boom. And I'll say m equals. Here, the multiplicity equals 1. So, what does it say about multiplicity when it's even?
It has an even square root. It touches.
It touches. Here, the multiplicity is just going to cross at each one of these. All right? And so what's so important, though, here's what I want to get, because this gets confusing. The reason why we like to determine multiplicity on the linear factors, yeah, these are quadratic. But ladies and gentlemen, what is still the k on the outside of that factor? It's still 1, right? So don't be worried about what is inside the factor, because you need to actually factor these down to the linear factors, where every single term inside of there is linear. But anyways, it all depends on, still, even if I left this as x squared, this factor is 1. However, there's 2 zeros within that as you solve. All right? And what's nice about that is, I'll show you guys how you can graph that real quick. Just by knowing that, you guys should know what the graph looks like. Because if I have a graph, first of all, it's even and the LC is positive. So the end behavior looks like that. Then I have a 0 at 0, negative 2, positive 2, negative 1, and positive 1, right? But this is the only one that has a multiplicity of 2, right? So that means it's going to rebound. It's either going to go up and up or down and down. So if I follow this end behavior, I know it has to cross here, it has to cross here, but then it has to rebound. So if I'm already up here, it has to look like that. But then it has to cross this one, it has to cross that one. Now that's a horrible representation of a graph, but you guys can see that's what that graph will look like. If you guys take your graphing calculator, you'll see that's exactly what the graph goes for. All right, you don't have to graph, but I just want you guys to see, you see how this multiplicity, how that works when you have a multiplicity. So just look at the factor to determine the multiplicity, okay? All right, what we're going to work on right now is graphing polynomial functions. And we're going to graph them, not by using a graph calculator, which is probably the best tool for us to graph them in the future and also to check our work. But right now what we're going to do is we're going to graph them off of what we learned. And the first thing we learned was our leading coefficient test. And remember, the first thing with our leading coefficient is we need to determine what is our leading coefficient. Well, remember, your leading coefficient is your first, your first term. And actually, our first term, we have x to the 4th. And remember, inside of there, we always have a number it's in front, which is a. And on this point, a is either greater than 1 or less than 1. And for this problem, I have a is greater than a is either greater than 0 or less than 0. For this problem, our a is 1, and it is greater than 0. Obviously, it's not negative. Are you nudge her? Nudge her? Elbow her? Yeah, there we go. This is important stuff. So for this one, my a, which is in front of my x squared, or my, what are my leading term, is going to be greater than 0. And then also my degree is even. So when it's even, we either have our end behavior is either both going up or both falling. So they're both rising or both falling. And it all depends on if my a is positive. Since a is positive and my degree is even, I'm going to rise left and rise right. All right, that's your leading coefficient test. We've done videos on that. We've done problems on that. Everybody should get to that point. The next thing, so we know what our end behavior is. The next thing we need to do is determine what our zeros are. So remember, our zeros are when g of x equals 0. So I'm going to say 0 equals x to the 4th minus 4x squared. Working on my factoring, first thing I want to do is always factor out common terms. I can factor out an x squared. That's going to leave me with x squared minus 4. All right, I can't factor this any further, so what I'm going to do is I'm going to write this as a set of linear terms when I have a set of linear factors. Since these both multiplied gives us zeros, I can say that x0 equals x squared and x squared minus 4 equals 0. Solving now for 0, and one thing to just kind of notice, you guys notice my linear factor is squared, right? I could write this like this. Right? That's the exact same thing. Remember, whenever you have your factor and it's squared, we know it's going to be a multiplicity of 2. Or when it's squared, it's to the 4th power. Whenever it's to an even power, we're going to have a multiplicity of 2. So let's just write in. And that's going to become very helpful when we're graphing this. So x equals 0. However, I know it's going to have a multiplicity of 2. Here, my whole factor is not squared. I know the x is squared, but the whole factor is not squared. So therefore, my answers for these are going to be a multiplicity of 1. So I add a 4 onto both sides. X squared equals 4 square root. X equals plus or minus 2. Right? And these are going to be a multiplicity of 1. Graphing it. First thing we want to do is we want to apply our points. We know we have a point at 0, 0, -2, and +2. Right? We know our end behavior. It's going to rise to the left and rise to the right. All right? So that's all we know right now. That's from the earlier part of the chapter. Everybody should be able to do this for every single problem, right? Now, the last thing we just need to do is, by using the intermediate value theorem, we know that there exists on this graph, we know that there exists a point between these two zeros. We also know there's a point between these two zeros. Now, there's one more important thing I want you to remember. Before even picking my points, this is a multiplicity of 2. So that's going to tell me it's going to touch it, right? Correct? So that means it's either going to go, I'm not going to cross at 0, 0. And here, if I'm going down, this is telling me it's going to go through, since these are a multiplicity of 1, it's going to cross. So that means I'm going to have a line that's going to go through those 2 points. And just always thinking, since this one has to bounce or touch it, I know it's going to be a downward spiral. Because there's no way I can go an upward spiral and then have it not cross again. So let's pick these 2 points. I picked, how about we do f of -1 and f of 1. Let's make this easy on ourselves. So f of -1 would be -1 to the 4th minus 4 times -1 squared. F of -1 ends up equaling -3. Negative 1 to the 4th power is 1, right? Minus negative 1 squared is 1. 4 times 1 is 4. 1 times minus 4 is negative 3. So I go down to negative 3. 1, 2, 3. I'm going to make a point. F of 1 would be the exact same thing. So that's going to give me 1 raised to the 4th power minus 4 times 1 squared. F of 1 equals negative 3. So then I go down to here. So now, all I got to do is just connect all my points. I've found 2 points between my zeros. I know what the multiplicity is, and I know what the end behavior is. So let's connect. It's amazing, isn't it? So that is how you find, that's how you graph a polynomial using your leading coefficient test and your zeros, and using the multiplicity as well.
So first thing we do when we're solving for our x, we're going to set this equal to 0, right? Because we have more than one x, right? It's not like a linear equation where you just undo the properties of equality on both sides. We have more than one x. And now, previously, even on your homework for the 1 through, well, you didn't have to do that for 1 through 4, but previously you'd have to factor it down. But this is already in what? Factored form. It's already factored, right? So we don't need to do anything with this. It's already factored, so that's perfect. And the reason why we want factored form, or it written as a factorization, which was on that last test, we want it in factored form because when we have multiple variables, now we can apply the zero product property. So we set each factor equal to 0. And then we just go ahead and solve. Well, here we already have x equals 0 here, so I have to use my inverse out property. X equals positive 2, minus 5, minus 5. X equals negative 5, right? So if I was going to find the zeros, or the solutions, I could write this as set notation, or I'm sorry, as solution set, right? You could leave them as like this, or you could just write it like a solution set, whatever the case may be. Is everybody okay with that? Yes, no, maybe, so. Good? OK, so we talked about the solutions. That should have been the easier part. Everybody should at least would have come up there. However, the graphing is not something we talked about, so this is a little bit of a stretch. So now we need to start thinking about what have we learned in this class. Well, one thing I talked about, especially last unit, when we have the real solutions, what do those represent? The real solutions represent what on the graph? Ooh, ooh, ooh. Yes, Julian? Close, Denise? Huh? No, you weren't. Julian's thinking about this. Yes, Julian? The x-intercepts. I think you just misspoke. But yes, the x-intercepts, right? Not the x-intercepts. So it's these are the x-intercepts. These are the solutions. So we have negative 5, 1, 2, 3, 4, 5. We have 0. And we have 1, 2. OK? Now, those are the x-intercepts. Now, what we talked about last class period, though, is the x-intercepts. There's a characteristic of the x-intercepts, which we call multiplicity. And what the multiplicity of a x-intercept tells us if the graph crosses or bounces at the 0. And the way to tell the multiplicity is to look at, and you could also write this as x minus 0 if you wanted to, is to look at the linear factor. So I look at all of my factors. Are all of my factors is the variable raised to 1? Yes. OK. So you can only determine the multiplicity of your linear factor. And then to look at the multiplicity, if you guys remember, the multiplicity was the power of the factor, which I wrote in the red. Now, there was no actually number up there, so we know that the number is 1. So we look at the multiplicity, and it's 1 for each one of those. So when the multiplicity was odd, what did that tell us about the how the graph behaved at the intercept? Did it cross, or did it bounce? It's in your notes, but does anybody remember? Yes?
It crosses.
It crosses. That was in your notes. When the multiplicity is odd, that means the power of your the power of your factor is odd. Doesn't matter if it's 1, 3, 17. If it's odd, Isabel, then the graph crosses at that x-intercept. Do you agree, Isabel? OK. So we still need to sketch this graph, correct? We still need to sketch the graph. And one thing I want you guys to look at is, do we know what the end behavior is of this graph? Do we know, does the graph fall left, rise right, fall right, rise right? We have no idea, right? So at least right now, if this was in standard form, could we figure out what the end behavior was? Yes. So you have two options. You could multiply this out so that it is in standard form. Okay? However, I'm just like you. I don't want to do any more. I don't want to do any necessary math or unnecessary math. Let's just kind of think about this in a little bit bigger picture. When you guys are determining the end behavior, we really only care about what? The first term in standard form, correct? Yes? So let's think about this. Ladies and gentlemen, if I was going to multiply x minus 2 times x plus 5, the first term in that product would be what? What would be the first term? X squared, right? So 0 equals x times x squared. I really don't care what the rest of that is, because it's all going to be smaller than x squared. And when we're talking about end behavior, we only care about the highest degree, correct? So we only care about that first term. We don't really care what the rest of this is. Then, can I multiply x? If I was going to apply distributive property, x times x squared is going to give me my leading term. So that's going to be 0 equals x cubed, dot, 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 dot. Does everybody see what I did? We don't really need to multiply this out exactly to write this in there. But you guys can see that this leading term is going to be x cubed. So if we have x cubed, what does that tell you about your end behavior? Well, the end behavior, if it's an odd degree, that means the graph is either going to fall left, rise right, or rise left, fall right. And that all depends on the leading coefficient. Is that positive or negative? Since that's positive, we know the graph falls left, rises right. Man, this mark green is not doing very well. All right, I'm going to get one.
Wait, do you want to fill this out?
Yes, you can throw it out. Does everybody see that? Does everybody see what the end behavior is? Does everybody agree with me? Does anybody have any questions? All that I've now done is determine what the end behavior was, and I found the zeros, and determine the multiplicity tells me how those zeros interact on the graph. Does everybody see that? Now, ladies and gentlemen, all I have to do to graph the polynomial is just connect. So it has to cross this 0. Then it has to go to this 0. So I'm just going to create a nice little loop. And again, I'm sketching. I'm not being exact. Then I need to come back over through here. So I'm going to loop again. And there is the equation of my graph. We have discussed how to find the zeros, or how to find the solutions from here. If you guys remember, whenever you're finding the solutions, we're going to replace our y with 0. Right? So if I give you the task of finding the zeros, if we have the product of factors equal to 0, then we know the first thing we're going to do is apply the zero product property. Right? It's already factored. Right? It's in factored form. So we don't need to factor it. We just need to set them equal to 0 and then solve. Right? We can apply the zero product property. Does everybody see that? Yes? No? Yes? OK. So now we can go ahead and use my inverse operations to solve. Take the square root. So I have x plus 4 equals 0, minus 4, minus 4, x equals negative 4, minus 1, x equals negative 1. So those are the solutions, right? Those are the real solutions. And if you guys remember what we did talk about last class period, when you have the real solutions, those represent the what? The zeros, which graphically, though, represent the x-intercepts, right? They are zeros. They are solutions. And the real zeros and solutions represent the x-intercepts. So we go to negative 1 and then negative 4. 1, 2, 3, 4. So we have these nice little points here. But there's something to graph this. There's two things that need to come into play. First of all was the multiplicity, right? And if you guys remember, we talked about multiplicity. And multiplicity was the power of our linear factors. Do you guys see how these are two linear factors? Our variable x is raised to the first power. Does everybody see that? So in the definition that we wrote down, these are linear factors. Well, you can see here I have a multiplicity of 2. And here I have a multiplicity of 1. Correct? This is what we covered last class period. So you can basically say that m is 2. And here m is 1. Now in your notes, what we talked about was that the multiplicity, if the multiplicity is even, that means the graph bounces at the 0, right? Or bounces at the x-intercept. So at -4, the graph is going to bounce. We don't know if it's going to bounce up or bounce down, but we know it's going to bounce. And at -1, we know that the graph is going to cross. We don't know how it's going to cross, but we know it's going to cross. Does everybody understand that? That was in your notes last class period for multiplicity, right? So, yes? I am going to connect them. Now, here's the one thing, though, that we did not go over. We did not go over, to connect them, though, we need to know how to connect them, right? We don't know how to connect them right now. So what I was hoping that you guys would be able to come to the thing is, to connect them, we need to understand what the end behavior is, particularly. So if you guys were to use the end behavior, let's multiply this out, or let's try to do a quick little fact. If you guys were to do x plus 4 squared, you don't need to know what x plus 4 squared is, but what is going to be the highest degree of x plus 4 times x plus 4? What is going to be the first term? X squared, right? We don't really need to know what x plus 4 squared is, but we know that the first term is x squared. Does everybody agree with me? And you guys can verify that by multiplying that out if you like. But I'm trying to save you a little bit of time and effort. Now, if I multiplied x squared, whatever it is, times x plus 1, what would be the highest degree of that polynomial, of the product of those? Well, what happens when you multiply x squared times x? You get what? You get x cubed, right? Is there going to be any other multiplication in there that's going to give you something higher than x cubed? No. So therefore, you guys can reason that the highest degree or power of the product of x plus 4 squared times x plus 1 is x plus 3. Correct? So now, not only is it x plus 3, but x squared times x is going to give you a positive x cubed. So therefore, we now need to reason, all right, so we have a odd end behavior, right? So now we need to go back to 5-1 and say, all right, well, what happens when our end behavior is odd and our leading coefficient is positive? Hopefully you guys remember that when it's odd and positive, the graph falls left and rises right. That's in your 5-1 notes as far as determining the end behavior. OK? So now, do I have enough information that I can connect? Yeah, well, I can go up here. It's going to bounce. It's going to come back down. Then it needs to go through here. And it looks something like that, like I'm just connecting them. So you guys see how this graph looks now? Does that make sense? Do you guys want to try another one? OK.
All right, what I'd like to do is show you how to graph a polynomial function. And we're not going to be using our graphing calculator. What we're going to do is we're going to learn how to graph a polynomial function by finding the zeros and by using the leading coefficient test. So the first thing I want to do is I have my little xy axis here. First thing I want to do is find our zeros. Remember, our zeros are going to be our x-intercepts. So our zeros are when f of x equals 0. That means our output value, which is f of x, is going to equal 0. And remember, that's the same thing as, here's your y-axis. It's kind of the same thing as your f of x-axis. It's dealing with your output. So when that value is 0, we're on the x-axis. So I have -4x cubed plus 4x squared plus 15x. First thing I look to do is see what can I take out of all these. Can I factor this in any form? And I always look and they all share an x, so I'll see if I can take out an x. So when I take out an x, I'm also, if I notice that's a negative, I don't ever want to have, usually don't like dealing with my negatives in front of my leading term, so I'm going to factor out a negative x. Negative, so just make sure every sign is now going to change. All right, now for the sake of time on the video is not made on factoring. If you guys need help on how to factor this, I'll be more than happy to show. I have all the videos to show, but I'm not going to spend time right now going over the factoring. This is something you guys can figure out. Use the diamond method. Do whatever kind of method you need to. But I can factor this further. 0 equals a negative x, and I previously did it, so it ended up being 2x minus 5. 2x minus 5 times 2x plus 3. So now that I have my factors looking like this, the next thing I'm going to want to do is I need to find exactly what the zeros are. So here's the list of the factors. I need to write them as zeros. So I say 0 equals negative x, 0 equals 2x minus 5, and 0 equals 2x plus 3. So when I solve, add an x equals 0, add 5, divide by 2, x equals a 5/2, and here I'm going to subtract by 3, then I'll divide by 2, and what I end up getting is x equals a negative 3/2. So for those of you decimal people, what we have is now I have these 3 points. So what I need to do is I want to graph these 3 points. So I go back over my table and I just do 1, 2, 3, 4, 1, 2, 3, 4. So I go 0, that's one x-intercept. The next one was 2.5, right here. And the third one is a negative 1.5, right there. Now, another thing you guys should know is these are all the multiplicity of 1. Each one of these had an exponent of 1. So they're at an odd multiplicity, and they're going to be a multiplicity of 1. One thing we need to remember about that is when they have an odd multiplicity, then we know that's going to cross the axis at the intercepts. If they were even, then we know they'd actually only touch at these points. But fortunately for us, we know that they're going to be odd, so they're going to cross at each one of those points. The next thing I need to look at is I need to look at our leading coefficient, or the leading coefficient test. And what you guys see is that is negative 4x cubed. And when you're looking at negative 4x cubed, the first thing we do is we look at if it's odd or even. Since it's odd, we know it's either gonna fall and it's gonna rise. Because even functions both fall or both rise. Odd functions rise and fall. And then the next thing I need to determine is if it's going to be if my a, the number in front of my term, is positive or negative. If it's negative, we rise left, fall right. If it's positive, you fall left, rise right. So this is all, like I said, all on my all the videos you guys can see for as far as how to apply the leading coefficient test. So I know that this is a negative, so therefore my final end behavior, my graph is going to go down like that, and it's going to fall to the right. I don't know what's going to happen in between here, but I know it's going to be fall to the right and rise to the left. So the last thing we need to do, we're going to do a little table of points. All right, we have some points. We have 0, 0. We have negative 1.5, 0, and we have 2.5, 0. Well, one thing you guys need to remember is the intermediate value theorem says that between any 2 points we're going to be able to find a third point. So there always exists another point between these 2 points. So we know there's a point that's between these 2 intercepts, and we know there's a point between these 2 intercepts. It's always good thinking to always check your work and always do a point outside of your last point and outside of this point, which would have been like a negative 2, and for here would be 1, 2, 3. For time purposes, I'm not going to evaluate them. Actually, I think I might have already. Actually, I did. But it's really important to make sure you find the values between your 2 intercepts. So to do that, you need to evaluate for a point, and just pick a point. Well, it's pretty easy to do negative 1 and 1. So you do f of negative 1, which equals negative 4 times negative 1 cubed plus 4 times negative 1 squared plus 15 times negative 1. And when you do the math, you get negative 1 cubed is a negative 1 times 4 is going to be a positive 4. And, plus negative 1 squared is a positive 1, plus 4 is 4. And plus negative 15. And therefore you get a negative 7. So negative 1 equals a negative 7. And for f of 1, you do the exact same thing, but these are all going to be positives. So what you actually end up getting is, I'll just write it out. All right, and I end up getting, when I do my math, I get 1 comma 15. So therefore I go over negative 1 and I go down 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, it's going to be something really high there. So to graph, my graph has to go through these 3 points. And then you can see, and this is at 1 comma 15. And this is at negative 1, 7. Okay, my apologies for not really having the most perfect graph. But you guys can see, all you really need to do to graph something like that, to graph a polynomial function, is find the zeros, understand the leading coefficient test, determine the end behavior, and then just find, your extra points, and you can easily plot the graph. Okay? And that's pretty much what you guys need to do. On this problem, it says find the zeros of the function. So again, when we're looking at finding the zeros, we know that we need to figure out what are the values of x when f of x equals 0. So again, we plug in 0 in for f of x, and we're going to have to determine what our values of x are. Well, it used to be pretty easy to find the values of x because we had 1x, and all we had to do was just solve for that 1x. Isolate the variable, get everything on the other side, and solve for x. Here we have a lot of stuff going on. We have x cubed, a negative 4x squared, and a negative 9x. So we have a lot of x's. And we can't use our regular factoring because that was always when we're dealing with a trinomial, when it has 3 terms, or a quadratic. We were always so used to doing, your factoring, setting it up as far as 2 linear factors. So now we need a different kind of factoring method. Well, the factoring method we're going to want to use, and always you should look at this whenever you see 4 terms, you should always look into factoring by grouping. So what you really just want to do is just kind of take 2 different terms and see if you can bring them together and if we can factor something similar out of them. So in this problem, I'm just going to look at these first 2 terms and I'll say, all right, is there something that these 2 have in common? You can say, yes, I can take out an x squared out of here. So if I factor out an x squared, I'll be left with x minus 4. And then here are these 2 terms. If I took out a negative 9, or factor out a negative 9, I'll be left with x minus 4. Which again gives me to what I want when I'm looking into factoring by grouping. Because now, if you look at these are just, treat these just as another term. I know they're a binomial, they have 2 terms within them, but just treat these just like a regular, variable. You can now, both of these terms, this and this, both share an x minus 4. So what I'm going to do is I'm going to factor both of those out. So if I factor out an x minus 4, I pull it out, I am left with an x squared. And if here I factor out an x minus 4, I'm left with, negative 9. Does everybody understand that? You raise your hand. Good? Thank you.
Why is it that we have 2 x minus 4s? Why did we only have 1 again? Why did we almost drop it?
What do you mean? Why does
We got rid of 1.
Because we had 2 x minus 4s, and then the next line was x minus 4. There's only 1 of them. Why is there only 1?
Okay, what I'm doing is it's like this. It's like 3x plus 3 squared, right?
Mm-hmm.
What is the what can you kind of factor out of this?
3x.
You can factor out 3x, right? So what I'm doing is I'm pretty much just kind of saying you have these 3. Actually, yeah. So what I'm doing is I'm taking a 3 out of both of them, right?
Yeah.
And I'm taking an x out of both of them. So you're left with, so what's left? Well, that's a 1 plus x, correct?
Mm-hmm.
Well, that's the exact same thing I'm doing here. These both share an x minus 4. Just treat it like it's another variable. So I'm taking an x minus 4 out of both of them. So therefore, that's why I only have, when I take an x minus 4 out of both of them, I'm just left with an x minus 4.
Okay.
So then what's left over? Well, that's left over, and that's left over. So that's why I write that in its own parentheses, x squared minus 9. Does that make any more sense?
Yeah, like, but when, I was just curious because when we did the work, it was almost kind of like we were dropping like one of the ones in parentheses. So I was just confused about
Yeah, you're not dropping it. What you're doing is you're actually factoring it out.
Yeah.
You're taking these two x minus 4s and you're factoring out. You're pulling it out, and then whatever's left for. I mean, it's the same thing if. Yeah, well, I'm trying to think of a different example of your 3s, but if you just remember that, if you look at these, what do these two share? They both share an x squared. So you factored out the x squared. What do these two? What does this term and this term share? They both have an x minus 4. So you can take that x minus 4 out. And when you take that x minus 4 out, the only thing left is that x squared and that negative 9. So that's why we write a new equation. Then we just have to finish this off by saying, remember, 0 equals x minus 4 or x squared plus 9. So therefore, we say either x minus 4 equals 0 or x squared minus 9 equals 0. Therefore, when solving for x equals 4 or x squared equals 9. Make sure now we have to take the square root. Whenever you're taking the square root, remember we have a positive and a negative, so x equals plus or minus 3. So therefore, the zeros for this equation, or this function, I'm sorry, is going to be when x equals 4 or when x equals plus or minus 3. And like I said, if you want to check your work, you can plug any one of those numbers up there, and one of those might be zeros. We'll learn how to check that a little bit later as well. But those are all possible zeros for your function.
So the last one here states, ladies and gentlemen, we have x squared, x to the 5th minus 5x cubed plus 4x equals 0. So what we did last class was I showed you guys some factoring techniques. The first important thing, guys, is we always want to see, can we factor out a GCF? Can we factor out a common factor? And you look at all these and you say, yeah, they share something. What do they share, though? Does anybody want to raise their hand? Yes? They share an x. So we factor out an x. So if I factor out an x, I'm left with x to the 4th minus 5x squared plus 4 equals 0. Right? So again, ladies and gentlemen, you have a product equal to 0. So you can set those both equal to 0 by using the zero product property. So you have x equals 0 and x to the 4th minus 5x squared plus 4 equals 0. Well, ladies and gentlemen, this is still something that needs to factor. We can't solve for x like this. So what I told you guys to do is when you have a polynomial to a higher power, notice I can't factor anything else out, right? So what I said was think of it as like a quadratic. If it's a trinomial, think of it like a quadratic. So if I wanted to just factor x squared minus 5x plus 4, if I was just going to factor that, I could factor, a lot of people got this one factored. The factored form of this would be, what two numbers multiply to give you 4, add to give you negative 5? Answers are x minus 4 times x minus 1. Right? So we could factor that like that. However, ladies and gentlemen, does x times x give you x to the 4th? No. So what power should I raise these to? Squared. And guess what? That works now. X squared times x squared gives you x to the 4th. Negative 4 times negative 1 gives you positive 4. Negative 4 times x squared plus negative 1 times x squared gives you negative 5x squared. Now I can apply the zero product property again. So I'd say x squared minus 4 equals 0, and x squared minus 1 equals 0. Now we just simply solve for x. So I have x squared equals 4, x squared equals 1. Square root, square root, square root, square root. Remember, whenever you introduce the square root, you have to take the positive and the negative. So my final answer is x equals 0, x equals plus or minus 2, and x equals plus or minus 1.
All right, so what we have here is a problem. And what they want us to do is they want us to find all of the zeros of this function. So, this is on page 160. This is number 21. All right. So, when we're trying to find the zeros, first thing that we want to do is you always want to look and see if you can factor it, right? And if I look at this, when I see 4 terms, I automatically think factor by grouping. So when I'm showing you guys how to do this problem, first thing you want to do is factor by grouping. You can't factor this by grouping. There's no way you can group these to factor out any number. So factoring is not going to work. I can't complete the square because it's not a trinomial. I can't use quadratic formula because it's not a trinomial. And so I'm kind of stuck right now. So one thing you could do is we gotta always graph it. But right now, I don't have a graphing calculator. So I'm going to show you what you want to do or what way to solve this without a graphing utility. So the next thing that we learned is there's a rational zero test. And what the rational zero test tells us is all of my rational zeros, remember all my rational numbers, 3, 5, -7, 1/2, 3/5, any number that can be put in as a fraction, all the possible rational zeros, so we write possible rational zeros, are what we label as P over Q, where my coefficient is Q and my constant term is P. So this is the factors of P and Q. So I look at what are all the factors of my P? Well, that's going to be plus or minus 4, plus or minus 2, and plus or minus 1, right? Then I look over here and I say, all right, what's my Q? Well, thankfully Q is pretty good because it's just going to be plus or minus 1. So therefore, all the possible rational zeros, remember we can still have imaginary, we can still have irrational, but just the possible rationals are going to be plus or minus 4, plus or minus 2, and plus or minus 1. All right? So these are all my possible numbers. Now, I don't know if any of these, none of these could work, or some of these could work. All right? So what I'm going to do is I need to test them out. So the easiest way that we can do to test these out is we can use synthetic division or evaluation. If we do synthetic division and we get a remainder of 0, we know it's a factor, right? If we do evaluation and we get 0 at our end, we know it's also a factor. So what I'm going to do is I'm going to do the easiest ones. I'm going to do 1 as a 0, and I'm going to do -1 as a 0. I don't have a graphing utility. It'd be a lot easier if I graphed this and I could see which one of those probably worked or were closer, but I don't have a graphing utility. So I'm going to use synthetic division. So I use my coefficients of each term. So 1 is for z, a -1 is for z cubed, a -2 is for z, nope, I'm sorry, I don't have a square term, do I? So that's 0, then I have -2, -4. This one's the same thing, 1, -1, 0, -2, -4. Again, the reason why I had 0 is because there's no square term. So if you don't have a square term, the coefficient is 0. So now I'm just going to do synthetic division. Drop down my 1. 1 times 1 is 1. 0. 1 times 0 is 0. 0. 1 times 0 is going to be 0. That becomes a -2. 1 times -2 is a -2, which becomes a -6. So therefore, 1 is not a 0. All right? So I can look at this and I say, all right, positive 1 is not a 0. Let's go and see if -1 is a 0. Drop down my 1. -1 times 1 is -1. -1 plus -1 is -2. -1 times 2 is +2. 0 plus 2 is 2. -1 times 2 is a -2. -2 plus -2 is a -4. -1 times -4 is a +4. -4 plus 4 is a 0. Ding, 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 ding. We got one, right? Awesome. We got it. So now we know that -1 is a 0, right? So we got one factor. Now, so I'll just write 0, -1. That means x minus x plus 1 is my factor. All right? Now the cool thing about using synthetic division is now we have a remaining polynomial, which is, let's see, it's going to be x cubed, x squared, x, and that's my constant. So my factor, or my remaining polynomial now, is x cubed minus,
Why did you move from z to x's?
there's absolutely no reason why I moved from z to x's.
Okay.
It's just being very used to always using x's. So my
Is it the
apologies.
same thing?
It is the exact same thing, but the problem is talking with z's. So we obviously should be using z's, right? Thank you. So therefore I have z cubed minus 2z squared plus z plus 2z minus 4. All right? So now we need some way how to factor this, right? Here's our remaining factor. So our one factor was x plus 1, and our other factor is this. If you were to multiply these two, why am I getting x? God, stop it. If I were to multiply these two factors, I would get my original polynomial, okay? So I need to see, can I factor this out more? If I knew what another factor was, I would use synthetic division again. I don't know what another factor is. I could try these out again and see if they worked, but I notice I can actually factor this by grouping. I have 4 terms, and what I can do is I can group my first 2 terms, and I can group my last 2 terms. I have a double plus sign. And what happens here is, when I can group these, I can pull out a z squared here, and I'll be left with a z minus 2. And here I can pull out a 2, and I'm left with a z minus 2. Then I look at my polynomial, and I notice again they both share a z minus 2. So now I can factor out a z minus 2. And when I factor out a z minus 2, I'm left with a z squared plus 2. All right? So therefore now, ladies and gentlemen, my 3 factors are z plus 1, z minus 2, and z squared plus 2. So I have 3 factors. But the original problem tells me to find what the zeros are. Well, I know the one zero was negative 1, right? So to find my other zeros, let's get rid of my synthetic division. To find my other zeros, I got to set these equal to 0. So I say z minus 2 equals 0, and z squared plus 2 equals 0. Add 2. Z equals 2. And then here, I got to subtract 2. Z squared equals negative 2, square root. Z equals square root of 2i. So this is a imaginary root, right? Yeah. It's there though. It's allowed. It's possible. It's an imaginary root. 2 was our possible. So therefore our final zeros, and I'm sorry, that's plus or minus, right? Because a lot of you got those wrong. Yes?
I got that too, but then I looked in the back and it's saying that only negative 1 and 2 are zeros.
We're going to get through, I'm looking at there. So when I look at this, and what they have actually in the book is they're just asking for what the real zeros were. That's why. It didn't ask for what the imaginary were. So therefore my final zeros are negative 1 and 2. All right? And plus or minus square root of 2i. But yes, you're correct. In the book, they just said what were the real zeros, so therefore you wouldn't include your 2i. But just you guys need to understand that this still does exist. This still is another factor. And is if I did include in my plus or minus plus these 2 factors, I'm allowed 4 zeros, right? So it would work. Okay? So that is how you find the zeros using the rational zero test. So I'll just go over this one just to help you guys out. It just says find the zeros and then determine multiplicity. To find the zeros, of course, the first thing we're going to do is set our function to 0. Therefore, we have t to the 5th minus 6t cubed plus 9t. Then the next thing we're going to do is we're going to determine our GCF. Well, we can see that each one of these terms shares a t, so I'll factor out a t. Thank you. So I have t to the factor out of t times t to the fourth minus t squared plus 9. Now, oh, I'm sorry, that's a 60, right? 60 squared. All right, so now I need to factor this. Well, I gave you that worksheet. Remember on perfect square trinomials? A squared minus 2 times, or a squared, or plus or minus 2ab plus b squared. Well, notice, ladies and gentlemen, t to this fourth is a squared term, 9 is a squared term, and the negative 6t squared is 2 times a times t, or a times b, so therefore I can factor this as 0 equals t times t squared minus 3 times t squared minus 3. Now again, yes, that's the factored form. If you guys can do the x if you want to do the x, and you can convert this to t squared if you want to. But now we have t squared minus 3 times t squared minus 3, so we have 0 equals t times t squared minus 3 squared. Right? All right, so if we are going to determine, let's go and first find the 0, so I apply 0 product property. T equals 0, and t squared minus 3 squared equals 0. So now, in this case, I solve. Well, I already solved t equals 0, so that's easy. Here, I'm going to have to apply my inverse operations, so I'll take the square root of both sides. Then I'm left with t squared minus 3 equals, square root of 0 is just 0. Then I add 3. T squared equals a positive 3. Take the square root, take the square root. T equals plus or minus the square root of 3. Now, those are two different zeros, right? Let's look again at the multiplicity of their factor. The multiplicity of their factor is a what? 2. So you could say that these two, I'm not going to write multiplicity, I'll say m. Multiplicity of here is 2, or even here we have a multiplicity that was 1, right? Because remember, t can be written as t minus 0, right? So therefore this multiplicity is equal to 1. So therefore the graph crosses at t equals 0 and then touches at plus or minus the square root of 3.
So in this example, though, if we're going to follow, now the one difference here, notice how we had 2 terms over here, 3 terms, and 4 terms. So the important thing to remember is when, like, for each term, they're all going to have a certain factoring technique or factoring, certain technique. So when we have 4 terms, we want to look into factoring by grouping. So what that means, Jacques, is you're going to take, first thing first is we're going to set it equal to 0, just like we did before. We want to get this to factored form. But we can't use the same technique we did for trinomials because it's not a trinomial, right? It's a polynomial with 4 terms. So what we can do is group the first 2 terms, group the second 2 terms. Then from those grouping, we're going to factor out the GCF, or the greatest common factor. So if I say, what do these two have in common? You could say an x squared. Now, when doing factoring by grouping, what we want to do is inside the parentheses, what's left over, we want to be the same. So over here, I have a negative x minus 3. I want that to be a positive x plus 3. Yes? Okay. So you'd want to factor out a negative 1. OK, now we have 2 expressions, and we want to see what they have in common. I used color code to make it very obvious, because you can see that these 2 expressions have what in common? X plus 3. It's an expression. It's not a term anymore. It's it's actual expression. But now we can factor that out, and we're left with an x squared minus 1. So then again, though, we need to factor this down, right? So we'd get 0 equals x plus 3 times x minus 1 times x plus 1. Therefore, now we can see that the solution set is negative 3, positive 1, and negative 1. Notice that the multiplicity is odd for all of those. So they all have an odd multiplicity. And remember, odd multiplicity will say that the graph will cross at each one of those, right? So by putting it into this factored form, though, if you guys see this, by putting it into this factored form, wouldn't you guys agree? You guys could graph this equation. If I said, hey, graph this, you guys could easily factor it and then use the end behavior and the zeros and multiplicity to graph, right? Kind of. All right, good. All right, so Josh is ready to go and get this started. Now, as I spoke to you guys as far as doing these problems, it's very important. It's very helpful. You will have graphing technology on there. I asked you guys to do the rational zero test, again, just as a practice, because this is important. If you guys do your product of your factors, which are going to be plus or minus 20, comma, plus or minus 10, comma, plus or minus 5, comma, plus or minus 4, comma, plus or minus 2, comma, plus or minus 1. And that's all over really plus or minus 1. So if I have a real 0, right, a real rational 0, not irrational, not complex, a real rational 0, it's going to be one of these numbers. Now when I graph it, I notice that I do have a rational 0, which ended up being 5. So what I can do with that is if I know if I have a 0, then I can apply division, and the quotient is also going to provide me with another factor. So I do synthetic division, because I'd prefer doing synthetic division than long division. And I'll just kind of work through this a little bit quicker. OK, so I get my remainder, constant, linear, quadratic. So therefore, if 5 is a 0, that means x minus 5 is my factor. And then this is my other factor, which is x squared plus 4. And then remember, that times that, this times this gives me my original polynomial, just like 3 times 2 gives me 6. However, the question is asking AJ to find all the zeros. So that means I need to set my factors equal to 0. We already know x is equal to 5. Here, this is even easier. You don't even have to factor this one, right? That's nice. Thank you, Mr. Well. That's a good problem. So therefore, but now you need to use the square root method, which is, again, was something that we talked about in our focus lessons. Subtract 4 on both sides. X squared equals negative 4. And then to undo the squaring, you have to take the square roots. And you have to remember, whenever you introduce the square root, you have to include plus or minus 2i. Always include plus or minus. And that's very important. Because if you didn't do that, Junho, if you just did the positive, then how many zeros would you have? You'd have 2i and 5. And how many zeros are we supposed to have? 3, right? So that's why that plus or minus is so, so important to make sure you guys remember whenever you introduce the square root, you have to include that plus or minus. So I also want you guys to recognize that these 2i, these come together. These are what we call conjugate pairs. So whenever you have a positive I, you're going to have the negative I. Just like the square root. If you have a square root of 5 or a square root of 5, you're going to have a negative square root of 5. So in the, I'm going to move on to the middle examples for you, just because I want to look at these. So let's go and take a look at y equals negative x minus 1 times x plus 2 times x minus 3. OK? So again, guys, notice if I want to find the x and the y-intercepts, the x-intercept is when y is equal to 0. So x-intercept, y equals 0. The cool thing about this is that's the same thing for functions. It doesn't matter what function I am talking about, going back to last chapter. The x-intercept is the x values when y is equal to 0. So I basically just replace y with 0, and I can go ahead and solve. So I have negative times x minus 1 times x plus 2 times x minus 3. And the cool thing about this is I just have 0. So if I want to find the x-intercept when a product is equal to 0, I can apply the zero product property, which basically states you have the product times all these values, set them each equal to 0. Now, does it make sense for me to set negative 1 equal to 0? No, right? We want to make sure you have a variable with that. So I'm just going to combine the negative 1 with this. So we'll see if it makes any difference or not. So I have a negative 1 times x minus 1 equals 0, x plus 2 equals 0, and x minus 3 equals 0. Can we now solve each and every one of those equations?
Yes.
Yeah, right? It's not too bad. Now here, I divide by negative 1 on both sides. So I have x minus 1 equals 0. So you could say x is equal to 1. So these are all of the x-intercepts. There's a couple different ways we can label these. We can label them just like this. We can also label them as coordinate points. And a lot of times, guys, does anybody know another name for the x-intercepts of functions sometimes, or at least the real x-intercepts? Yeah, a lot of times we're called the real zeros. So a lot of times I am going to, at least for now, I am going to interchange that the x-intercept I'll also refer to as zeros. And zeros we can write as x equals, or a lot of times you'll see them written as set notation. OK, so the zeros are, and again, I'll have the notes for the zeros. So again, to like reiterate, remembering the definition of the zeros. But the zeros, or the real x-intercepts and the zeros are really interchangeable. Now, the next thing we can do is look at the y-intercept is when x is equal to 0. So can I figure out where the graph crosses the y-axis? Sure, just plug 0 in for x. Oh, that's all we had to do, Mr. McLogan? Yes, that's all you had to do, was just plug in 0 for each variable and then solve for the other. So we have 0 minus 1 is -1. Remember that minus is like a -1, right? I'll just leave the minus up. 0 plus 2 is 2, -3. So let's do this. Negative times -1 is +1, times 2 is +2, times 3 is y equals -6. You could also write that as a coordinate point. OK, so I have my x-intercepts, and I have my y-intercepts. Cool? Yes? No? No? You guys don't like that? Sure. Basically, in this example, we're looking for the zeros. And the zeros are when f of x is equal to 0. That's what we're looking for. OK? We're looking for when f of x is equal to 0. And if you guys were to look at a graph, when f of x is equal to 0, that is on the what axis? X-axis. So basically, what we're looking for is what are the x-intercepts. All right? And I'll explain why this multiplicity and all this kind of stuff is important. So anyways, all you simply are going to do for these problems is you're going to replace f of x with 0. So we're looking for the solutions that make f of x equal to 0. Now, by applying the zero product property, what the zero product property states, if you have two expressions multiplied, two terms or two expressions multiplied equals 0, then you can set them both equal to 0. So what I'm going to do is these are what we call factors. All right? What you're going to do is you're going to take each factor and you're going to set it equal to 0. Now, why are we going to set them equal to 0? Because, ladies and gentlemen, if one of these, for one of these values is equal 0, do you guys notice how I'm multiplying one factor by the rest of them? It's going to equal 0. For instance, what if x was 7? 7 minus 7 is what? 0. 0 times all of this is going to equal 0, right? So basically, that's why you set each factor equal to 0 to find the values that make the equation true. So therefore, a 0 could be 7. You could have -1. Here, we have to undo the squaring function. So I'm going to take the square root of both sides. The square root of 0 is just 0. Yep. Right. What makes it true? Makes the equation true. So our solutions that make this equation true is 2, -1, or 7. Meaning if I plug in one of those three numbers into this equation, it's going to make the equation true, which we call the zeros, OK? Which we also call the x-intercepts. Because when you look on a graph, these numbers represent the x-intercepts. And let's actually plot them, because I'm going to show you guys something. That's -1, 1, 2, 3, 4, 5, 6, 7. And this is 2. Do you guys agree with me? Now, the next thing is we need to talk about multiplicity. What multiplicity does is multiplicity goes back to your factored form, and it says, what was the power of your factors? Well, if you don't have a power, you know that power is going to be 1. Here, my multiplicity was 2. So we're just going to say even. Multiplicity is even. We really only care if it's even or odd. Multiplicity is odd. Multiplicity is odd. OK? That's basically all I'm asking you guys to do. Okay, what I want to do is talk to you a little bit about the remainder theorem, because it's really important for you to understand what the remainder theorem states. And what the remainder theorem says is if f of x, which I have an example here, is divided by x minus k, which would be a factor, right? If it is divided by a factor, then the remainder r is equal to f of k. So what I mean by all of that is, let's say I divide this into this. So to use synthetic division, I'll do 5, 7, and negative 24. So if I divide this into it, what I get is drop down 5, negative 15. That becomes a negative 8, 24, 0. All right, so my resulting factor would be 5x minus 8, right? But you notice the remainder is 0 right here, right? What the remainder theorem tells us, which is so cool, is I can also determine that this is a factor of this by evaluating the 0. So what I can do is I could say f of k. K in this case is negative 3. So I could say f of negative 3 is equal to 5 times negative 3 squared plus 7 times negative 3 minus 24. So the same thing, if you take your factor, divide it, and you get a remainder 0, if I evaluate for that same 0, guess what? I'm going to, by the remainder theorem, I'm also going to get 0. So let's take a look. Negative 3 squared is 9. 9 times 5 is 45. Minus 3 times, well, you don't know it's minus yet, but negative 3 times 7 is negative 21 minus 24. And guess what, ladies and gentlemen? Of course, by the remainder theorem, it works. Now, this can work for any sort of number. We can even, if I change this, all right, so this evenly divides into it because the remainder is 0. So why is that so important? Well, if you wanted to know if a 0 works, right, or if a factor evenly divides into a polynomial, rather than always having to divide, you can also check your answer by evaluating that 0 by plugging it into the function. So let's take a look. Let's say I also wanted to, well, we actually already know what the other factor is, f of x minus 8. But let's try one more example, all right, and see if that works. So let me get my eraser here. Let's pretend that I want to see x minus 2. Let's see if that works. So let's see, first of all, if we get the same answer. So now my k is positive 2. And I have 5, 7, negative 24. Bring down the 5. 5 times 2 is 10, 17. 17 times 2 is going to be 34, 32. Now let's evaluate. So let's evaluate for my 0, which is f of 2. So I get 5 times 2 squared plus 7 times 2 minus 24. Well, 5 times 2, I do that. 5 times 2 is 10, 17, 34, 32. Here I get 2 squared, plugging it in. Yep. Oh, no, yeah. So 2 squared is 4. 4 times 5 is 20. Plus 7 plus 2 is 14. Minus, that's right, it was negative 24. I was wondering, I'm like, where'd the 2? It's negative 24. So negative 24, that's 10. I was wondering, I'm like, what's going on here? So therefore, it's not, it's minus 24 minus 24. I'm like, the answer just doesn't make sense. So 20 plus 14 is 34. Minus 24 is 10. And again, ladies and gentlemen, you notice that my 0, when divided to get my remainder, and then if I evaluate it, I get that same number. That number is also your remainder. So if you want to evaluate functions, whatever that number when you evaluate, that's the remainder of the polynomial. That's why it's so cool. Thanks again for watching. So I want you guys to understand. So basically what this question is asking is x minus 3 a factor of that polynomial, right? So we have to kind of understand, again, breaking this down into stuff we understand. Is 3 a factor of 6? Yes, because it divides into it 2 times, right? So therefore, is 2 a factor of 6? Yes. So therefore, we need to understand, they're basically asking, is x minus 3 a factor? So does x minus 3 evenly divide into that? Well, you could use long division. You could do synthetic division. and test to see if it evenly divides. If it evenly divides, you'll have a remainder of 0, right? However, it's saying using the factor theorem. So they're not asking for division. However, you could do the problem using division. If you remember in our notes, if you guys remember, we did something like this. Remember we plugged in zeros? So if this is a factor, if we're going to call this factor x minus 3 a factor, then we could set it equal to 0. And we could find the 0, which is 3. Right? You guys remember doing that? And remember, we plugged in. So let's call this f of x. So if we plug 3 in for x of this function, if we get 0, then the remainder theorem said x equals 3 is a 0. That's what the remainder theorem was. Remainder theorem. Which is the same thing as like division. Remember, we kind of checked our answer by dividing. So if you plug in a number and you get 0, that means x equals 3 is a 0. If you get 0, then x minus 3 is a factor. That is the factor theorem. And you guys agree with me that x minus 3 and x equals 3 are related to each other, right? X minus 3 is the factor. X equals 3 is the 0, right? So let's just check. F of 3 equals 3 cubed minus 3 squared minus 3, minus 3, minus 15. So we have 27 minus 9 minus 3 minus 15. So that gives me positive 18. That gives me negative 18. So therefore, that gives me 0. So therefore, you don't need to do long division. You could. Or you don't need to do synthetic division. You could. But we can just prove here now that, via the factor theorem, that x minus 3 is a factor. So the next problem, or over here, is what I'm going to use is what we call the factor theorem. And what we can say is, if I can do f of, let's just call z as in 0, and I get 0, that means x minus z is a factor. So if I can plug in a value and I get 0 as the remainder, or 0 as the value, what that does is that tells me that that's a factor. Kind of very similar to the remainder theorem. If you plug in a number and you get 0, then that tells you that number is a 0, correct? That's what we proved over there. And it's easy to compare between zeros and factors, because we've been doing this for a very long time. Factors, zeros. Zeros, factors. Remember on your last quiz, I gave you zeros and I said write the equation? What do we have to do? We had to take our zeros, write them as factors, and then we could multiply them, right? In solving, we take a polynomial, we factor it out so we have factors, and then we apply the zero product property to find the zeros. So zeros and factors are very closely correlated. So the remainder theorem and the factor theorem are very closely correlated. Basically what it's saying is, if you plug in a value and you get 0, that value is the 0, which is the remainder theorem. And the factor theorem is, if you write that 0 as a factor, then it's a factor, as long as it equals 0. So if we're asking, if I'm saying my factor is x minus 1, then my 0 is x equals 1. So what this is saying is, if I plug in 1 into my function and I get 0, then this is a factor. So all we need to do for this is plug in f of 1. So I get 2 minus 3 plus 4 minus 1. And my answer is 2, right? No. Negative 3, 1, yep. So therefore, it is not a factor. And what I just want to show you guys is, if you have a 0, right? And let's say you're trying some things, and you want to know, rather than doing a lot of synthetic division, what the remainder theorem tells us is, if you have a 0, so let's say x minus k, that is our factor. that means x equals k. And I think I wrote this on your piece of paper. If that is your factor, then x equals k is your 0. Did I write that down on your guys' piece of paper? Yes, I wrote that down, right? You guys see it on your piece of paper? Yes? OK. So I said that 3 is a 0. What the factored form, what the factor theorem tells you is if you do f of 3 is equal to 0, then 3 is a 0 of the polynomial. So let's go ahead and try it. Let's go ahead and do, oh, this should have been a function. Or let's rewrite this as a function, f of x. So let's do f of 3 equals 5 times 3 cubed minus 12 times 3 squared minus 23 times 3 plus 42. 3 cubed is going to be 27. 27 times 5 is 135. 9 times negative 12 is going to be negative 118. 3 times 23, 23, 46, 69. Let me just double check my math is correct. 135 minus 118 minus 69 plus 42. Dang it. What did I do wrong? It's 108. You're right, 90 plus 18, 108. That's right. OK. So anyways, guys, if you guys plug that into your calculator, f of 3 equals 0. So what I want you guys to see about this is when you plug in the value of your 0, when you plug it into your function and you get 0, then 3 is a 0. And if you know that 3 is a 0, x minus 3 is a factor. Does that make sense? Yes? So whenever we're going to be talking about using the remainder theorem and so forth, basically what you guys need to do is plug in the values to see what the remainder is. And also, let's just pretend f of 4 is equal to 7. Whatever, I'm just going to make something up. What I'm trying to tell you is if you were to use 4 here, guess what your remainder would have been? 7. So the remainder theorem basically tells you if you plug in a number to check to see if it's a 0, if you get 0, then that number was a 0. If you get like the number 7, that means your remainder, if you would have done division, would have been 7. Does that make sense? OK. So that's how the remainder and factor theorem work. For this problem, the directions for this problem say use synthetic division to find each function value. Verify your answer using another method. So ladies and gentlemen, we have a function. They say apply synthetic division. They say g of 3. So you might be thinking to yourself, OK, g of 3. Well, that means I could plug in g of 3. Because remember, there's 2 different ways we could determine if it was a 0. We could apply synthetic division. And by applying synthetic division, if we got a remainder of 0, we knew that our 0 of our polynomial was a 0. And then we could use the remainder theorem. And remember what the remainder theorem is plugging in your 0 that you're trying to solve. So I'd have 3 to the 6th power minus 4 times 3 to the 4th power plus 3 times 3 squared plus 2. All right, can I borrow your calculator? Because I do not know what 3 to the 6th power is off the top of my head. OK, so 3 raised to the 6th power equals 729 minus 4. I'm sorry? OK. Let me just write it just to make sure you guys are, we're all on the same page. Does everybody follow me? OK. So now you just go and simplify the rest of that. So you do 729 and you get 434. right? So therefore, is 3 a 0 of this polynomial? No, guys, this answer has to be 0. If you get this answer to be 0, then you know it's a remainder. So now the next thing is it says use synthetic division. So I should have seen everybody apply synthetic division. So when we apply synthetic division, notice we're missing, right? Remember synthetic division, guys, you have to make sure it's in descending order. And I saw a lot of students. Look at all the zeros. Look at all my missing terms. When you're applying synthetic division, you can't forget those zeros. So I apply synthetic division by taking my coefficients. So I have 1, 0, -4, 0, 3, 0, 2. All right? And this is how we use two different methods. We apply the remainder theorem, which is plugging in your suspected 0 into your function to determine what the remainder is, and then also using synthetic division. So I bring down the 1. 1 times 3 is 3. 0 plus 3 is 3. 3 times 3 is 9. That becomes a 5. 5 times 3 is 15. 15 times 3 is 45. 3 plus 45 is 48. 48 times 3 is going to be 96. So it would be, sorry? 96 plus 48 would be 144. 3 times 48, 96. Then 144 times 3 is going to be 288. And 288, so it'd be 3 or 432, right, obviously. And then bring that up as 434. Now, obviously, you guys can look at this and say, oh, well, obviously, this is not a 0 of this polynomial because you have a remainder. But what is the important thing, Jessica, for you to understand is when you do synthetic division and you get a remainder, that is the exact same number as when you take that 0 and plug it into the function. OK? So that's how we can verify by using two different methods. You can plug it into the function, or you can apply synthetic division. Either way, the remainder is going to be exactly the same as the value. So if you get something wrong, if you don't get the same number, you either did something wrong here or you did something wrong there. All right? So make sure you go back and try to be very, very clear on what exactly process that you use for each one of those. All right. So x minus 1, basically what we're asking is, let's go ahead and evaluate. We need to determine, is this a factor of this polynomial? So if you remember, there's two things that we talked about. Remember when we evaluated for a number, let's say c? If we plugged in f of c and we got 0, then what that tells us is x equals c is a 0. That was what we called the remainder theorem. The remainder theorem says if you plug in a number in for the function and you get 0, that tells you that that is a 0. But remember how zeros and factors are related? If I plug in f of c and I get 0, then if here's your 0, what would the factor be? X minus 0 equals 0, right? Subtract the c. So x minus c is a factor. So this is the remainder theorem. Basically says if you plug in a value and you get 0, then that value is a 0 of the function. If you plug in that same value, you get 0, then if that's the 0, then that means that's the factor. So up here, this is a what? What is this? This is a divisor, which would be written as expression, so it'd be a factor. And what we basically want to be able to identify is we want to plug in the 0. So if x minus 1 is our factor, then what is our 0? X equals 1 is our 0. So we want to test our 0. So what we're going to do, we'll just call this f of x. And we're going to say f of 1 equals 1 cubed minus 1 squared plus 1 minus 1. And what we get is 0. So by the remainder theorem, x equals 1 is a 0. And by the factor theorem, x minus 1 is a factor. So you can just say yes, because the question was, is it a factor? And that's all it was asking. So in this problem, what we have is x squared minus 3x plus 2 divided by x minus 1. So the purpose of this is obviously we already know the answer, but I want to make sure you guys know how to set it up, because I'm going to give you guys 2 more difficult problems, which are ones that you're going to see. So the first thing we always want to do when we're doing synthetic division, in long division, we divided by the factor. In synthetic division, we're going to divide by the 0. In synthetic division, we wrote what the whole dividend was. In long division, we wrote the whole dividend. In synthetic division, we're just going to write the coefficients of the dividend. So here's our divisor. Here's our dividend. OK? So remember what I said. Long division, you have to do it when x is squared, right, or third, or whatever else, when your divisor. Is our divisor linear in this case? Yes. So we can find the 0. So to find the 0, all I simply need to do is take my factor and set it equal to 0, x equals 1. So what I do is I just write 1 on the outside of that. And then I go ahead and take the coefficients of my dividend. Now make sure that your coefficients are your dividend is in descending form, descending order. And also make sure if you have any missing terms, which we'll do a problem of, make sure you replace that with 0. So like, for instance, if I went to x squared to 2 and there was no 3x there, you'd have to put 0 as the coefficient. Remember, because we kind of showed you that place value over there. All right. So anyways, in this case, we have 1, -3, and 2. So synthetic division is great, but remember, we can only do synthetic division when we have a linear divisor. But the problem with synthetic division is that it is kind of cryptic. It's an easy way to divide, but we have to kind of understand what our answer looks like. So Alex, this is what we basically do. The first term is we're going to bring it all the way down, and that's your first part. So you're going to multiply on the diagonal, add on the vertical. Multiply on the diagonal, and then add on the vertical. Once you multiply on the diagonal, you add on the vertical. So you multiply on the diagonal. 1 times 1 is 1. And you add on the vertical. -3 plus 1 is -2. You multiply on the diagonal. -2 times 1 is -2. And you add on the vertical. 2 plus -2 is 0. Now, again, like I said, this is kind of cryptic. What the heck does that, right? When we did long division, it was nice because the quotient was written right up top. So we need to understand what this is. The last term is your remainder. The second last term is your constant. And then it goes to x, x squared, x cubed, x to the 4th, however many numbers we have. But it just keeps on going in succession. But that's our answer. So we can write our q of x as x minus 2, because these are the coefficients, which we already knew from doing this problem 3 times. Correct? OK?
Well, so I like this problem because what it does is it makes us remind ourselves that when applying a problem like this, we have to make sure, yeah, we know our divisor. Hopefully we remember our divisor. We set equal to 0. We solve, and we get x equals -1. But we also make sure when we're taking our dividend, what we're dividing into, we have to make sure this is in descending order. Right? And you can see, remember, descending order means we're going to have our degree first. Our largest exponent is going to go first. So I need to make sure I rearrange this. So I'm going to rearrange this as a -x cubed plus 2x squared minus 3x plus 5. And the rearranging is very important because a lot of times our negative signs or other signs might get kind of confused in with there. So if I know my 0 is -1, and therefore I'll take the coefficients of my polynomial, which would be -1, 2, -3, and 5. So now what I'm going to do, by applying the algorithm for synthetic division, I will break down my first term and bring down terms and add vertically, and then multiply diagonally. So I'll bring -1 down, -1, then -1 times -1 is going to be a +1. 2 plus 1 is going to be 3. 3 times -1 is a -3. -3 plus -3 is going to be a -6. Negative 6 times negative 1 is going to be a positive 6. 5 plus 6 is going to be 11. Now that's okay, you got a remainder. We're just practicing dividing. And really the main important thing is making sure that we put this in our descending order. I wasn't missing a term, was I? No. Okay, actually, yeah, that's fine. So therefore that's a remainder, constant, linear, quadratic. Now when writing this, I need to make sure I have this as a negative x squared plus 3x minus 6 plus my remainder over my divisor, which is x plus 1. So there you go, ladies and gentlemen. That's going to be your quotient for the division of these polynomials by synthetic division. Thanks. Okay, so here we go. I have 3x cubed minus 4x squared plus 5 divided by x minus 3/2. And I love this problem because we have a fraction. And guess what? We're still going to do the exact same things we've done the whole time. Take x minus 3/2 and set it equal to 0. Take your divisor, which we call our factor, and we're going to set it equal. When we talk about functions, we'll talk about it as being a factor. But we're going to take our divisor, set equal to 0. Remember, it has to have a degree of 1, and for it to be a binomial, for us to apply synthetic division, then I'll add 3/2. So therefore, x equals 3/2. So when I'm applying my synthetic division algorithm, I'm going to have 3/2 outside my parentheses. Now I need to make sure that I include the coefficients of every single term of my dividend. Now I notice that I have 3, 2. I don't have an x, a linear x term, so I need to make sure I include a coefficient of 0. So I'll write 3, negative 4, 0, and then 5 as my constant. Now what I'm going to do is, again, by applying the synthetic algorithm, is just drop down my 5, which is 3. Now I need to multiply 3 times 3/2. This just looks like fun, doesn't it? 3 times 3/2 is going to be 9/2. Now if I'm going to multiply negative 4, let's just do a little work so you guys can make sure you remember how to do fractions. Okay, so negative 4 plus 9/2. Well, I need to make sure I put this over, and then I need to make sure they have the same denominators. So that's really going to be negative 8 over 2 plus 8/2, 9/2, which is going to equal to 1/2. So I bring down 1/2. Then I multiply 1/2 times 3/2. Remember, when you multiply fractions, you just multiply across, which is 3 over 4. Okay, so that becomes 3 over 4. 0 plus 3 over 4 is going to become 3 over 4. Then I multiply again, so I have 3/2 times 3 over 4, which equals 9/8. Then I need to add, let's do it over here. 5 plus 9/8. So therefore I need to get the same denominator, so I'll multiply by 8 over 8. So therefore I have 40 over 8 plus 9 over 8, which equals 49 over 8. But don't worry, that's going to be your remainder, so it's okay if it's some weird fraction. So remember, we write this as remainder, constant, linear, and then quadratic. And remember, those are my coefficients of my quotient polynomial when I divide x minus 3/2 into this polynomial. So therefore I have 3x squared plus 1/2 x plus 3/4, and then plus my divisor, which would be 49 over 8 divided by x minus 3/2. Now, we don't really want to have a fraction and another fraction, so what I can do is I can just rewrite this as 8 times x minus, or 3/2, and let's distribute that. 8 times x minus 3/2. So therefore that's going to be 4 x minus 12. X minus 12. So there you go, ladies and gentlemen. That is how you find your quotient when using synthetic division with some lovely fractions. Thanks.
Welcome. So I want to do one more problem when we have our x minus k, and we need to go ahead and solve for it, and we're going to be doing some fractions. So in this case, we'll just take our divisor, 3x plus 2, and we'll set it equal to 0. So subtract 2, so we have 3x equals negative 2. Divide by 3, divide by 3. X equals a negative 2/3. So I'm going to place that on the top. or on the outside of my box. Then I'm going to take the coefficients of each term. Notice that I do not have a linear term, so we're going to use 0 for that. So I have 15, 15, positive 10, negative 6, and 0, and then a positive 14. You got to make sure we include that 0, or we're going to have some problems. So the first thing is I bring down the 15. So 15 times a negative 2/3 is going to be, let's see, 3 is going to divide into 30 10 times. So that's going to be a negative 10. Negative, so 2 times that would be negative 30. Negative 30 divided by 3 will be a negative 10. 10 plus negative 10 is 0. 0 times a negative 2/3 is going to be 0. Negative 6 plus 0 is negative 6. Negative 6 times a negative 2/3 is going to be a positive 12 over 4, which is going to be a positive 12 over 3, which will be a positive 4. 0 plus 4 is going to be 4. 4 times a negative 2/3 will be a negative 8/3. So now what we need to do is we need to convert our 14 over to a decimal. I'm sorry, not a decimal, but over to a fraction with a denominator of 3. So I'll multiply by 3 over 3. So I have 14, 28. So that's going to be 42 over 3. So 42 over 3 plus a negative 8 over 3 is going to be a negative 34, or I'm sorry, positive 34 over 3. So that's going to be our remainder, constant, linear, quadratic, cubic. So you can see now we have the coefficients for each term plus our remainder. So our quotient is 15x cubed. We don't need to write the plus 0x squared minus 6x plus 4 plus our remainder of 34 over 3 divided by 3x plus 2. But then again, to kind of get this off of our denominator, we can rewrite this as 34 over 3 times 3x plus 2. So there you go, ladies and gentlemen. That is how you solve your final, that's how you solve using synthetic division, or find the quotient. Thanks. Again, guys, if you're losing, they're asking you to basically just divide. Now, we could use long division or we could use synthetic division. I always think, though, the synthetic division is going to be your easiest whenever your divisor is linear. So again, our divisor is linear. So therefore, that's what we're going to do. So you set your divisor equal to 0, and you find your 0, which is 1. Now, in this case, you guys can see we do not have any x to the 4th, x cubed, x squared, or anything like that, right? So what you could do is rewrite this as x to the 5th plus 0x to the 4th plus 0x cubed plus 0x squared plus 0x minus 1. Because what's 0 times all of these? 0. However, when using synthetic division, we have to account for those place values. So I set up my problem with a 1. Then I have 1, 1, 2, 3, 4, 5. Now remember, the first term you always bring down. You multiply on the diagonal. 1 times 1 is 1. Then you add vertical. 0 plus 1 is 1. 1 times 1 is 1. So we have a remainder of 0. So that evenly divides. So that is your remainder. That is your constant. Constant, linear, quadratic, cubic, quartic. Well, no, it only goes up to, if there was another one, you go up to x to the 5th. I always start from the right. Remainder, constant. So therefore, my final answer is x to the 4th plus x cubed plus x squared plus x plus 1. That is your quotient for that problem. Anybody have any questions on that? No? Again, first main thing, guys, is we only want to apply synthetic division when our divisor is to 2 to the first power, right? So again, to set up this, now again, guys, when we're looking into this, we're not using long division. What we want to do is try to treat this like as the 0. So the first important thing would be to set this 1 minus x equal to 0. And therefore, we could say x is going to equal 1. That's what's going to be on the outside using my synthetic division as a 1. The next thing, though, is we need to rewrite this in descending order. And we also notice that when we rewrite this in descending order, I don't have a cubed. So what I'm going to use is use a placeholder 0x cubed minus x squared. And then I don't have an x, so I'm going to use a 0x plus 2. This wasn't important in long division. Like, you could do it or not do it. It just depends on what you were familiar with. You have to do this for synthetic division. So now we take each coefficient, 3, 0, -1, 0, and 2. OK? So bring down the 3. First one, that's the freebie, right? Everybody loves the freebie. Multiply on the diagonals, add on the verticals. 3 times 1 is 3. 0 plus 3 is 3. 3 times 1 is 3. -1 plus 3 is 2. 2 times 1 is 2. 0 plus 2 is 2. 2 times 1 is 2. 2 plus 2 is 4. OK, that's fine. So we have a remainder, right? And that's fine, because I was just asking you to divide. So it's either going to divide evenly or it's going to divide with the remainder, right? I didn't say that this was a factor. If I said this was a factor, we know that the remainder would have had to have been 0, right? But I didn't say it was a factor. I just said divide. So remember to now find out what our quotient is. Goes remainder, constant, coefficient of our linear, coefficient of our squared, coefficient of our cubic. And then we could just keep on going higher and higher. So our answer is our quotient is 3x cubed plus 3x squared plus 2x plus 2. And then remember, always take the remainder and put it over your divisor. And that would be our quotient, our, let's say our q of x. If you want to write it as a function, q of x. OK? However, I didn't just say divide. What I said was divide and check your answer using the remainder theorem. So what that means then is if I take this original function, let's just call this fx. If I plug in f of, what was my 0? F of 1, I should get 4. I should get the remainder. If I plug this 1 into my original function, I should get 4. So let's go ahead and check that out. Let's go and see if that works. I'm going to call this f of x, by the way. So if I plug in a 1, I get 3 times 1 to the 4th minus 1 cubed squared, and then plus 2. So I get 3 minus 1 plus 2, which equals 4. So therefore, I know that I didn't make a mistake using my synthetic division, that I did that correctly. Does that kind of make a little bit of sense? Más o menos? So for this problem, it says I'm given a polynomial, x cubed minus 6x squared plus 11x minus 6. So that is our polynomial. Then I'm given a factor. All right? So what do we remember? Let's go back through. What do we know again about polynomials and factors? Well, let's go back to numbers and factors. So Madison, if I said, what is a factor of 12? You could say 6, right? Well, why do you know that 6 is a factor of 12? Because the definition of a factor is you know that your factor is going to multiply by another factor to give you 12, right? So you could say, yeah, I know 6 is a factor of 12 because 6 divides into 12 2 times, right? So ladies and gentlemen, if I say x minus 3 is a factor, do we now know that x minus 3 divides into this polynomial? We might not know right now how many times it does. It's not as easy as 6 and 2 and 12. But we now know, since I said in the problem, this is a factor, then you know it divides into this. So there's 2 different ways we can divide, long division or synthetic division, right? And what we learned is as long as we have our factor is a linear factor, then we can apply synthetic division. So we can apply synthetic division. So we set 3, and then we use the coefficients. All right. Now, let's go back again. What is the question actually asking us, though? It says, if this is a factor, tell me all the other factors. So that's like saying, OK, if here's number 12, and I say 6 is a factor, tell me all the other factors, right? Or what we like to say is factor this completely. So you can say, oh, well, that's 6 times 2, 3 times 2 times 2. Now, obviously, we know that 4 is also a factor that's not included in that problem. But when I say factor a number completely, you break it down to a product of prime numbers, right? Which is 3 times 2 times 2. So when I say find all of the factors, I want you to find all of the linear factors, just like we found all of the prime numbers when you guys did this type of problem. So let's divide and see what our other factor is. So I bring down the 1. 1 times 3 is 3. Negative 6 plus 3 is negative 3. Negative 3 times positive 3 is negative 9. 11 plus negative 9 is positive 2. 3 times 2 is 6, give you 0. Since my remainder now is 0, does this now tell me I have or this divides evenly into the polynomial? Yes. So remember we say remainder, constant, linear, quadratic. So now I could say x minus 3 times x squared minus 3x plus 2. This times this equals that. Could everybody agree with now kind of the understanding of this? I said 6 is a factor, right? 6 divides into 12 2 times. 6 times 2 equals 12, right? X minus 3 divides into this polynomial. How many times? X squared minus 3x plus 2 times. So this times this gives you that, right? Same thing with numbers, now just with polynomials. But with numbers, we don't want just to say the factors. We want to find you the prime numbers. So we factor 6 again, right? We factor it further down. So can we and when we're talking about polynomials, we only want our factors as linear factors, meaning we only want them to be raised to a power of 1. So is this a linear factor? No. So we need to see, can we factor this further down? Just like I factored 6, let's see if we can factor this down. And can we break this down further? Well, that's why factoring is so important, because you guys, we need to know how can I quickly factor this? Well, hopefully you guys can see that this can be factored into x minus 1 times x minus 2. So therefore, now, is it written as a product of linear factors? Yes. And guess what? These are now all of the factors of my polynomial. And that's done. That's what you... Yeah, this is, yeah. Because it's saying, what are all the factors? So these are all your factors. Because this times this times this gives you that. And they're all linear. OK? Ladies and gentlemen, I need you to make the connection of this to this. OK? Now, again, if you guys look over there, I have x squared minus 3x plus 2 divided by x minus 1. We showed last class period that x minus 1 divides into it. You guys can see it algebraically here, but we also proved it with synthetic division and long division, that it evenly divides, right? Since it evenly divides, it's called a factor, correct? Then, from the factored form, we can set the factor equal to 0 to find the 0, correct? Now, how many times x minus 1 divides into x squared minus 3x plus 2 was x minus 2, which we also call a factor because, just like I had, 6 divided, is 3 a factor of 6? Yes, because 3 goes into 6 how many times? 2. So what is 2 also a factor? Yes. So that means the quotient of that is also a factor. So when I tell you or I give you a 0, what that means is I can divide that 0 into this because it's going to evenly divide, right? And then the answer is also going to be a factor of the polynomial, correct? Again, if you give something that's a factor and you divide it into it, the answer is also a factor, correct? So what we're going to do is we're going to use synthetic division. You could use long division, but why? Synthetic division, 3, 2, negative 19, and 6. All right, I'm not going to talk my way through it as much as I did last class period. Or go as slowly as I did last class period for synthetic division because nobody asked me for questions on their homework, so that I assume that everybody did it and didn't have any issues. So the first thing you're going to do, bring down 3. 3 times 3 is negative 9. 2 plus negative 9 is negative 7. Negative 7 times negative 3 is 21. Negative 19 plus 21 is positive 2. 2 times 3 is negative 6. Remainder 0. we know it has to, right? If it doesn't evenly divide, we know that we did something wrong because the problem says that's a 0. So we know it has to evenly divide, right? Now, this is our other factor. This is how many times this divides into that. So we have to write out what that is. OK. So remember, if that's the 0, we can write it as a factor, right? Because the factors multiply to give us this polynomial. So if here's my 0, that means x plus 3 is the factor. And then this is my other factor. This times this gives me my original answer. Again, I'll revert that to what we did last class period. 3 divides into 6 2 times. That means 3 times 2 equals 6. This divides into this, 3x squared minus 7x plus 2 times. So 3x squared minus 7x plus 2 times x plus 3 is going to give me that. Now, what's the question, though? The question is asking us to find all the zeros. We already know 1 0. We need to find the remaining zeros. That 1 0 is shown right there. We need to find the other 0. So we already know x equals -3. That's fine. So what do we need to do? We need to set this equal to 0 and solve. Now, if you guys remember the beginning of the year, we did a focus lesson all concentrated on solving quadratics. Literally, we spent about 4 weeks solving quadratics. You can solve quadratics by factoring. You can solve quadratics by the quadratic formula. You can solve quadratics by completing the square. These will all be acceptable methods to do this. But you have to make sure you guys are comfortable and can solve quadratics, because you all will be expected to factor. It's a part of this problem. That's why we spent that time practicing that. So now we have to see if this is factorable. So I break it up into 3x and x. And then I see what 2 numbers I need to multiply to give me 2, add to give me -6. So I think I got it. -2 and -1. Oh, shoot. I forgot to do something. Sorry about that. That's the factored form. If it wasn't factorable, you could have completed the square, or I would prefer using quadratic formula. But that is factorable. And therefore, I set them equal to 0. 3x minus 1 equals 0. And x minus 2 equals 0. So therefore, x equals 1/3 and x equals 2. So I have how many zeros? 3. What is my degree? 3. So I know at least I'm on the right path with that. The one thing I forgot to mention to you, which I forgot to do, was we forgot to check the rational zeros. So did everybody at least get this written down? Because what I want you guys to do on your problem, this is what I want you guys to do first. I want you guys to do the rational zero test. So the rational zero test would be the factors of 6, which are 6, 3, 2, 1, all over plus or minus the factors of 3, which are 3 and 1. So what you do, once you find the factors plus or minus of your constant over your leading coefficient, is you just write out every single possible combination. So you do 6 over 3, comma, plus or minus 6 over 1, comma, plus or minus 3 over 3, comma, plus or minus 3 over 1, comma, plus or minus 2 over 3, comma, plus or minus 2 over 1, comma, plus or minus 1 over 3, comma, plus or minus 1 over 1. Now, you guys might say, Mr. McLogan, that's a lot of work. Well, once you guys kind of get used to this, you'll start to see that a lot of these start to simplify. 6 over 1 is just 6. Then you can do plus or minus 6 over 3 is 2, comma, plus or minus, actually we have 3 over 1. Then you have 3 over 3 is 1. That was 2 as well, so that was a duplicate. And then we have, that's 1 over 1, so that's 1. That's a duplicate. Then we have plus or minus 2/3 and plus or minus 1/3. Now, these are all real zeros. These are all real numbers, real rational numbers. Yes?
You don't have to do anything in this multiple?
I mean, it's just duplicate. It's like saying 2 twice. So it's not, This is just giving you the possible rational zeros. Now let's double check. Are all of my solutions, all these rational zeros, a part of this number? It's not like I have 5 as an answer, do I? No. So is -3 in that list? Yes, -3. Is positive 1/3 a part of that list? Yes, positive 1/3. What about positive 2? Yes, right? So therefore, it's a good way to kind of double check if you did something wrong. Because if you have like 19 as an answer, obviously it's not in the rational zeros. So obviously there's something wrong with what you did. Okay? So we'll do this first on the next example. And then we'll go through the same process. What I have up here is I have 3x to the 4th plus 4x squared. How did this happen again? Jeez. 3x cubed plus 4x squared minus 5x minus 2. And what they say is we have one factor. 3x plus 1 is a factor of this polynomial. That means this number divides into that polynomial, right? So let's prove it and make sure and see how many times it divides into there. So remember, when we're doing synthetic division, we always took our factor. And I'm going to explain more why we always set it equal to 0 in a second. But we solve for x. Therefore, when using synthetic division, we're going to say we're going to use -1/3 outside of our box. So that means our synthetic division problems are going to deal with some fractions. All right. So then the next step we're going to do is make sure, and notice this is linear. It's linear and it's a binomial. So that's why I can use it for synthetic division. Then we just make sure this is in standard form, and we write our coefficients. So we have 3, 4, -5, and -2. So remember, the process goes, bring down the first number, which is 3. 3 times -1/3. Well, those are reciprocals of each other. And one's positive, one's negative. So therefore, I'm going to have a -1. So therefore, 4 plus a -1 is a positive 3. 3 times -1/3 gives you a -1. -5 plus -6 is going to be, or -1, is a -6. -6 times -1/3 is now going to give you a positive 2. -2 plus 2 gives you a 0. So was that bad? No. Okay, you guys, you see fractions, and you're like, oh, I'm just not going to do it. Yeah, it wasn't as bad. So now let's write it. So we say remainder, constant, linear, quadratic. So our formula is 3x squared plus 3x minus 6. That times this gives you our binomial. I'll say it, our polynomial. Again, I'll say this divides into this many times. Meaning this times this gives you that. Right? However, I'm asking you to find all of the factors. And so I don't want just the factors, that 2 numbers that factor. I want to find all of the linear factors. So we need to see, can we factor this even further? So let's check it out. Let's try. So what I'm going to do is I'm going to break it up into 2 binomials. Well, I know the first 2 numbers have to multiply to give me 3x. So that means that one number has to be 3x, and the other number has to be x. Now our issue comes into, now you could do the diamond, but I'm not going to work through the diamond. I'm just going to work through this a little bit quicker. Now the next thing is going through is, what 2 numbers multiply to give you -6? Well, there's a couple, right? You could do -6 and 1, -1 and 6. You could do -3 and 2, -2 and positive 3. But what we notice is when we multiply them, we need to add them up to a positive 3x. All right. So, well, let's look at 3 and 2. We know that -3 plus 2, right? That could be an option, right? Because -3 times 2 gives you a -6. So what we're going to do to check our work is we know that the first give us our first term in our trinomial, and the last give our last term in the trinomial. And when we combine the outer and the inner, that gives us our middle term. So does -3x plus 6x give us a positive 3x? Yeah. Right? Yeah, so that works. So therefore, that times that is your factor. If you have a 0, how do you prove that it's a 0? There's 2 different ways we can prove it. How do you prove it's a 0? Use synthetic division, and there's another way that we proved if it's a 0. remainder theorem, right? You can take this 0 and evaluate. You can do f of 2i. If f of 2i equals 0, then that's a remainder. Or I'm sorry, then that's a 0. The remainder theorem, we talked about it in your notes. We didn't do a lot of work with it, but you guys need to know you can evaluate it, and if you get 0, when you evaluate it, it's a 0. However, we've usually done just synthetic division because when doing synthetic division, we get the resulting factor, right? Which we kept on factoring down until we got all the linear factors. So, ladies and gentlemen, if I had 2, if I said the 0 was 2, what would you do? What would you do? You'd do synthetic division with that, right? You'd say, all right, Mr. McLogan, well, that's a 0, so that's 2. And then you do 2, -1, 7, -4, -4. Right? Well, guess what? 2 i's are 0, not 2. So we're going to do the same thing. So let's practice. 2 bring down is going to be 2. 2 times 2i is 4i. -1 plus 4i. Now, how do you multiply that times that? Well, just use, remember, this was part of your quiz. 2i times -1 is a -2i. Right? 2i times 4i is going to be 8i squared, which is -8. 7 plus -8 is going to be a -1 minus 2i. -1 times 2i is a -2i. -2i times 2i is a -2i squared. I squared is -1. -1 times -2 is +4. That just gives you -2i. -2i times -2i is going to be a -4i squared, which gives you a +4. So is this a 0? Yes, right? It divides into it. I know it's a little bit difficult, but all we're doing is now just adding and multiplying your complex numbers. Now, here's where it gets difficult. Guys, remember when we talked about square roots, right? The square root of 3. If I told you the square root of 3 was a 0, then what else did you already know was of 0? Negative square root of 3. It's the same thing with your complex numbers, right? Because remember, your complex numbers is the square root of -1. Plus or minus the square root of -1 would be your 0. So if 2i is a 0, what else do you know has to be a 0? -2i. So I do -2i. And then let's synthetically divide again. Take again these factors. 2, -1 plus 4i. -1 minus 2i. -2i. So again, we go through it again. Bring down the 2. 2 times that is -4i. -1. Gives me a +2i. -1. -1 times -2i is +2i. Is that a 0? Yes. What's my remaining result? That's my remainder, my constant, linear, quadratic. So what I have is 2x squared minus x minus 1. Now they're trying to find all the zeros though, right? So I write this out, 2x squared minus x minus 1. Now I need to factor this. So how do you factor that? Well, you got to see. Factor could only be 2x times x right there, right? Factoring practice. Let's see. Since that's going to be negative, it's going to be -1 plus 1. So now my zeros are 2i, -2i. Set these equal to 0, do 0 product property. I have 1, and I have a -1/2. So I have 4 zeros. Or I could write this as, it didn't say, it just says find the zeros, right? Not the linear factors. Yeah, find the zeros. I have 4 zeros. 2 of them are complex, or 2 of them are imaginary, 2 of them are real, right? How many possible zeros, how many zeros do I have to have? I have 4, right? So I'm good, right? So if you just did 2i and 2i, and you're like, oh, okay, I'm done. You only solved the 2, you only proved that 2 zeros. You have 4 linear factors, which is going to give you 4 complex zeros. All right, so you got to make sure you keep on going on. So just factor that through. Questions? Anything? No? Okay, just practice on this stuff. Okay. So for this one, if we have a 0, 5 plus 2i, right? What we need to do is remember, automatically, when we know 5 plus 2i, then automatically, Jacob, we know that we have what is also our other 0? 5 minus 2i, right? Automatically. 5 plus 2i, we have the conjugate 5 minus 2i.
So then the next thing what we need to look at is, yes, you can use synthetic division for this. Not a problem. Set it up. 5 plus 2i, synthetically divide. Go for it. Give it a shot. See how you do. All right? However, there's another way we can do this. And I like to do this method, especially when we have a binomial and another binomial, is let's multiply these out to get another factor that's not going to include the I, right? Because remember, what happens when we multiplied a complex number by its conjugate? We got rid of the I, right? So we have 5 plus 2i. Oh, wait, that's the 0, right? So the factor is going to be x minus 5 plus 2i, right? That's one factor. And then the other factor is going to be x minus 5 minus 2i. Correct? So if I was going to multiply these out, again, you can multiply them like this, or let's do the step that we did again. Let's rewrite this using associative property. Then, we have difference of two squares. So when I multiply this out, I have x minus 5 squared. And then 2i times a negative 2i is going to be negative 4i squared, which would be plus 4. Right? So then I have x minus 5 squared, which is going to be x squared minus 10x. And then we'll have plus 25, but plus 4 is going to give you what?
29.
Plus 29. Okay? Now, we can use this to use long division for this polynomial.
Wait, why?
Huh?
Why would you use long division?
Because now I know that this is a 0 and that's a 0, right? They both multiply to give me this, correct? Both those zeros are written as factors, multiplied to give me this polynomial. So think of it like this way. Just think of like if you had 2 and 3, like if I have factors, let's say if I have factors of 12 or 2 and 3, right? Multiply them to give me 6. I can still divide 6 into 12 to find all. Remember, we're trying to find all the zeros,
Oh, okay.
right? And remember, since this is to the third power, right? Do I have all of my zeros? No. So I still have one more I need to get. So I need to still continue to factor this down. So what I'm going to do is, I have x squared minus 10x plus 29, long division, x cubed minus 7x squared minus x plus 87. Okay, so, remember how we had to use long division again, right? X squared goes into x cubed, x times. X times x squared, x cubed. X times negative 10x is going to be a negative 10x squared. X times 29 is going to be 29x, positive 29x. So then remember, we subtract the whole row. X cubed minus x cubed, 0x cubed. Negative 7x squared minus a negative 10x squared is a positive 3x squared. Negative x minus negative 29x is going to give you a negative 30x. And then that's the rest of my multiplying things. So then I could have 87 on the bottom. So now I do x squared divided into 3x squared. Yes, it goes in there, positive 3 times. 3 times x squared is going to give you a 3 times x squared gives you 3x squared. 3 times negative 10 is a negative, 3 times negative 10x is a negative 30x. 3 times 29 is going to give you a positive 87. Subtract the rows, everything's equal to 0. So therefore my last remaining factor is x plus 3. So if this is a 0, I know, Jacob, that that's a 0, all right? Then I multiply them, use long division, and I figure out my last factor, proving that that's a 0 as well. Cool? Pretty awesome, huh? All right.
And what Descartes came up with in the rule of signs is he was able to determine that rather than dealing with the rational zeros, he was able to formulate a way for us to determine the real zeros, right? We have real and we have imaginary, right? It's either real or it's imaginary. Those are the only two that we're dealing with. So he said if you take a look at the positive real zeros, what I want you to do is take the signs of each monomial. Remember a polynomial? Remember that crazy definition I said? A to the n, x to the n, plus a to the n minus 1, x to the n minus 1, right? Dot, dot, dot. A polynomial is a sum of monomials. So if you take the sign of each one of these monomials, and let's write them out. So up here, I have 3x cubed. We know that's a positive, right? So I say positive to negative to positive to positive. That's a bad marker. And what we notice is the signs of each one of my monomials, you can see they alternate from positive to negative and then negative to positive, right? So there's 2 times that they alternate from a different sign. So therefore, the number of positive real zeros, you're going to have 2 real positive zeros or 0 real positive zeros. And somebody might say, well, wait a minute. All right, I understand getting the 2, but why is it possible also for it to be 0? Because on Descartes' rule of signs, what it states is that the number of times that you alternate from a sign, that's the number of real zeros, minus an even number. So if I take 2 and I subtract an even number, which would be 2, I would get 0. So therefore, it's either 2 or it's 0. I'll show you how we will figure this out. But there's going to be 2 possibilities. Now, to determine the negative, we have to do a little bit of mathematics. And our mathematics is, rather than dealing with f of x, we're now going to deal with f of negative x. So if you guys remember from functions, if I have f of negative x, I'm now going to plug in negative x in for my function. So this will be 3 times negative x cubed minus 10 times negative x squared plus 13 times negative x plus 10. So when doing this, any negative number raised to an odd power is going to be negative. Negative x cubed times 3 will be a negative 3x cubed. Any negative number squared is going to be positive. Positive times a negative 10 will be a negative 10x squared. This negative x times 13 is a negative 13x plus 10. Again, we drop down the signs. Negative, 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 positive. So therefore, you guys can see that we only have 1 change in signs. Right? Yes?
Wouldn't that be less than x squared?
OK. Remember when you're doing remember you have to follow the rules of the order of operations. So you square the number first, then you multiply. Right? So now when we're looking at this, so now you can see, all right, there's 1 change in signs. Therefore, there's 1 negative real 0. But if you subtract an even number, you can't. If you subtract 2 from 1, you're going to have negative 1. You can't count negative 1 real zeros, right? You can't have negative real zeros. You can have a 0 that is negative, though. So therefore, we'll have 1 real negative 0. All right, and we're going to learn in the next problem how we can determine how we're going to use this. Okay, why is this important, how we're going to use this? All right, so the first thing, remember, using the rational zeros, we have to use the rational zero test, right? We're going to take p over q, where p is all of our factors of our constant, and q is going to be all of our factors of our leading coefficient. So the first thing, we're just going to do p divided by q. That's going to equal plus or minus 3 and over plus or minus 1. All over q, which is going to be plus or minus 4, comma, plus or minus 2, comma, plus or minus 1. Right? So if we were going to write this out, I'll just write it out, all of them. We'll have plus or minus 3 over 4, comma, plus or minus 3 over 2. Actually, let's write this. Let's do it below. So we have plus or minus 3 over 4, comma, plus or minus 3 over 2, comma, plus or minus 3 over 1, comma, plus or minus 1 over 4, comma, plus or minus 1 over 2, comma, plus or minus 1 over 1. Right? OK, do we have any repeats? No, nothing else we can cancel out, right? So if we don't have graphing technology or a way to take a look at the graph, we don't really know where to start with our synthetic division or where, what zeros we can work on. However, like I said, what I asked you guys to do is if we take our calculator, and what we can use that to our advantage to graph this polynomial and take a look, what does it look like our zeros are? We can use the calculator functions to find the exact zeros. But really, if we just have an estimate, that helps us. And by graphing this, when I looked at it, it looked like I had zeros at 1 and 3, correct? It looked like that's where it was close to. So what I'm going to do is I need to verify them. And there's two ways we could verify them. We could verify the zeros either by synthetic division or the remainder theorem. I'm going to choose the synthetic division because then I'm going to get another factor that I can continually factor it out with. So the first 0, let's say we picked 1. So I think 1's probably the fastest and easiest one to always choose. And hence, ladies and gentlemen, also, if you don't have graphing technology, I always like to start with plus or minus 1 anyways with synthetic division, because usually you can kind of get through it pretty quickly. So I have -4, 15, -8, and -3. Drop down to -4. -4 times 1 is -4. 11. 11 times 1 is 11. This becomes 3. 3, 0. Doesn't work? Right? So that means 1 is a 0. Correct? Good. Now, the next thing we need to do is we need to say, all right, well, we got 1 0. However, this is a polynomial to the 3rd degree. So we're going to have some more zeros to work with. Now, you could take -4x squared plus 11x plus 3 and factor it. However, it looked like 3 was a 0 as well, so let's check that. So I'll do 3, and then I'll do -4, 15. What am I doing? You've got to take the answer. Don't want to refactor. You've got to take down here. So I have -4, 11, and 3. So I bring down the -4. -4 times 3 is a -12. Bring down -1. -1 times 3 is -3. 0. So now we have both of them. And you could say now I have my two zeros are 1, 3. And I have a remaining factor, which is a -4 times -1. So like all the rest of my factors, I can write my factor equal to 0 and solve. That's an x, I'm sorry. -4x equals 1 divided by -4. So I could say x equals -1/4. That's 1, 0. And then my other two zeros are 1 and 3. So those are going to be your zeros of the function. Make sense? Got it? Preguntas? Questions? Good? All right. Ladies and gentlemen, the first thing when doing a problem like this, what it asks us to do is it asks us to first list all the possible rational zeros. So what I'm going to do is I'm just going to list them all out. All right. Then once you guys get used to it and you understand what we're kind of doing, you can start breaking them down first of all. But remember, to find all the possible rational zeros, that's going to be the factors of P over Q. Right? So let's look at all the factors of P over Q. That's going to be plus or minus 24, plus or minus 12. That's going to be plus or minus 8, plus or minus 6, and plus or minus 4, plus or minus 2, plus or minus 1. Correct? So all the factors, every single number that divides into 24. Let's look at Q, or Q. So that's going to be plus or minus 9, plus or minus 3, and plus or minus 1. Right? So what I need to do is I need to put every single one of these numerators over each one of the denominators. This is a big problem, right? This is going to be a lot of solutions. So P over Q is plus or minus 24 over 9, comma, plus or minus 24 over 3, comma, plus or minus 24 over 1. Right. I'm gonna go and simplify them all. I'm just gonna write them all out, and then you guys will see. Oh, you don't need to write them all out. You can cut some out if you don't. Once you see duplicates, because you don't need to write in duplicates. If you have extras, then you can eliminate them. So then I have plus or minus 12 over 9, comma, plus or minus 12 over 3, comma, plus or minus 12 over 1, comma, plus or minus 8 over 9, comma, plus or minus 8 over 3, comma, plus or minus 8 over 1. Is everybody kind of finally seeing my my trend that I'm doing here? This is a lot of problems. This is a lot of them. but we'll go through them. So we have comma, plus or minus 6 over 9, comma, plus or minus 6 over 3, comma, plus or minus 6 over 1. I am running out of space, so I'm going to continue over here. Comma, plus or minus 4 over 9, comma, plus or minus 4 over 3, comma, plus or minus 4 over 1, comma, plus or minus 2 over 9, comma, plus or minus 2 over 3, comma, plus or minus 2 over 1, comma, plus or minus 1 over 9, comma, plus or minus 1 over 3, comma, plus or minus 1 over 1. All right. This one has a lot, and then there's also some duplicates in here that we don't need to keep on rewriting, right? We just all I want you to do is just tell me the possible. So when you look at this, 24 over 9, that's going to be equals plus or minus 24 over 9. 24 over 3, that's really plus or minus 8, right? Then I have plus or minus 24. Plus or minus 12 over 3, it can be, we can reduce to 3, would be 4 thirds.
Why do you reduce to 24 over 9?
Huh?
Why do you reduce to 24 over 9?
24 over 9. I could go ahead and reduce it. You're right. I'm just going to leave it right now as 12 over 9. Well, actually, never mind. We're just going to leave it as how they are. 12 divided by 3, though, we can reduce to 4. 12 over 1 can be 12. Plus or minus, these are all plus or minus. That's 8 over 9. 8 over 3. However, you guys can see I already have 8, right? So I don't need to continue that. 6 over 9 is going to be 2 thirds. And I don't have a 6 over 9. Plus or minus 6 over 9, 2 thirds, plus or minus 2, which I do not have yet, right? 2, and do I have a 6? Nope. Let me look over here. I have 4/9. Now, actually, you can see here, yeah, when I reduce this, right, that is 4 thirds, right? So I can reduce that down to 4 thirds, and you can see that these are the same. So I don't need to include this other 4 thirds, because this actually is reduced down to 4 thirds. Actually, let's write that down as, that one is, hold on. That was the same thing, wasn't it? Yeah. Sorry, you can't see it. 24 over 9 is the same thing, or no, that's 6 divided by 3 is going to be 8. That's 8 thirds, not 4 thirds. This one is 4 thirds. So what we see is here, I already have a 4 thirds when I reduce it, so I don't need to write that one. I already have a 4, so I don't need to write that. Do I already have a 2/9? No, so I could do plus or minus 2/9. Okay, do I already have a 2 thirds? Yep, I already have a 2 thirds, which was right there. That can reduce down to 2 thirds. I already have a 2. I do not have a 1/9, a 1/3, but I already have a 1. No, I don't have a 1. How do I not have a, yeah, I guess that is my only one. So I don't have plus or minus, so I have 2/9. I already have 2 thirds, I already have 2, but I do not have a plus or minus 1/9, comma, plus or minus 1/3, and plus or minus 1. It's a lot. This is probably going to be longer than anything else you even get on your test, but it's good practice to make sure you write down all the factors, all right? I'm going to leave it at that, and then I'll go through, finish the rest of the problem. So that's just doing your rational zero test. Welcome. All right, so in this case, what I'd like to do is show you how to determine all the possible positive and negative real zeros. So to do this, to find all the possible positive real zeros, what I'm going to do is take our function and just drop down the signs of each term. Therefore, that's a positive 18 x to the 5th, so I'll just have it positive, positive, negative, positive, positive, positive. So therefore, you can see now what we're going to do is look at the change of the signs from positive to negative, where we can see that we have 2 change of signs, where I go from positive, negative, and then negative to positive. So when determining how is that going to help us out, Descartes' rule of signs says that the number of change in signs between our terms is going to tell us how many possible real zeros we have for the positive minus an even number. So therefore, you can see I have 2 change in signs. So I have 2, and then minus an even number. Well, think of your even numbers, 2, 4, 6. Well, I can't subtract anything greater than 2. So it's either 2 or, I'll write or, 0, positive, real zeros. Okay? So that means on my, in this function, if I'm going to find the zeros, I could have 2 positive real zeros, or I could have 0 positive real zeros. And if it's not a positive real zero, then it has to be a negative. So the next thing we'd want to do is determine the negative real zeros. So to do that, what I need to do is evaluate for f of negative x. So now my input variable is going to be a negative x rather than a positive x. So it's going to be negative x to the 5th plus 2/3 times negative x to the 4th plus a minus a negative x cubed plus 2 times a negative x squared plus 2 times a negative x plus 3. Okay? So now what we need to do is evaluate for our negative x. And just remember, whenever we have a negative value raised to an odd power, that exponent is still going to remain negative. And if we have a negative number raised to an even power, it's now going to become an even exponent. So this now turns into a negative because I'm multiplying the negative x to an odd power. So now this whole term will be negative. So now that's 18, negative 18, x to the 5th. Since that's to the even, that's just going to remain positive. This now turns into a negative, but a negative times a negative is now going to turn to a positive. This remains positive. That's going to remain negative. So now, again, we drop down the signs. So I'll have, well, let's drop them down with a different color, right? So now I have negative, positive, 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 negative, positive. So now when looking at our change in signs, what we can do is we can see, well, we have 1 change of signs, 2, 3. So again, going by our rule, that was my microphone. Sorry about that. So by going by our rule of the change in signs, you can see now I have 3 possible, 3 real zeros, or minus an even number. Well, again, I can subtract 2, but I cannot subtract 4 because you can't have negative number of zeros. So I could have 3, or by subtracting 2, I have 1. So 3 or 1 negative real zeros. Okay. So there you go, ladies and gentlemen. That is how you use Descartes' rule of signs to determine all your positive and negative real zeros. Thanks. So the last test we're going to have, so we have this polynomial. And I want to show you a couple things before we actually get to our problem. All right? So we talked about the rational zero test, and I said there's one more test that we can learn about. The other test is what we call Descartes' rule of signs. Okay, so Descartes' rule of signs. And what Descartes' rule of signs says is it doesn't tell you what the possible zeros are. All right? All it says is it helps tell you how many zeros you have. But it's not going to be just talking about rational. It's only going to be dealing with real. Okay? And it's going to be dealing with positive and negative. So we can use the rational zero test to tell us how many rational numbers we have. And we can talk about Descartes' rule of signs to tell us how many positive and negative real zeros we have. So Descartes' rule of signs, rather than kind of writing up the long description, what we're going to say is the number of positive real zeros, all right? So the number of positive real zeros is going to be the equal to the number of sign changes of your polynomial in standard form. So the number of sign changes and then down as a factor 2. So it is equal to, elaborating. So it's the number of positive real zeros is going to be equal to the number of sign changes of your polynomial. Okay, and then minus a factor of 2. And this isn't or possible. Okay, I'm going to kind of explain. It's probably better me to explain it than actually to write it in there. So what I mean, let's go and look at the number of sign changes. This is a positive to a positive. So did we change signs? No. We went from a positive to a negative. Did we change signs? Yes. So we have 1. That means we're going to have 1 positive real 0. Then we go again, negative to a negative. Did we change signs? No. Then we go to negative to positive. So now we have 2 real zeros. All right? So the number of positive real zeros in this case is 2 or 0. Where did it get 0 from? What I mean is minus a factor of 2. Minus 2 or 4 or 6 or 8. So if we had, let's say we had 10 sign changes, right? That means you'd have 10 positive real zeros, or you'd have 8, or you'd have 6, or you'd have 4, or you'd have 2, or you'd have 0. So in this case, so what you do is you find the number of sign changes, which we have 2, and then you subtract a factor of 2. So it's either 2 positive real zeros or 0 positive real zeros. So if you have 0 positive real zeros, what else could you have? Negative. You could have negatives, or you could have complex, right? No. Yes. So let's go and look at how do you find out the number of negative? So the number of negative real zeros, all right, what we're going to do now is plug in f of negative x. So to plug in f of negative x, we now have for negative x raised to the 5th plus negative x raised to the 4th minus 2 negative x raised to the 3rd minus 5 negative x squared plus 8 negative x plus 16. So what we do is now we figure out what is f of negative x. So any negative number raised to an odd power is always going to continue to be negative, right? Any negative number or any positive or negative number raised to an even power will always be positive. So negative x to the 5th is now negative x to the 5th times 4. So now I have a negative 4 x to the 5th minus x to the 4th plus, that becomes positive. I'm sorry. Negative x to the 4th is positive x to the 4th, right? Then this one becomes, that's still negative, so that's now positive 2x cubed. This becomes positive, so this will now still remain a negative 5x squared. This is now negative.
Why wouldn't it be positive?
Well, because, remember, negative x squared is positive x squared, right? So positive x squared times negative 5. So now it's going to be the same thing. I'm not going to rewrite it for time purposes, but it's going to be the number of sign changes minus a factor of 2. So that works for here as well. So let's count how many we have. We have 1, 2, 3. So therefore, the number of negative real zeros is going to be either 3 or 1. Because remember, I said you have to subtract a factor of 2. So 3 minus 2 is 1. Right? So it could be 3. You could have 3 negative zeros. Or I'm sorry, you have 3 negative zeros, or you could have 1 negative real zero. But it's going to be one or the other. Okay? Cool? Questions? No? Okay.
Do you take the biggest?
All right, this question is asking us how to find the zeros of the polynomial. And so what we need to do is we need to remember, first of all, what the heck are zeros, right? And where did we ever obtain zeros? One thing, guys, if you can kind of think of this like this, x squared plus 7x plus 6 equals 0. A lot of times we'd say, like, solve, right? And we'd say solve for maybe the x-intercepts, maybe say find the roots, or maybe we'd say find the zeros. But you remember you'd factor this, x plus 1, x plus 6, equals 0. Then you set both of those equal to 0. And then you solve for x. And you got x equals -1 and x equals -6. And if I wanted to find actually what the zeros were, I would just write zeros were -1 and -6. Right? Now what we're doing is I'm giving you the zeros. So what I want you to do is I want you to go from here to here. So it's just kind of working exactly backwards. So if I'm given the zeros, the next thing I want to do is I want to write them as a set of linear factors. So just notice that my 0, when it's -1, when I write it in a factored form, it's going to be x plus 1. My 0 is -6. As a factor, it's x plus 6. Because remember, we write it as x plus 6 equals 0. Got it. So we're just going to work backwards. So therefore, if I want to write my zeros as a list of linear factors, I'll write 0 equals x minus 3, x minus 4, and x minus 0. Doesn't really matter. I just changed the order. Should probably x 0 first. Anyways. Then I'm going to, now I just need to FOIL this out. Let's just multiply it out. I guess I might as well do a little FOIL method. FOIL first, right? So x times x is x squared. Outer, x times -4. Then you got your inner. -3 times x. And then you do your last. -3 times -4 is a positive 12. Times x minus 0 is just going to be x, right? I can reduce this to x squared minus 7x plus 12 times x. And then I need to do distributive property with this one. So I get 0 equals x squared, I'm sorry, x cubed, minus 7x times x, which is a 7x squared, plus 12x. And there's your polynomial with those given zeros.
That's all you do?
Okay, that's all you got.
Allows you to do subtraction, not addition. Like how you have x minus 3, x minus 4, why don't you do positive?
Because if my zeros were x plus 3, then the 0 would be x equals -3. Remember, that's the 0, that's the factor. I gave you the zeros, I want you to find the factors. So they are of opposite ends. Okay?
Welcome. So what I have here is 2/3, 1/2, and 3. And what I want to do is show you how to find our function when these are given zeros. Now, our function, or our polynomial that we're going to be determining, we want to have integer coefficients. So that's going to be kind of pose a problem when I have my zeros are fractions, because usually what we do is we set each of our zeros equal to 0. Equals 1, positive 1/2. And x equals 3. Now, once we set them equal to 0, we set them equal to x, then we set them equal to 0. So I'd add 2/3 to both sides. But then I have x equals, or x plus 2/3 equals 0. And then if I'm going to use that as my factor to multiply by my other factors, I'm going to have fractions in those as those coefficients. So I look for a different way to do this. And the way that I'm going to do this is by using my inverse operations. If I multiply by 3 on both sides, therefore I get 3x equals -2. Then I can add 2 to both sides, and I'll have 3x plus 2 equals 0. Now that's going to be a factor I'm going to use. I'll do the same thing here. I'll multiply by 2 on both sides. And therefore I have 2x equals 1. Subtract the 1, subtract the 1. So I have 2x minus 1 equals 0. And here, this is much nicer. Just subtract 3 on both sides. So therefore you have x minus 3 equals 0. Now it's important to understand that 3x plus 2 equals 0 would have been is equal, if you added the 2/3, there's nothing wrong with that. It's not mathematically incorrect. But the problem with that is these are, the exact same equations. They're equivalent to each other. However, if I'm going to use x plus 2/3 as a factor compared to 3x plus 2 as a factor, you can see this doesn't have any fractions and this does. So when I multiply that out with my other factors, this is going to produce fractional coefficients. This will not. And our goal is to produce a polynomial without any fraction coefficients. All right, so now that we have each of our factors, set equal to 0, now I'm going to undo my 0 product property and set them all equal to each other equal to 0. And if you think about doing the 0 product property, instead of working the problem down, if I was working the problem up, this is exactly would be the case that we do to find the zeros. If I gave you a polynomial that was written in its product of its factors, since the product is equal to 0, you would set them all equal to 0 and then solve, and that would be your list of zeros. However, we're not trying to determine the zeros. We already know the zeros. We're trying to determine what is going to be the polynomial. So therefore, then what I need to do is multiply them. So in this case, what I'm going to do is I'm going to multiply these by FOIL. So if I have 3x plus 2 times 2x minus 1. And I'm just going to, my multiplication is going to be, I'll break it out. That's fine. So in this case, I'm going to do my first two terms, which is going to be 3x times 2x. My outer terms is going to be 3x times negative 1. My inner terms is going to be 2 times 2x. And my last terms is going to be 2 times negative 1. So when I multiply these, 3x times 2x is 6x squared. 3x times negative 1 is a negative 3x. 2 times 2x equals 4x. And 2 times negative 1 equals negative 2. I notice that these both have a variable factor of x, so therefore I can combine them. So now I have 6x squared plus x minus 2 multiplied by my other factor, which I did not multiply. So I multiply these two, but I did not multiply it by x minus 3. All right, so I'm kind of doing my work over there. So now I need to apply FOIL again. But in this case, I'm not going to write out FOIL because you can see it's a binomial times a trinomial. But remember, FOIL is just a nice way for us to remember to really apply the distributive property among polynomials. So what I'm really going to do is just multiply the 6x squared times x, 6x squared times negative 3. Multiply the x times x, and then multiply x times negative 3. Multiply negative 2 times x, and then multiply negative 2 times negative 3. And I'm just going to write that down all below here. So 6x squared, and I'll use the vertical method. So 6x squared times x. 6x squared times x is 6x cubed. 6x squared times negative 3 is going to be a negative 18x squared. Plus, next row. X times x is x squared. Since it's squared, I'm going to put it under the x squared, so I can easily combine these. And then x times negative 3 is going to be a negative 3x. Next row, negative 2. Negative 2 times x is a negative 2x. And negative 2 times negative 3 is going to be a positive 6. Then what I'm going to do is I'm just going to add vertically. 6x cubed, there's really no other terms, so that's going to be 6x cubed. Negative 18x plus x squared is going to be a negative 17x squared. Negative 3x plus negative 2x is a negative 5x, and plus 6. So therefore, my function, which I'll write first, f of x is going to equal 6x cubed minus 17x squared minus 5x plus 6. So there you go, ladies and gentlemen. That is how you write your polynomial when given two fraction zeros and an integer or as your zeros. Thanks. So, oh, never mind. What we're looking at for this problem is they're asking us to write the polynomial, right? All right. So, ladies and gentlemen, we have already done a couple of these examples, but when we did examples with this, we used integers. And all we're going to do is we're going to be working backwards. Remember, ladies and gentlemen, if you're given zeros, we found zeros by knowing what the factors were, right? And once we knew what the factors were, then the factors, remember, multiply to give us our polynomial. So when given zeros, the first thing we need to do is write these as our factors. So there is a bit of information, if you guys remember, in your notes that we said if x equals a is a 0, then x minus a is a factor. That was in your notes. It was called the zeros of a polynomial. We wrote it down. And pretty much all it states is if that's what you have, if you have x equals a is a 0, then x minus a is a factor. So therefore, I can write these all as factors. I can write these as x minus 4 times x minus 3i and x plus 3i. Right? And remember factors. Where does the term factors come from? Think of the factors of 6. Two factors of 6 are 2 and 3. Why are they factors? Because they multiply to give you 6, right? So these factors multiply to give me f of x. And that's what the question is asking. What is that polynomial? What does a polynomial look like? So you have it now written as factors. All you have to do is multiply. So we look at what I'm going to do is I'm going to multiply these first. Why do I want to multiply these first? Because I've been doing math for so long that I keep on noticing I always want to multiply difference of two squares first whenever I can because it's very simple. First two terms are the same. Last two terms are the same. Alternating sign. All I need to do is just multiply x squared and the last two terms, which would be negative 3 times 3 would be negative 9 times I squared, which would be negative 1. Negative 1 times negative 9 would be positive 9. Right? Remember, you can still do FOIL, but the middle terms cancel out. All right? Because what I notice is a lot of students now, they take all their binomials and they say, oh, you can just multiply the first and last two numbers. No, that's only for difference of two squares. For this one, we're going to have to use FOIL. We're going to have to make sure I multiply my first term times both terms, and this one by both terms. So when I do that, I get x cubed plus 9x minus, wait, x cubed plus 9x minus 4x squared minus 36. Let's rewrite it in descending order. X cubed minus 4x squared plus 9x minus 36 equals f of x. Any questions? What we did? Yes? Well, you're not communicating to me what you're doing then, right? I mean, the question is asking, find the polynomial. So it's really going to depend on what you're saying your answer is. If you just say this, and you're not telling me that's the polynomial, then you're just kind of writing, you're just multiplying you're just multiplying binomials. I want to see, yes, if I say, tell me what the polynomial, I want you to say the polynomial is this. Or you're going to have to communicate it somehow that the polynomial equals this. Make sense? Okay. Just make sure you're communicating to me what you're doing and why you're doing it. Otherwise, I just assume it's just going to look like you're multiplying, right? So what we want to do here, ladies and gentlemen, is we have our zeros 1 plus square root of 3 and 1 minus square root of 3. Just like you had for your homework quiz, the main important thing you guys need to understand is, remember, these are your zeros, right? Your x-intercepts. We talked about these. The zeros, the solutions. So when we write that, when we were finding the solutions, we said x equaled your zeros, right? Remember those notes we took last class period? We talked about the zeros are equal to the x-intercepts. They're equal to your roots. So x equals 1 plus square root of 3, and x equals 1 minus square root of 3. So then what we did from before we got to here, we set them all equal to 0. To solve x equals this, we had them set equal to 0, right? So what I'm going to do is I'm going to set all these equal to 0. So I'm going to say x minus 1 plus square root of 3 equals 0. And x minus 1 minus square root of 3 equals 0. Does everybody follow me so far? If not, you can raise your hand. It's totally cool. Okay. The next thing, how we got to this point, remember, why did we set them equal to 0? Because of the zero product property. The zero product property said we had two factors that multiplied to equal 0. So what I had is I had this times this equals 0. So that's exactly what I'm going to write. Okay? Right? Remember, we had zero product property. You set them both equal to 0. And then you solve for x, and you get your solutions. You get your zeros. So now I'm just working my way backwards. So now I have two factors, and I need to figure out the polynomial. So I'm not setting them equal to 0 anymore. Now what I want to do is I'm going to call it f of x. When I multiply these out, I want to see what f of x is. And that's what we're trying to get, the polynomial. So here's where it gets a little confusing. This looks pretty confusing. It's not as easy as your typical FOIL, right? First, outer, inner, last. This is like your last term is a binomial. So this can get pretty confusing. If you're going to try to do the first, right, then the outer, inner, last, try to do FOIL with this, you could get a little confused. However, if you're very detailed, you can get through it. It's not bad. But I'll show you a little trick. One thing we can do is use the associative property. And what I'm going to do is I'm going to rewrite my parentheses to include, instead of the last two terms as a binomial, I'm going to write the first two terms as a binomial. And the reason why I wanted to do that is because when the first two terms, when I write them as a binomial, are exactly the same. And now the last two terms, that's supposed to be minus. The last two terms are exactly the same, but I have a difference of signs. Does anybody remember when you have the first two terms the same, the last two terms the same, and a difference of signs, what we call that? Anybody? Difference of squares, right? Because these two are going to multiply to give me a square number. X plus 1, so x minus 1 times x minus 1 squared, and then square root of 3 times negative square root of 3 is a negative 3. I could multiply the middle terms, ladies and gentlemen, and you have to. If you want to follow the rules of FOIL, do it. But what you'll notice is the middle terms cancel out. All right? So I'm just applying the rules of difference of two squares. Now, x minus 1 squared is going to provide me with a perfect square trinomial. That equals f of x. So here I get x squared minus 2x plus 1 minus 3 equals f of x. I'll write the f of x first. F of x is my function equals x squared minus 2x minus 2. So therefore, when I have a function, x squared minus 2x minus 2, it will include the zeros, 1 plus square root of 3 and 1 minus square root of 3. OK? Yes? Why didn't I distribute the negative 3? You mean here?
Yeah.
Well, because remember, it's minus 3. So it's not being multiplied by negative 3. It's minus 3. That's why I didn't distribute it. Does that make sense? Remember, it's like, well, remember, I had something like this, x plus 4 times x minus 4. So when you multiply this out, you get x squared minus 16. You don't distribute like the negative 16. It's x squared minus 16. The only difference was, I'm getting tangled around. The only difference is now it's just a binomial that's being multiplied. Instead of x squared, it's x minus 1 squared minus 3. Does that kind of see it? I know it's a little bit, looks a lot more different than that, but it's the same kind of process. Cool? Yes?
So, since the, what do they call it, radicals, since they're opposites, they equal negative 3?
Since they're, yeah, yes.
So
That's a positive and that's a negative.
So it's always a negative.
Yeah, positive times a negative will give you a negative.
Okay.
Right? And then square root of 3 times square root of 3 gives you 3. But anybody questions on this?
All right, given this equation, given these zeros, what we have is we have 2 and 4 plus I. Now, what they want us to do is they want us to find a polynomial with given those zeros. So one thing I could do is we can write these as factors, right? When you write zeros, to write as a polynomial, it's best to write what the factors are. So this would be x minus 2, and this would be x minus 4 plus I. Right? X minus 4 plus I. Now, the one thing, you could multiply this and you're going to get a polynomial, but it says they want a polynomial to the third degree. And the other thing you need to know is whenever you're given a 0 as a complex number, you also know that the conjugate 0 is also available. So therefore, I can write this as a factor as well, x minus 4 minus I. So whenever given a complex number, also know that your conjugate of your complex number is also a 0. So now I have 3 factors. So I know my polynomial is going to be to the third degree, which I believe this question actually asks. So there's a little bit of trick on doing this type of problem. We could multiply this just like 3 binomials, right? Pretend that this is a term in itself. But an easier way to do this is what I'm going to do is I'm going to regroup these. So I'm going to write this as x minus 2 times, and I'm going to group the x minus 4. Let's see, x minus 4 plus I, and x minus 4 minus I. And the reason why I want to do this is because now, if you look at this, this is really kind of like an A. Let's pretend x minus 4 is A. A equals x minus 4. So therefore, it's A plus I times A minus I. And now what you know is we have a difference of 2 squares. So when I multiply these, I'm going to get rid of my middle terms. So this is something very important that you always want to look out for in mathematics. So what happens is, let's multiply these. So x minus 2. So I have x minus 4 times x minus 4 is going to be x minus 4 squared And then this is going to give me I times negative I is going to give me a negative I squared. And then, let's see, we get something. Multiply these. Yeah, I'll get my product here. I squared is going to give me negative 1. So let's go ahead and figure out my x minus 2. X minus 4 squared is going to give me x squared minus 8x plus 16. And then here I have a I squared minus 1 is going to give me a negative 1, but times I squared is negative 1. Negative 1 times this negative is going to give me a positive 1. So therefore I have x minus 2 times x squared minus 8x plus 17. Now I have to multiply my binomial times my trinomial. And again, we're just going to use, just make sure you multiply every term times every term. So let's see, x times x squared is x cubed. X times negative 8x is negative 8x squared. X times 17 is going to give me a positive 17x. Negative 2 times x squared is going to give me negative 2x squared. Negative 2 times negative 8x is going to give me a positive 16x.
Can Ms.
And
Winfield
negative 2
and
times
Ms.
17.
Altman please report to the gym? Ms. Winfield and Ms. Altman,
Negative 2
please
times
report
17
to the
give me a
gym.
negative 34. I can just combine these now to give me x cubed. Let's see, minus 10x squared. Let's see, plus 33x minus 34. So that would be my third degree polynomial given the zeros of 2, 4 plus I, and 4 minus I.